Let's see. 2.2.1, the IUPAC name of compound E. Okay. So let's go ahead and take a look at compound E. We have a carbon with a double bond. So that is a characteristic of an alkene. Okay. How many carbons do we have in our longest chain? Let's see. If we start numbering from this carbon, we're going to have 1, 2, 3, 4. Even if we go down, we still have 4 carbons on our longest chain. So that seems like we have 4 carbons on our longest chain. So for 2.2.1, we know that we have but. Let's go ahead and figure out everything else. We have to start numbering from the side closest to the double bond. Okay? If we are saying that we have 1, 2, 3, 4 carbons, then if we start numbering from this side, then we will get to the double bond first, okay? Because if we start numbering from this side, then the double bond will be on the third carbon, and that's not what we want. We want the side closest to the double bond, which will be this side. So this is our longest carbon chain, okay, which is but. So we've built one in one because our functional group is on the first carbon, okay? And as you can see, we have methyl and methyl. One methyl is on, so we have 2 point, so this is the second carbon and this is the third. 2.3 dash dimethyl but one in, okay? Right, so that is our IUPAC name of compound E. 2.2.2, we are looking for the IUPAC name of H. So let's go ahead and take a look at H. Okay, on H, carbon double bonded to oxygen. And this carbon is sandwiched by 2 other carbons. That is a ketone. So I'm going to have butane 2 on, okay? I think even if you don't include this 2, it would still be correct. Because if you have 4 carbons and on a straight chain, right? And it is a ketone, then the oxygen bonded to the carbon should be on the second carbon. If that is not the case, then it becomes an aldehyde. So butane 2 on. But I also think that if you don't put these 2, you would still be correct. That is 2.2.2. Okay, let's move to the question that follows. We have butane 2 on. Okay, right. 2.3. 2.3, we are looking for the structural formula of compound B. So let's go ahead and take a look at compound B. That is 2.3.1. So compound B, a carbon with 3 hydrogen, followed by 3 carbons with 2 hydrogen each. So 1, 2, 3 with 2 hydrogens each. Okay, and then after that we have another carbon which is double bonded to an oxygen, one other oxygen which is bonded to its carbon. Okay, so this is the structure you're supposed to have for compound B. Obviously, we need to fill out our hydrogens. Okay, you cannot leave it like this. Only I can do that and not you. So this is the structural formula of compound B. Let's see if we have the correct number of carbons. So we have 1, 2, 3, 4, 5, 6. This is 1, 3 makes it 4, 5, 6. I think we are good to go. Okay. Structural formula of compound C, 2.3.2. Let's go ahead and take a look at that. 2.3.2, structural formula of compound C. We have 4-ethyl-3.3 difluorohexane. So I'm going to start by taking care of hexane. I need 6 carbons. So 1, 2, 3, 4, 5, 6. On the third carbon, I have difluoro. There we go. And on the fourth carbon, I have ethyl. Ethyl will look something like this, okay? I have a branch with 2 carbons, right? So now I just need to fill out my hydrogens and I am done, okay? So let me leave that for you. Go ahead and fill out all the hydrogens that are required. Okay, right. So this is the structural formula of compound C 2.3.2. 2.3.3 general formula of the homologous series to which compound E belongs. Compound E is an alkene, so the general formula should be CnH2n. Yes, not plus 2, not minus 2, just CnH2n. 2.3.4 structural formula of functional group of compound F. Compound F, carbon double bonded to an oxygen sandwiched by 2 other carbons. That is a ketone. The structure of the functional group should look like this. Okay, we should not have carbons on these. We should not have hydrogens on these 2 carbons. So if you put hydrogens on those carbons, then it is then not correct. Okay, you are now drawing the structure of propanol, right? And no longer the functional group of ketones. That is 2.3.4. 2.3.5, IUPAC name of the alcohol needed to produce compound B. So for compound B, we have the structure. Let's use the structure instead. Okay, if you come here and put a line, the carbon that is bonded, or the part of the structure that is bonded to 1 oxygen is from the alcohol. Which alcohol has 1 oxygen? Not 1 oxygen, but 1 carbon, okay? That is methanol, right? Yeah, the alcohol with 1 carbon is methanol. 2.4.1, 2.4.1, we're looking for letters of a compound that is the letter of a compound that is a functional isomer of compound G. So if you take a look at compound G, we have an acid because of the functional group, which we can identify right there. And that acid has 1, 2, 3, 4, 5, 6 carbons. So we are looking for an ester with 6 carbons. It will be a functional isomer of compound G. If you look at B, in B we have 6 carbons. So the answer to 2.4.1 is B. That ester right there with 6 carbons will be a functional isomer of G. And then 2 compounds that are chain isomers of each other. Okay, G and D. D is hexanoic acid. It is a straight line hexanoic acid. Okay, and compound G, it is an acid with 6 carbons, so they should be chain isomers of each other. Same molecular formula, just different chains.
Is this organic compound a primary, secondary, or tertiary alcohol? We're supposed to give a reason for the answer. So let's go ahead and take a look. Right, so in compound A, let's just zoom in on compound A. We have 1, 2, 3, 4 carbons. So that should be butanol, right? We do have a branch here that I'm not accounting for, but we're going to take care of that. So let's take a look. Let me just circle that. This is our longest chain. We can take this as our longest chain. Even though if we go up, we would still get the longest chain of 4 carbons. Let's just take that as our longest chain. And then we have a branch on the second carbon and the functional group. Right, that is what we are dealing with. Let's go back to the question. Is it a primary, secondary, or tertiary alcohol? Well, this is a tertiary alcohol. So let me just write that down first and then explain to you why I'm saying so. This is a tertiary alcohol, right? Why do we say that it is a tertiary alcohol? It is because, take a look at these. This carbon that is bonded to OH. The carbon that is bonded to OH is bonded to 1, 2, 3 carbons, right? So if the carbon that is bonded to OH is bonded to 3 carbons, it makes it a tertiary alcohol. If it was bonded to 2 carbons, it would make it a secondary alcohol. And then if it is only bonded to 1 carbon, it would make it a primary alcohol. So right, it is a tertiary alcohol because the carbon bonded to OH is bonded to 3 other carbons. There we go. So that is 2.1.1. Let's take a look at 2.1.2. Write down the IUPAC name for the above mentioned compound. Okay, so like we have figured out, we have 4 carbons on our longest chain. So that is butane. And then which carbon is our functional group found? Well, if we start counting from the left, we have 1, 2, 3. But if we start counting from the right, we have 1, 2. So clearly we have to start numbering our carbons from the right. So we're going to have butane, 2, all. But we need to account for that branch there. We need to account for that branch. So on the second carbon, we have 2-methyl. So there we go. 2-methyl butane 2-ol. That is the IUPAC name of our compound A. 2.1.3. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the product that is formed. Elimination reaction. So let me just write that structural formula without condensing it. So this is OH, and then hydrogen. We need another. Okay, here we have a branch, so let's put that there. And then elsewhere we have hydrogens. Okay, so which elimination reaction can an alcohol go through? Because this is an alcohol that you're dealing with, right? So the elimination that an alcohol can go through is dehydration. It is dehydration. The alcohol loses 1 hydrogen and an OH, right, making it H2O, hence dehydration. That is the only elimination reaction alcohols can undergo through, right? So it means that the structural formula of the major product formed should be an alkene, right? This question is very specific. Major product, right? We have a major product and a minor product for these reaction. We have a major, well, for the product of an elimination reaction of alcohol, right? Dehydration. We have a major product and a minor product. So this is just the alcohol. This is not the answer. This is not the answer. This is just the alcohol. We just draw in the structure of the alcohol so that we can better make sense of it. So the major product of dehydration that compound A will undergo will look like the following. So we have 1, 2, double bond, carbon, carbon. So there we go. And then hydrogen everywhere else. Hydrogen everywhere else. So 4 bonds on that carbon. It is satisfied, and let's just fill out hydrogens everywhere. So let's check the number of bonds. This 1, 2, 3, 4. So everything is fine. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Right. You have to calculate the number of bonds to avoid making any mistake. We also need our branch. I'm forgetting to put the branch here. Because we have a branch here on the second carbon. So we don't have a hydrogen here, but rather we have a branch. So that is what we have. That is what we are dealing with. Let's check if the number of carbons is still intact. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. All right, let's move to the question that follows. 2.2, 2.2.1. Consider the organic compound B. 2.2.1. Define the term functional isomer. Okay, so compound B is pentane 3-on, so that is a ketone. But well, the question wants us to define the term functional isomer, so let's go ahead and do that. Functional isomer, organic compounds with the same molecular formula but different functional groups. Same molecular formula but different functional group. That is a functional isomer. And then 2.2.2, I'm expecting that the question is gonna have something to do with isomers. Write down the homologous series to which the above mentioned compound belongs. Okay, compound B. This is 2.2, and 2.2.2 is a sub-question of 2.2.2. Okay, I was starting to ask myself which above mentioned compound, because I was thinking 2.2.1, but it is compound B that we are referring to. So compound B is a ketone, but the name of the homologous series is actually not ketone. It is ketones. It is in plural, by the way. Yeah, it's one of those things that we usually overlook. But the name of the homologous series is not ketone. It is ketones. Yeah, if you go to your exam guidelines, that is exactly what you're going to find. You're not going to find the homologous series ketone. No, the homologous series is ketones, right? We're just being, more precise. We live in no stone unturned. Okay, that is 2.2.2. Let's do 2.2.3. IUPAC name of its functional isomer. So the functional isomer of ketones is aldehydes, right? The functional isomer of ketone is aldehydes, right? They have the same, a aldehyde looks very similar to a ketone, but the only difference is that the double bond oxygen is at the end. So here we have pentane 3-on. So the ketone that you're looking for is pentanol. That is, the aldehyde, not the ketone, I meant. The aldehyde that we're looking for is pentanol. Pentanol and pentane 3-on are functional isomers. So what are we looking for? IUPAC name of its functional isomer. Oh, okay, we're done then. We're looking for the IUPAC name. I thought we were looking for the structure, right? But we're just looking for the IUPAC name. The IUPAC name is pentanol, right? 2.2.3. What about 2.2.4? Letter that represents its positional isomer. So we are dealing with pentane 3-on, right? So the positional isomer is pentane 2-on. It has only one positional isomer, right? Because we have 1, 2, 3, 4, 5 double bond oxygen, right? If you put this oxygen here, it is pentane 2-on. Same is true with when you put it here, you'll still have pentane 2-on, because we have to start numbering from the side closest to the functional group. So we're looking for pentane 2-on here on our table. Letter that represents its positional isomer. Okay, let's take a look. Pentane 2-on looks to be compound E. It looks to be compound E. Because take a look at compound E. We have 1, 2, 3, 4, 5. So that is where our pent is coming from. And then on the second carbon, double bond oxygen. So there we go, pentane 2-on. That is compound E. So the letter that represents its positional isomer, the answer is E there. The answer is E. It is compound E, pentane 2-on. Write down the balanced equation using molecular formula for the complete combustion of compound F. So let's take a look at compound F. Compound F is 1, 2, not 2 anymore, but actually 3, right? So we have 5 carbons in total. So that is C5. How many hydrogens do we have in total? We have these 3 here. We have these, which gives us 6, and we have 3. So that is 12, right? So H12. And then it is a combustion reaction. So it is excess oxygen to give us CO2 plus H2O. We just need to balance this equation. So C5, C1. What do? We put 5 and put in 5, the carbons are balanced. And then we move to the hydrogen. H12, H2. So we put 6 in attempt to balance the equation. And now take a look at this. We have O2 here, and here we have 5 multiplied by O2, which is 10, plus 6 multiplied by O2, which is 6. So this is 16. And then in order to get 16 on the left hand side, we must multiply with 8. So there we go. We have our balanced combustion reaction. Here we go.
Homologous series to which compound B belongs to. So let's go to our compound B and see what is happening. It will be easy to see that compound B is an ester because of this functional group that we have here. Compound B is an ester. So the answer to 2.1.1, that compound B is an ester. And then the second question, 2.1.2, we're looking for the IUPAC name of the same compound. So this is how you actually name an ester, ladies and gentlemen. You're going to come here to the structure and you're going to put a line that divides the oxygen with the double bond from the oxygen with the single bond. And then the part of the structure that has the oxygen with the single bond is coming from the alcohol. And the part of the structure that has the oxygen with a double bond is coming from the acid, because we know that in order to form an ester, you need an alcohol and an acid in the presence of H2SO4. So let's look at our alcohol. Our alcohol that was used in making this ester is methanol. Why are we saying it is methanol? Because of this single carbon right here. And the acid that was used to make this ester is propanoic acid. Why are we saying so? These 3 carbons that we have there. So when we name this ester, the name is going to be methyl propanoid. Methyl propanoid. Right. So this methyl here is coming from the fact that the alcohol that was used is methanol. If the alcohol that was used was butanol, then the name would start by saying butyl. And then the propanoid is coming from the acid that was used, propanoic acid. Let's move to the second question, 2.2 and 2.2.1. An alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Write down the role of the concentrated sulfuric acid in this reaction. So sulfuric acid in an esterification acts as a catalyst. So the answer to 2.2.1 is catalyst. It acts as a catalyst. It speeds up the reaction. You can also say that. And then the answer to 2.2.2, names of the alcohol and the organic acid used to prepare compound B. So we have already deduced which alcohol was used and which acid was used when we were naming our compound B, right? So now we're just gonna say the alcohol that was used is methanol and the acid that was used is propanoic acid. The acid that was used is propanoic acid. 2.2.3, name of the type of reaction that is taking place. Obviously the name of the reaction that is taking place is esterification. And other books will say condensation, which is also correct. I see that option time after time in memos. That is 2.2. Let's move to 2.3. So in 2.3, from the table above, consider compound C. So let's go to compound C and see what I have. Compound C, we have an acid. This is the functional group of an acid. Ethanoic acid to be specific. Let's go to the questions. 2.3.1. So the first question, 2.3.1, write down the name of the functional group of compound C. So we've already deduced that compound C is an acid, right? The name of the functional group of acids is carboxyl. So we have carboxyl group. That is the name of the functional group. And then 2.3.2, to which homologous group does compound C belong to? It is the carboxylic acid. That's an easy question to answer. It is a carboxylic acid. 2.3.3, differentiate between the terms functional group and homologous series. This question is actually just asking you to define homologous series and functional group. So let me just remind you, homologous series is a series of organic compounds that can be described by the same general formula. A series of organic compounds that can be described by the same general formula. While functional group, on the other hand, is a bond or an atom or a group of atoms that determines the physical and chemical properties of a group of organic compounds. There we go. You just need to define functional group and homologous series for 2.3.3. 2.4 for the table above, from the table above actually, consider compounds A, D, and F. And then the first question, write down the homologous series to which they belong to. So let's go to compound A. Compound A, we have an OH, which is the functional group of an alcohol. So we know that compound A is an alcohol. And then compound D, we also have another OH, so that is another alcohol. Let's look at compound F. It ends with ol, so we have another alcohol again. So A, D, and F are alcohols as far as the homologous series is concerned. So the answer to 2.4.1 will be alcohols, because A, D, and F are all alcohols. 2.4.2, compound A and D are isomers. As what type of isomer will they be classified? So let's go to A and D. A and D. So A, let me just write down A real quick for the sake of clarity. So for A, we have something like this. We have hydrogens everywhere else. And then let's look at D. So for D, we have condensed structural formula, which we're going to write in full now. So we have a carbon with 3 hydrogens. We have the second carbon, and then on the second carbon, we have 1 hydrogen and an OH. And then the third carbon with 3 hydrogens. So what type of isomers is compound A and D, not B? Excuse me, compound A and D. So compound A, the OH is on the first carbon, and then for compound D, the OH is on the second carbon. So they have the same molecular formula, but just different position of the functional group. So those are called positional isomers. So 2.4.2, the answer here is positional isomers. They will be known or referred to as positional isomers, compound A and D. The third question, 2.4.3, we asked to draw the structure of compound F. Let's go ahead and look at compound F. So for compound F, 2-methyl propane-2-ol. So let's start with the prop. So as soon as we see prop, we know that we need 3 carbons. So we have 1, 2, 3, and then 2-ol. This 2-ol tells us that the OH is on the second carbon. So let's have that OH right here. And then this 2-methyl, we have a branch on the second carbon. So we're going to have 1 carbon there. And then now we just left out with the hydrogens. And we have the structural formula of compound F just like that. Let's go ahead and move to 2.5. So 2.5, we're interested in compound G and compound E. 2.5.1, we're supposed to name compound G. Let's go to compound G. So compound G, the first thing that we must look for is the longest carbon chain. It is easy to see that this will indeed be our longest carbon chain. Let's count that. 1, 2, 3, 4, 5, 6. That is hex. And then as soon as I see BR, I know that it is a haloalkane, right? So it will be hexane. It will be hexane. Now I'm just left with the branches. Where do I start numbering? If you start numbering from the left, on the second carbon, you have Br, you have bromo. And then if you start numbering from the right, on the second carbon, you have methyl, you have dimethyl, right? So the question now is, what takes preference between a branch and a halogen? Well, according to the exam guideline, nothing takes preference between the halogen and the branch. You just have to start numbering from the side that will lead to the smallest number. What do I mean by that? If we start numbering from the left, then we're going to have 2 for bromo, right? And then this is 2, 3, 4, 5. And then we're going to have 5,5 for that dimethyl. And then these numbers will give us 12. If we start numbering from the right, we're going to have 2.82 for the dimethyl, right? And then we're going to have 5 for the bromo. So this is 2 plus 5, which is equals to 9. If we start numbering from the right, we have the smallest number, and that's what we need to do. Nothing is going to take preference between the halogen and the branch. So we're going to have 5 bromo. We're going to have 5 bromo dash 2.2 dash dimethyl hexane. 2.2 dash dimethyl hexane. And that is the name of our compound G. The last question, structural formula of compound E. Let's go ahead and look at compound E. So compound E, we have 2.4 dimethyl pent 1-ene. So pent 5 carbons, 1, 2, 3, 4, 5. And then we have a double bond on the first carbon. We can tell from this pent 1-ene. So there we go. We have a double bond. And then on the second carbon, we have a branch with 1 carbon. And then on the fourth carbon, we also have another branch with 1 carbon. So now we're essentially done. We just left with filling out the hydrogens. So let's go ahead and do that. Yeah. So 1, 2, 3. We still need another hydrogen. And then 1, 2, 3. It's a painful exercise, but yeah, we have to do what we have to do. Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5 with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the third carbon. So we're going to have pentane 3-one. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1 all, and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to one other carbon. So that makes it an aldehyde. So we have pentane 1 all and pentanol. Pentane 1 all is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1 all. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1 all, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole-dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent 1 all will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1 all? Right, only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again in pentane 1 all we have hydrogen bonding. In pentane 1 all we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1 all. Higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1 all has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D, we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkanes, right? Well, you can draw compound C fairly quick by saying C 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkanes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases. How can we boil down these complex concepts to a few bullet points? Well, if a reaction starts with an alkene and you get whatever product you're going to get, then that reaction is an addition reaction. If a reaction starts with whatsoever it is starting with and it ends up with an alkene, then that reaction is an elimination reaction. And if our first condition is not met and our second condition is not met, then that reaction is a substitution reaction. What am I even saying? Let me show you what I'm talking about by answering this question. Let's look at 4.1. Consider reaction A and write down the type of reaction that takes place. So reaction A is right here. So let me go through my conditions and see which one is met. Do we start with an alkene? No, we don't. We start with a secondary alcohol. Do we end up with an alkene? Yes, we do. We have propene as our product, right? So we know fully well that from that only, our reaction is an elimination reaction. Our second condition is met. So the answer to 4.1 is elimination. It's elimination. Just because we know that if a reaction ends with an alkene, it's elimination. If it starts with alkene, it's addition. And then if none of that is correct, then it is a substitution reaction. Let's do 4.2 and 4.2.1. Reaction B represents a hydration reaction. Let's look at B. At B, we're starting with propene and we end up with a secondary alcohol. And then we are told that that reaction is a hydration reaction. Right, and then now what we're asked to do is to define hydration reaction. It is the addition of water to a compound. That's it. That's the definition. It's the addition of water to a compound. That's what we mean when we talk about a hydration reaction. We add in H2O to a compound. And the follow-up question, 4.2.2, write down the name or formula of the catalyst used for this reaction. So a catalyst you can use for a hydration reaction is H2SO4. So we can use sulfuric acid as a catalyst for a hydration reaction. Let's look at 4.3 and 4.3.1. During reaction C, a specific rule is followed to determine the major product when HBr is added. Let's look at reaction C. So for reaction C, we are starting with propene and we end up with 2-bromopropene. So let's go back to our conditions. Do we start with an alkene? Yes, we do. So we know that reaction C is supposed to be an addition reaction. Well, the answer to 4.3.1 was actually very difficult to find. But if you visit the CAPS document and other relevant resources, you'll find out that for hydrohalogenation, our addition reaction in this case, we need no water because alkenes cannot react with pure water. And then apart from needing no water, we need a concentrated strong acid. So we need a concentrated strong acid for this reaction that we have in 4.3.1. It is an addition reaction
namely hydrohalogenation. We're adding a hydrogen and a halogen. 4.3.2, use structural formula and write down the balance equation for this reaction. So propene plus HBr. Let's go ahead and do that. So we're going to have 1, 2, 3 carbons, right? So 1, 2. Now we just need to add our hydrogens, and we're supposed to have something like that, plus HBr to give us something. If you look back to the equation statement, it says that during reaction C, a specific rule is followed to determine the major product when HBr is added. So now you actually have to know that rule in order to answer this question. Well, to some extent, we know that this double bond is going to break, and either one between H and Br is going to come to the second carbon, and then the other is going to come to the first carbon. So do we get Br on the second carbon, or do we get Br on the first carbon? You need to know where to place that Br, because if you place it at the wrong location, then you lose a mark. But there's a rule for that. There's a law for that. Markovnikov's rule. So basically what it is saying is that the hydrogen is going to go where there's a lot of hydrogens, and then the halogen is going to go to the other spot. So if you look at this carbon here, it has 2 hydrogens, and then the carbon in the middle has 1 hydrogen. So the hydrogen will tend to go to the carbon with a lot of hydrogens already. So that Br, it will usually go to the middle, because that's where we have the least number of hydrogen. So our product is going to look like this. Br is going to come to the carbon in the middle, and the hydrogen is going to come to the first carbon. And then now it's just a matter of filling out our hydrogens. So this is our major product according to Markovnikov's rule. And then Br being on the first carbon and H being on the second carbon is our minor product. This is our major product. Yeah, usually when this reaction occurs, this is the product, right? 4.1. Identify the type of reaction taking place at, so let's go to reaction D. Reaction D. Yeah, this one is going to be easy because we know our conditions. Do we start with an alkene? No. Do we end with an alkene? No. So we know that it is substitution. It is substitution. There isn't a lot to think about there. And then 4.2, which reaction are we interested in? We are interested in reaction F. In reaction F, do we start with an alkene? The answer is no. Do we end with an alkene? The answer is still no. So again, that is a substitution reaction. That is a substitution reaction. It cannot be otherwise. And then 4.5.1. Reaction E is a hydrogenation reaction. Let's look at reaction E real quick. We're starting with propene and we're ending up with propane. So it is indeed a hydrogenation, right? And then what does the equation say? Write down the 2 reaction conditions for this reaction. 2 reaction conditions for hydrogenation. So we need heat, and another thing we need is a catalyst. We need a catalyst. Yeah, which catalyst in this case? We need palladium, platinum, nickel, and so on. Right. And then 4.5.2, name one use of hydrogenation in the food industry. Well, I will leave that one to you.
This question is difficult, okay? But let's go ahead and give it a try. The first question, 3.1, we're supposed to define the term boiling point. So boiling point is the TP at which the VP is equals to the ATP, right? So the temperature at which the vapor pressure is equals to the atmospheric pressure. 3.1. Let's take a look at 3.2. In 3.2, write down the conclusion that can be made for curve P. So let's go ahead and read through our question statement and sort of figure out what is happening. So the relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. Curves P, R, and S are obtained. All compounds used as straight chain molecules. Right. And then write down the conclusion that can be made for curve P. As we can clearly see, as the molecular mass increases, the boiling point is increasing. So that is the conclusion we can make for curve P. Well, the same is true for curve R, and the same is true for curve S. As the molecular mass increases, the boiling point also increases. Why is that the case? We're going to address that sometime later. That is 3.2. 3.3, explain the answer to question 3.2 in terms of the structures of the compounds. Okay, so now we actually have to support why we are saying that as the molecular mass increases, the boiling point increases. Well, not support, but justify why that is the case. So let's go ahead and try doing that. Okay, so when we're told that we have straight chain organic compounds, right? As the chain is increasing, the London forces are increasing. Okay, so that is the reason why when the molecular mass is increasing, the boiling point is increasing. It is because when you increase the number of carbons on your straight chain, the London forces are going to be increasing between those carbons. So that is the reason we're supposed to give for 3.3. I wrote it down. It says, as the chain length increases, the London force increases, and the boiling point will increase as a consequence because the intermolecular forces, the strength of the intermolecular forces is increasing. That is 3.3. 3.4, 3.4.1. Curve R represents alcohols. Well, we can deduce that curve R represent alcohols without being told. We can deduce that because we have an alcohol, we have a carboxylic acid, and we have aldehydes. We know which compounds consist of which intermolecular forces and which intermolecular forces are stronger than which. We know all that. So yeah, and they're telling us, but we already know. They don't have to. Okay, and then 3.4.1, which homologous series is represented by curve S. So we have aldehydes, carboxylic acids, and alcohols. We know that R is alcohol. Why is R alcohol? Because we have one side of hydrogen bonding, and S is aldehyde, right? Dipole forces. And P is carboxylic acid, where we have two sides of hydrogen bonding. Okay, so this is our acid, this is our carboxylic acid. What is the question saying? Which homologous series is represented by curve S? Aldehyde. Our homologous series is aldehyde. Aldehyde is the homologous series. Okay. 3.4.2. Explain the answer to question 3.4.1 by referring to the strength of intermolecular forces. So, okay, this is the train of thought. Between carboxylic acids consist of two sides of hydrogen bonding. Alcohol consists of one side of hydrogen bonding. Aldehydes consist of dipole, right? Hydrogen bonding is stronger than dipole. So for the same molecular mass, aldehyde should have the lowest boiling point compared to alcohols and carboxylic acids. So that is 3.4.2. Let's move ahead. Okay, we're moving up and not down. So we have 3.5. Let's take a look at 3.5 and hear the stories. 3.5.1, Write down the molecular mass of the compound with a boiling point of 97 degrees Celsius. For curve R, the molecular mass of the compound with a boiling point of 97 degrees Celsius. So let's go ahead and have a look. So here we have compound R. These are our boiling points on the y-axis. So let's go ahead and identify 97. 97 should be somewhere here, right? That's where we should have 97. And the molecular mass between 50 and 70, so that is 60. So the answer to 3.5.1, we have 60 grams per mole. 3.5.1. So a straight chain alcohol with a molecular mass of 60 grams per mole. Okay, so let's see. We have methanol. What else? We can also just write an equation for this. I think we can write an equation. Let's see. For an alcohol, we know fully well that we are supposed to have CnH2n plus 2O. Okay, this is the general formula of an alcohol. CnH2n plus 2O. We know that the molecular mass of carbon is 12. So we can say 12 multiplied by n plus that of hydrogen. So hydrogen, we have 2n plus 2. Okay, so we're going to have 2n plus 2 plus that of oxygen. Of oxygen, we have 16. Okay, this is equals to 60. So let's find the value of n in attempt to finding the alcohol with the molecular mass of 60. So we're going to have 12n plus 2n, that will be 14n. 2 plus 16, that is 18. This is equals to 60. So I have 14n being equals to 60 minus 18. 60 minus 18 should give us 42. So n is equals to 42 divided by 14. I think this is supposed to be 3. Okay, let me just verify if it is indeed 3. 4, 4, 4, 12, 2 plus 1, 42. So, right, n is equals to 3. So we know that our alcohol is C3H3 multiplied by 2, that is 6, plus 2, 8. So 3 C3H8O. This is propanol. This is propanol. So there we go. We have identified the alcohol. I'm sure there's other ways you can use to identify alcohol, but that is just, yeah, the approach I'm deciding to take. 3.5.2. 3.6. Two compounds A and B used in this investigation have a molecular mass of 74 grams per mole. A has a boiling point of 118 degrees Celsius and B a boiling point of 142 degrees Celsius. Explain the difference in these boiling points by referring to the structures of these compounds. Okay, so we're looking for two molecular mass, two compounds. Okay, so let's focus on compound A. Compound A has a molecular mass of 74 grams per mole, and then it has a boiling point of 118 degrees Celsius. So let's identify what A is first. Okay, so let's go to our graph. The molecular mass is 74. How many blocks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 blocks between 70 and 90. So 1, 2, 3, 4, 5 should give us 80. So we have 80 right here. So that tells me that, let me see. That tells me that 1, 2 should be 74. So if I want to find a molecule with a compound with a molecular mass of 74 grams, then I need to draw a line like that. So, okay, we have 74 grams per mole and a boiling point of 118. So, where can I find 118 here? Okay, I think I find it on the alcohol. Okay, let me erase here so that I can see what is underneath. I think I find it on the alcohol. This right here should have a boiling point of around 118. So compound A is an alcohol. I know that for sure. It cannot be compound. It cannot be S, because S is way below 100, and it cannot be P. It cannot be on the line P, because you can see it is very close to 150. So A is the alcohol. Let's take a look at B. What is the data I have for B? So B also has a molecular mass of 74 grams per mole and a boiling point of 142 degrees. Okay, so 142, we can clearly see that it is this one that we have up here, which is our acid. So B is the acid. So what does the question say? The question says, the question is up here. The question says, explain the difference in these boiling points by referring to the structure of these compounds. Okay, so we have the alcohol and the acid. In alcohols, we have one side of hydrogen bonding, while in an acid, we have two sides of hydrogen bonding. The intermolecular forces on the acid will be stronger than that on the alcohol, requiring more energy to overcome the intermolecular forces. And that's a consequence. We're going to have a higher boiling point on compound B, the acid.
Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to two other carbons, and because of that we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5, with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the third carbon. So we're going to have pentane 3 own. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to one other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanal, which is dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pentanol will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentanol? That only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces, and then again in pentanol we have hydrogen bonding. In pentanol we have hydrogen bonding, so that will lead to ketone having a higher than vapor pressure compared to pentanol, higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentanol has stronger intermolecular forces, so it will require more energy to overcome the intermolecular forces, and then as a consequence it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkenes, right? Well, you can draw compound C fairly quick by saying C, 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkenes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases.
The temperature at which the vapor pressure is equals to the atmospheric pressure is what we refer to as the boiling point, and that is 3.1. So from here on, let's go ahead and take a look at 3.1.2. What does the question say? which of the compounds A, B, or C is mainly in the liquid phase at 100 degrees Celsius? My grade 10 learners can answer this question, but let's take a look and see what is happening. So we have organic compounds A, B, C, and D, but we are only concentrating on A, B, and C as our question instructs. So the question is, which compound of these three is mainly in the liquid phase at 100 degrees Celsius? Right, so it must not be a gas at 100 degrees Celsius. It must not have boiled at 100 degrees Celsius. So let's take a look. Compound A. The boiling point of compound A is 78 degrees Celsius. So at 100 degrees Celsius, we are above the boiling point of compound A. So it is already a gas at 100 degrees Celsius because it boils at 78. Same is true with compound B. Compound B has a boiling point of 46 degrees Celsius. So at 100 degrees Celsius, it is above its boiling point. So it has turned from liquid to gas already. So C is the compound that is in the liquid phase at 100 degrees Celsius. If we take a look at A, B, and C. So the answer here to 3.2, 3.2 and not 3.1.2. 3.2 is C. C is at the liquid phase at 100 degrees Celsius because it has not yet reached its boiling point. Okay, explain the difference in the boiling points of compound A and B. That is for 3 marks. So let's take a look at compound A and compound B and see how they differ. Well, they are all haloalkanes, but they differ in branching. The structure of compound A, let's take a look. 1, 2, 3, 1, 2, 1, 2, third carbon, fourth, 1, 2, and chloro. And then this is A. Let's take a look at B. Right. At B, we have 1, 2, carbon, hydrogen, 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 and then hydrogen. Well, let's just leave the dash there. And then we have another carbon that serves as a branch. And then carbon, hydrogen, hydrogen, chloro. So this is compound B. As you can see, in compound B, we have this branch here. And then in compound A, we don't have a branch. So the difference in the boiling points of compound A and B is because compound A is less branched compared to compound B. So compound A is going to have more surface area, stronger intermolecular forces, and thus more energy is required to overcome the intermolecular forces in compound A. That is why we see a higher boiling point compared to compound B, because it is less branched. Okay, so that is 3.3. What about 3.4 and 3.4.1? Let's go ahead and take a look. Consider the boiling points 75 degrees Celsius, 120 degrees Celsius, and 126 degrees Celsius. Which of these values represents X, the boiling point of compound D? So let's go ahead and take a look at compound D and see if we can make sense of this. Compound D seems to be an aldehyde. Let's take a look. Carbon, 3 hydrogens, carbon, 2 hydrogens, carbon, 2 hydrogens, carbon, oxygen, 1 hydrogen. So compound D is indeed a aldehyde, but compound C is an alcohol. Right, so the boiling point of compound D must be lower than that of C, because aldehydes we have dipole, and then in alcohol we have hydrogen bonding, and hydrogen bonding is way stronger than dipole. So X should be less than 118 degrees Celsius at least. So take a look at this. We have 120. So this can't be correct because D must have a lower boiling point compared to C, because D is dipole and C is hydrogen bonding. And then this is also not true because it cannot be higher than that of alcohol. So the only thing that makes sense is 75 degrees Celsius. So 3.4.2, we have 75 degrees Celsius. So X makes sense to be 75 degrees Celsius. Well, 3.4.2 says explain, and we've explained that. Now let's take a look at 3.5. 3.5 is quite an interesting one. I had to take some time and think about that. The atmospheric pressure is now changed to 83 kilopascals. Well, under normal circumstances, we have 101 kilopixels. I think 101.3, something like that. But I know for sure it is around 101. And now it has changed to 83 kilopixels. Now it is changed to 83 kilopixels. Let's hear the stories. How will the boiling points of these organic compounds be affected? Choose from increase, decrease, or remain the same. So do the boiling points increase, decrease, or remain the same if we lower the vapor pressure? Well, let's stick to the definition. What is boiling point? Boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. So you are essentially increasing the vapor pressure so that it reaches the atmospheric pressure, and we say that we have reached the boiling point. Essentially, if you are lowering the atmospheric pressure, you will reach a boiling point way sooner than you would under normal circumstances. Right, maybe for water, the boiling point is 100 degrees Celsius. So if you lower the atmospheric pressure, you would reach the boiling point, let's say at 80 degrees Celsius, way before what it usually is at 101 kilopixels. So this would actually make the boiling point to decrease. Right, this is the first time I'm actually coming across a question like this, but I'm quite convinced that decrease is our answer in 3.5. If you have any other ideas, just let me know in the comments and let's talk about it. Apart from that, which video do you want me to do next? Pressure exerted by a vapor at equilibrium with its liquid in a closed system. That is vapor pressure. 3.2. Which one of the compounds A or B has the higher vapor pressure? So what do we know? We know that the higher the boiling point, the higher the melting point, the higher the viscosity, but the lower the vapor pressure. So which one of the compounds A or B has the higher vapor pressure? Well, the compound with the lowest boiling point will have the highest vapor pressure. So between A and B, which one has the lowest boiling point? It is compound A with minus 42 degrees Celsius. Compound B has a boiling point of 36 degrees Celsius. So the answer here is A. A has the lowest boiling point, so it should have the highest vapor pressure. Right, 3.3.1. Let's consider compound C, 2-methylbutane. Is compound C a saturated or unsaturated hydrocarbon? Well, it is easy to see that it is saturated. Why are we saying that it is saturated? A compound is saturated if it only consists of single bonds between the carbon atoms, no multiple bonds whatsoever. That is a saturated compound. Just like our compound C, it is a simple alkene, saturated compound. Alkene and alkynes are unsaturated because we have double and triple bonds. Here we only have single bonds. 3.3 because we've just answered 3.3.2 there. Which type of intermolecular forces are mainly present between these compounds? Well, the compounds on our table, we have propane, pentane, 2-methylbutane, and then we have an outlier, pentane 1-ol. As you can see, one intermolecular force that is present from compound A to compound D is London forces. It is present even in compound D, pentan 1-ol. So that is the type of intermolecular force which is mainly present between these molecules. There is London forces in pentan 1-ol. It is just that the strongest intermolecular forces in pentan 1-ol will be hydrogen bonding, but London forces is present. 3.3.3. Let's go ahead and look at 3.4.1 and 3.4.2. Define the term structural isomer. Organic compounds with the same molecular formula but different structural formula. Same molecular formula but different structural formula. Just like compound B and C, we have C5H12, 3.4.2 refer to the structure intermolecular forces and energy in your explanation to explain why compound B has a higher boiling point than compound. Let's go ahead and have a sketch of compound B. 5 carbons in a straight line. So 1, 2, 3, 4, 5. While compound C on the other hand, we have 1, 2, 3, 4, and a branch on the second carbon. How does compound B differ from compound C? The only difference between these two compounds is the degree of branching. Compound B is less branched compared to compound C. Less branched means more surface area. So we have more surface area in compound B. From there on, our song starts. More surface area, stronger intermolecular forces. If the intermolecular forces are stronger, more energy will be required to overcome the intermolecular forces, and consequently a higher boiling point, just like we can see. Right, so B is less branched compared to compound C, as we can clearly see. This is straight, and here we have a branched. Less branched will mean more surface area. More surface area, stronger intermolecular forces, more energy is required to overcome those intermolecular forces. I hope that is clear. The last question, 3.5, explain the difference in the boiling points of B and D. Refer to the intermolecular forces and energy in your explanation. Let's go ahead and look at B and D. B is pentane and D is pentane 1-ol. Look at the difference in the boiling point, even though they have the same number of carbons, 36 degrees Celsius and 137 degrees Celsius. So why does compound D has a higher boiling point compared to compound B? Well, compound B consists of London forces, while compound D consists of hydrogen bonding. We know fully well that hydrogen bonding is a stronger intermolecular force compared to London forces. So compound D will have stronger intermolecular forces. More energy will be required to overcome the intermolecular forces in compound D, and as a consequence, it has a higher boiling point.
If a reaction starts with an alkene, then it is an addition reaction. And then if it ends with an alkene, it is an elimination reaction. And if the first condition or the second conditions are not met, then it is a substitution reaction. So this is how you can easily identify the type of a reaction by just looking at the compound it starts with or the product that you have. If it starts with an alkene, it is an addition reaction. If it ends with an alkene, it is an elimination reaction. And if either of those are not true, it is a substitution reaction. So let's see how we can use this to answer this question. So 4.1.1, identify the type of reaction represented by B. So take a look at reaction B. Does it start with an alkene? No, it does not. It starts with an alcohol. So it cannot be an addition reaction. Does it end with an alkene? Yes, it does. As soon as we see that, we know that it is an elimination reaction because it ends with an alkene. Right, those are the only two things we need to look at. If it didn't end with an alkene, then it would be a substitution reaction. That is 4.1.1. Let's take a look at 4.1.2. Identify the type of reaction represented by D. So again, does it start with an alkene? No, it does not. Bromoethane is not an alkene. And does it end with an alkene? It is not. It ends with an alcohol. So because the first condition is not met and the second condition is also not met, then we are saying that it will be a substitution reaction. Those are the only two things that we need to look at. Does it start with an alkene? Does it end with an alkene? If that's not the case, then it is a substitution reaction. So there we go. That is 4.1. Let's take a look at 4.2. 4.2, we're supposed to write down two reaction conditions for reaction B. So reaction B it's easy to see that we have a elimination reaction. So heat is a reaction condition for all elimination reactions. Heat is a reaction condition for all elimination reactions. Right, so heat is our first answer, right? As soon as we see a reaction condition and it is elimination, heat, we're going to think after that. So now let's find another reaction condition. So what is happening here? We have dehydration, right? We have an alcohol turning to an alkene. So we need a dehydrating agent, of which we can use a catalyst such as H2SO4. So we also need a catalyst as a reaction condition for this elimination reaction that we have. 4.2, let's take a look at 4.3 and 4.3.1. For reaction A, write down the name of the inorganic reactant. So reaction A, we are turning an alkene into an alcohol. Obviously, we need H2O to turn an alkene into an alcohol. And by our definition, H2O is inorganic because it does not contain carbon. So name of the inorganic reactant, it is water, right? Not H2O. The question is very specific. We are looking for the name of the inorganic reactant. And then 4.3.2, chemical formula of the catalyst used. Chemical formula, not the name, right? So don't confuse the two. Well, you know what they mean. Just be careful and not write a formula when they want a name, or write a name when they're looking for a formula. So here the chemical formula of a catalyst needed. We need H2SO4, right? H2SO4 is not always the answer to a question with regards to catalyst, right? It just happens that we have used it twice in this equation. Okay, 4.4.1. Let's take a look. For reaction C, okay, so reaction C, we are turning an alkene to a haloalkane, right? And then 4.4.1, use structural formula and write down a balanced equation. Okay, we're supposed to use structural formula. So this is our alkene with 2 carbons. How many bonds do we have? 1, 2, 3. So we need another hydrogen. And we can see that our product is bromoethane. So what are we adding here? We're adding HBr. And this should give us bromoethane. So the double bond gets broken, and it's just a matter of filling out the hydrogen and the bromo in one of those bonds. So there we go. I don't think there's any wrongdoing that we do in there. I think all is well, right? Quite an easy reaction. We have our alkene, we add a hydrogen and a halogen, so it is a hydrohalogenation addition reaction, and then this is our product. Okay, there we go. 4.4.1. Let's take a look at 4.4.2. So 4.4.2, explain why no water should be present during this reaction. Explain why no water should be present during this reaction. We are avoiding the formation of OH instead, right? If you have water, it's very possible that instead of having Br there, you might have OH. So that is what we are running from. Yes, we are trying to avoid the formation of the hydroxyl group, right? That is 4.4.2. 4.5, let's go ahead and take a look. So we are now concentrating on reaction E. Okay, let's see what the first question says. Type of reaction. Okay, so reaction E represents the conversion of the alcohol into organic compound X. So reaction E. Okay, so we start with an alcohol, as we can clearly see, and then we add what looks like an acid to get compound X. So something should come to mind when we talk about alcohol plus acid. This is clearly a esterification. So the answer to 4.5.1 is esterification. An alcohol plus an acid in the presence of a suitable catalyst will give you esterification, right? It will give you an ester. So type of reaction, esterification, right? So esterification. There we go. That is 4.5.1. Let's take a look at 4.5.2. Chemical formula of the catalyst used. We know what suitable catalyst we need in esterification. We need concentrated H2SO4. That's what we use in our esterification reactions. And then 4.5.3, structural formula of compound X. Compound X, I would assume, is the product formed. Let's go ahead and take a look. Okay, there we go. So our alcohol has 2 carbons. 1, 2. Okay, that's easy to see. And then our acid, let's go ahead and find out. We have 1, 2, 5, right? That's C multiplied by 3 there. So we have 1, 2 from the alcohol, and then we still have our oxygen from the alcohol. And then as long as it comes, and the carboxylic acid, we still have our double bond oxygen. And then 1, 2, 3, 4. So in total, 1, 2, 3, 4, 5. We have our 5 carbons from the carboxylic acid. So now, what we just need to do is to fill out the hydrogens everywhere else. I hope we're looking for the structure of the product and not the entire reaction, right? So there we go. Yes, maybe we should just do the reaction, the entire reaction, so that you can see where it is coming from, right? Maybe we should do the entire thing so that you can see where it is coming from. But this is the answer. This is our product. This is compound X, right? Let me show you where it is coming from. Either way, let me show you where it is coming from. So we're saying that our alcohol has 2 carbons. Yes, so it means that we have 1, 2, OH, hydrogen, hydrogen everywhere else. Okay, this is what we have, plus the carboxylic acid. Our carboxylic acid has 5 carbons, so it is 1, 2, 3, 4, 5. Well, let me put these a little bit to the right so that it will be easy to see when we remove our H2O, so that it can be easy to see when we remove our H2O. So hydrogen everywhere else. Hydrogen everywhere else. Okay. There we go. So what happens is that the alcohol loses the hydrogen and the acid loses the OH. Okay. And then that is why a byproduct or an inorganic product of esterification is H2O. Right. So we essentially losing this. We'll lose this part because water is removed from, well, we get water when we add the two compounds. So that is why our product ends up looking like this. This is why our product ends up looking like that. Okay, so there we go. I hope you can see where it is coming from. Right, the alcohol loses a hydrogen and the carboxylic acid loses an OH. But anyway, stories. Let's take a look at the question that follows. Is it 4.5.4? I think so. We're looking for the IUPAC name of the compound. So how do we name an ester? Right, well, we started with the alcohol and then we finished off with the acid. So the alcohol here is ethanol, as it has 2 carbons. So we're going to have ethyl, and then the carboxylic acid is pentanoic acid, as we have 5 carbons. So we're going to have pentanoid. So the name of this ester is ethyl pentanoid. Right. If the alcohol had 3 carbons, it would be propyl pentanoid. If the carboxylic acid had 4 carbons, for instance, it would be ethyl butanoate. That is how it works. First part of the name comes from the alcohol, how many carbons we have, and the second part of the name comes from the acid, how many carbons we have. That is 4.5, 4.6. Let's go ahead and take a look. So 4.6, reaction F takes place in the presence of warm concentrated sodium hydroxide. Use condensed structural formula and write down a balance equation for this reaction. Let's go ahead and take a look at reaction F. So reaction F, bromoethane to give us an alkene. Okay, so let's take a look there. In the presence of concentrated NaOH. So in the presence of concentrated NaOH, that's where elimination is going to take place. If it was in the presence of dilute NaOH, then substitution would take place. So let's go ahead and take a look at that. We start off with our bromoethane. Okay, so Br, hydrogens everywhere else. Okay, this is what we're starting with. And then plus NaOH. Okay, so what happens here is that, well, we are supposed to use condensed structural formula, not the way I'm doing it here. But let me just carry on with this for the sake of clarity. After doing this, then we're going to write it in the correct form. We're going to use condensed structural formula. Okay, so let's just carry on with this for the time being. So what happens here is that Na will bond with Br, and then OH will bond with the hydrogen removed, right? And then it means that our product, well, our byproducts, we're going to have NaBr plus H2O. Okay, that's how it goes. So let me show you. It means here that the products, we're going to have one double bond because now it is an alkene, hydrogens elsewhere, plus NaBr plus H2O. This is how the reaction takes place in terms of the structural formula. But our equation, we're supposed to use condensed structural formula. So let's go ahead and do that. This is just for the sake of clarity. So condensed structural formula, CH3, CH2Br. Okay, plus NaOH. And what does this give us? This gives us CH2, CH2. As you can clearly see, CH2, CH2. And then plus NaBr plus not NaOH, but H2O. Right, we have H2O there. So there we go. That is the condensed structural formula for reaction F. Okay, so 4.7, cracking. Let's take a look. We know fully well that this is still part of our syllabus, but it's one of those questions that they're not usually there in the exam. But let's go ahead and take a look at it. A large straight chained alkenes can be catalytically cracked to produce shorter chained alkenes and branched alkanes, which are more suitable for use in petrol. The reaction below indicates the catalytic cracking of octane. Okay, so octane, obviously we are expecting 8 carbons, and then here on the alkene we have 2 carbons. It means that on compound Y, which should be an alkene, we should have 6 carbons. So C6H14. That's what we expect compound Y to be. Right. So what does the question say? Write down the IUPAC name of compound Y. So 6,6, that is hex. So this is hexane. 4.7.1 is hexane. So there we go, hexane. And then 4.7.2, briefly explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkanes. So what do you think it is the answer to this question? Explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkanes. Right, maybe just to give you a hint, think about intermolecular forces, energy required, so on and so on. Let me know in the comments what your answer to this question is.
The name or formula of the catalyst used. So let's go ahead and take a look and see what is happening. In an experiment, a test tube containing methanol, propanolic acid, and a catalyst is heated in a warm bath. Well, we have the setup in front of us. The warm bath. Under the warm bath, we have some heat, methanol, propanolic acid, and a catalyst. Already, you should be able to tell that we have esterification taking place. Okay, so which catalyst is required when we are trying to have esterification? The catalyst is H2SO4. That is the catalyst. The question says name or formula. So if you say sulfuric acid, that would also be fine. But in some instances, the question would say the name, and then if you write H2SO4, it would be wrong, or it says the formula, of which if you write the name, it will be wrong. Right, so there we go. That is 4.1.1. What about 4.1.2? The type of reaction taking place. Even in, say, after doing all the questions, what does this comment say? Do you mind doing multiple choice for paper 2? We'll see about that, but I doubt I will. Multiple choice takes too much time and it doesn't get as much views, so it doesn't make sense for me to do it. The type of reaction taking place is esterification. So esterification, there we go. That is 4.1.2. And then 4.1.3, 2 reasons why the use of a water bath is preferred in this experiment over direct heat. One of the reasons is because alcohol is extremely flammable, right? So there we go. That is one reason. Alcohol is flammable. So if you put it on heat, if you put it directly on heat, then it's gonna burn, and that's not what we want. So that is one reason why we use a water bath over putting the reactions on heat themselves. So what is the other reason? I would like you guys to tell me. So please leave a comment and tell me which other reason you can think of. Well, in class, during the course of the year, at the beginning of the year, we actually performed this experiment, and we lost patience at some point of time because it was taking too long, and we put the test tube directly on heat, on the fire that was burning. Yeah, because we're using a sort of a Bunsen burner. I forgot the technical name of the apparatus we were using, and then we experienced some issues. Well, almost all the contents evaporated from the test tube, so we were not actually able to smell the contents, or because after an esterification you take a smell and then there's some things that you write, so on and so on. So we're not able to do that because we lost patience and put the test tube over the fire. But let me know, which other reason can you think of? That is 4.1.3. Let's do 4.1.4. The balance equation for this reaction using structural formula. So we have methanol plus propanolic acid. So let's go ahead and take a look. Methanol, so alcohol with 1 carbon. Okay, that is methanol. Plus propanolic acid, acid with 3 carbons. So we're gonna have, let's take a look. Carbon, well, we're supposed to have OH here, and let's see. Oh, we need more space. Let me start with the H instead. H, O, carbon double bond oxygen, right? And then let's 3 carbons and not 2 because it's prop. So hydrogen, and we need another hydrogen here. 1, 2, 3, 4. Okay, so this hydrogen, that carbon is fine, and then this will give us an ester. So what's gonna happen? The alcohol loses the hydrogen and the acid loses the OH. As a result, we're gonna have carbon, oxygen, and then now carbon. Okay, and then 1, 2, 3. Okay, there we go. And then now we just need to fill out the hydrogens, right? So let's do that. So there we go. We're supposed to have something like this, and then obviously here we can write H2SO4 as our catalyst. But what happened to the H2O that we removed is that it doesn't disappear. So we're gonna have plus oxygen HH, not plus H2O, because H2O is not a structural formula, right? You're supposed to write it in this manner. If you write it as H2O, that is technically wrong because H2O is not a structural formula. So this is what we have. Let me just check and see if I'm not making any mistake. Okay, let me take a look. I'm supposed to have an oxygen here and not hydrogen. 1, 2, 3, 4, 5. Okay, another mistake. Hydrogen. I've removed that hydrogen. It's all going well now. I think I have everything covered now. So that is 4.1.4. I hope you didn't make those mistakes that I was making there. The IUPAC name of the organic product for this reaction. The organic product is the ester and not the H2O. So what is the name of this ester? We're going to have methyl propanoate. Right. This part of the name comes from the alcohol, and this part of the name comes from the acid. Methyl propanoate. Right, I think we have that covered. Let's take a look at 4.2. Compound A is a 6-carbon branch alkane, and it is used in a 2-step reaction to prepare compound C. Okay, so compound A, and then we go to B, and lastly we go to C. Reaction 2 is an addition reaction. If reaction 2 is an addition reaction, then here we have an alkene, because you can only add it to an alkene. Okay, we know that for sure. And then 4.2.1, the name or formula of the inorganic reactant needed in reaction 2. So we have an alkene and our product is an alkane. So we have an alkene and our product is an alkane. So I think, it is quite easy to deduce here that we have a hydrogenation. We have a hydrogenation. So what is the inorganic reaction needed for hydrogenation? Platinum, palladium, nickel. I wonder what else, but those are the ones that I can recall from my head on the spot. Okay, 4.2.2, the IUPAC name of compound B. So compound B is an alkene. Let's try sketching the alkene. We can try sketching the alkene using compound C. We're sort of removing 2 hydrogens there. So the question says the IUPAC name, but it's better to sketch before we actually name the compound, right? It becomes easier. So let's see. 1, okay, and then carbon, and then carbon, and then here we're gonna have carbon and then another carbon, but we are removing 2 hydrogens in reaction 1, right? Not 2 hydrogens, but let's say, yeah, we are removing the compound that is here and another compound, not compound but element, another element that is there, right? So we have a double bond here as a consequence. In compound B we have a double bond, because how are we adding these 2 hydrogens in reaction 2 if compound B doesn't have a double bond? It will not make sense. So we have a double bond there. So now we can name compound B using that knowledge. So if we're to name compound B, obviously we would have butane 1 in, okay? And then so this is 1, 2, 3, 4. So on the 3rd carbon we have 2 not 2, because like I said on the 3rd. So why do I say on the 3rd and say 2? Right, let me just, I'm trying to drag this to the right. So I'm gonna have 2.2 dash dimethyl butane 1 in. So let me hide the structure and try drawing it and see if I'm going to end up with the same thing. So butane, so 1, 2, 3, 4. 1 in, double bond. 2.2 dimethyl. So 2 is here. So carbon, carbon. Is that what we have? Is that what we're dealing with? That is not quite what we are dealing with. Because if I reveal that structure, let me do that. I have, okay, the carbons are on the third. So this is 3.3 and not 2.2. Right. If I didn't do that, if I didn't try to verify, I was actually going to get it wrong. So yeah, I'm glad I did try to verify because I had made a mistake. But anyway, stories. That's what we have. That is 4.2.2. And then what about 4.2.3? The type of reaction represented by reaction 1. In reaction 1, we have a haloalkane. Oh, well, in compound A, in reaction 1, we start with a haloalkane and we end up with an alkene. Clearly, it is an elimination reaction. Yeah, because we start with a saturated compound and we end up with an unsaturated compound. So that is 4.2.3. Using structural formulas, write down a balanced equation for reaction 1. Let's go ahead and take a look at reaction 1. We are starting with but1 in. We are adding a hydrogen and a halogen to get some product X. Well, in our previous videos, I've made it very clear. If a reaction starts with an alkene, it is an addition reaction. Without looking at any other thing, if it starts with an alkene, it is an addition reaction. No questions asked. What are we adding in this reaction? We're adding a hydrogen and a halogen. Well, let's start and see what we're going to have. We are starting with but1 in. So that is 1, 2, 3, 4. And on the first carbon, we have a double bond. So now it's just a matter of filling out the hydrogens. Let's go ahead and do that and see where we end up. Right, there we go. We have but1 in. Let's make sure that we have the correct number of hydrogens. On this carbon, we have 1, 2, 3, 4 bonds. So that is okay. On the second carbon, we have 1, 2, 3, 4. So it seems like everything checks out. So what are we adding? We add in a hydrogen and a halogen. The name of this addition reaction would be hydrohalogenation. The name of an addition reaction comes from what you are adding. Well, let's go ahead and have our products. It is easy to see that this double bond is going to break to accommodate the hydrogen and the halogen. But where is the hydrogen going to go? Where is the halogen going to go? The hydrogen is going to go to the carbon with the most number of hydrogens already. If you look at our situation, this first carbon here has 2 hydrogens and the second one has 1 hydrogen. So the hydrogen is going to go to the carbon with the most number of hydrogens. That is Markovnikov's law. So let's go ahead and have our product now. We're saying that our hydrogen is going to go to the first carbon as it has the highest number of carbons compared to the other carbon that it can possibly occupy. Yeah, so from this reaction, this is our major product. Our minor product is when the halogen is on the first carbon. That is 4.1 formats. Let's go ahead and do 4.2. Write down the name of the type of reaction that occurs when but1 in is converted to compound X. We already know that if a reaction starts with an alkene, we have an addition reaction. Quite an easy question to answer. 4.3. Write the structural formula and IUPAC name of the secondary alcohol Y that forms. So we've but1 in, and through some reaction 3, our product is a secondary alcohol. Well, it is starting with an alkene, so we know that it is an addition reaction. Which addition reaction leads to an alcohol hydration, right? Also given that it is a secondary alcohol, but we would also be able to get to a conclusion that the alcohol that is formed is secondary. But anyway, let's go ahead and have our alcohol. 1, 2, 3, 4. On the second carbon, we have OH. Yeah, that is wrong. It's not supposed to be like that. We're supposed to have a dash here to show that OH is not one thing. It is an oxygen bonded to a hydrogen. If you are writing the structural formula, you need to put that bond there. Well, everywhere else we have hydrogens. So we can just go ahead and put that there. Again, our product is a secondary alcohol because of the Markovnikov's law. Let's go ahead and name this alcohol. How many carbons? 1, 2, 3, 4. Which side are we numbering from? From the right, because our OH is going to be on the second carbon. But if we start numbering from the left, it is going to be on the third carbon. Well, it means that our IUPAC name will be butane-2-ol, right? The functional group is on the second carbon. That is 4.3. Let's do 4.4. Name the type of substitution reaction that occurs when compound X is converted to the secondary alcohol Y. So there is only one substitution reaction that can give you an alcohol. It is hydrolysis. There is no other substitution reaction that leads to the formation of an alcohol. So without thinking very hard, we know that the answer is hydrolysis there. If your alcohol is formed through a substitution reaction, it is hydrolysis. If it is formed through an addition reaction, it is hydration. Yes, 4.5, 4.5.1. Butane can be converted directly to the secondary alcohol without the formation of the intermediate product X with the help of a catalyst. 4.5.1. Except butane, write the name of the reactant needed for this reaction. Well, a reaction that takes us from butane to the secondary alcohol, it is an addition reaction. But they don't want to say now in 4.5.1 because it is equation in 4.2. So if they tell you what it is, then you can actually say, oh, okay, it means that the answer to 4.2 is addition. What do you need to add to butane in order to have an alcohol as your product? You need to add H2O, but they say the name. So if you write H2O, it is wrong because H2O is not the name. The name is water, right? That is another trick to the question, because if you write H2O, I'm telling you, your answer is wrong. You need to write water. And 4.52, write down 4.5.2, write down the formula of the catalyst that can be used. If you write sulfuric acid, your answer is wrong. The question says formula. So you're supposed to write H2SO4 and 4.5.3. Name the type of reaction that will occur during this direct conversion. It's 2 marks for one question because the same question is getting asked in 4.2. The type of reaction that will occur is addition.
Which letter represents an alkene, right? So what we want to do here is to have a functional group of an alkene, right? So we know that in an alkene, we have a double bond, right? And then the name ends as E-N-E. So when we go to our table here, whatever that has a double bond or the name ends with E-N-E, we know fully well that that's an alkene, right? Clearly on A here, we have a double bond. So as soon as we see that there's a double bond, we know that it's an alkene, right? So right now we can just write A. And then B, we don't have any double bond between carbon atoms. And then on C, we have a double bond here. So C is part of our solution. So for 2.1.1, we have A and C. And then for D, there's no double bond, and then it doesn't end with E and E. And then for E, no double bond, and then for F, there's a triple bond, right? And that's not what we're looking for. So the answer for 2.1.1, we just have A and C. Now let's go to 2.1.2, which letter represents a ketone. Again, we're going to look at the functional group of a ketone. For a ketone, we need something like this, right? We need a carbon that is bonded to an oxygen and then bonded to two other carbons, right? So if we see something like that, or a name that ends with O-N-E, then we know that we have a ketone, right? So for A, we already know that A is an alkene, so there's no way it can be part of our solution. But then if you look at B, we have a carbon here bonded to an oxygen and two other carbons. So clearly B is our ketone, right? So for 2.1.2, we have B. C is also an alkene, so it cannot be part of our solution. D doesn't have what we're requiring. E and F also doesn't have what we're requiring. So now we can go to 2.1.3. 2.1.3 says, let's look for a compound with a general formula CnH2n minus 2. Right? If you're not already familiar with this, this is an alkyne, right? The name ends with Y-N-E. Another way of identifying it, we have triple bonds, right? So a carbon is bonded to another carbon, and there's triple bonds in between the two. So again, we go to our table and we look for that. A cannot be part of our solution. B cannot be a part of the solution. C also cannot be part of our solution, right? And then D, we don't have a triple bond or Y-N-E, right? So that cannot be part of our solution. For E, no triple bond. And then F, that's where we have our triple bond, right? You can see it here. So for 2.1.3, we can put F as our answer. Right? The way of approaching this problem, you have to know exactly what you're looking for, right? It becomes extremely easy when you do that. And then 2.1.4 says, let's look for a structural isomer of octanoic acid, right? Octanoic acid. So for an acid, if we're looking for a structural isomer, we're looking for another acid or we're looking for an ester, right? Because acids and esters are functional isomers. So if the structural isomer is an acid, then we should find something of this manner, right? Or something that ends with the name acid, right? And then if it's an ester, then we're looking for something like this, right? Or a name that ends with ATE, right? A cannot be part of our solution, B cannot be part of our solution, C cannot be part of our solution. But obviously, if you look at D, this name here ends with ATE, right? And then not only does it end with ATE, it also has 8 carbons, right? Like the octanoic acid, which is of our interest, right? So the answer of 2.1.4, we are going with D. And then now we can do 2.2. 2.2 starts by saying that let's write down the UPEC name of compound A. So what you want to do first, step number 1, is that to identify the longest carbon chain, right? So we have 1, 2, 3, 4, 5, 6. Even if you take any other way, you'll end up with 6, right? So now we know that as part of our name, we should have hex. Now we are going to look for the side which leads us to the functional group first. Obviously, if we start counting from this side, if we say 1 here, 2 here, and then we have our functional group, right? So it will say hex 2 in, right? But then if you start on the other side, you'll say 1, 2, 3, 4, and then it will be on carbon number 4, right? So we prioritize the side that leads us to the functional group first. So we have hex 2 in, right? Now we can look for the branches. So let's name our carbons first. So that is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, right? On carbon number 4, we have a branch. We have one carbon, right? And then on carbon number 5, we also have a branch. So now we can say 4,5 dash. We don't say methyl, right? Because we have 2. Instead of saying methyl, we say dimethyl. 4,5 dash methyl, right? And between words, there's no need to put a dash. Now we can go and do 2.2. We need the UPEC name of compound E. So let's go look at compound E. Let's look for the longest carbon chain. So if we say this is 1, 2, 3, 4, 5, 6, 7, and then if we take this way and we keep going forward, we get 6, right? So we can conclude that the longest carbon chain has 7 carbons. So what is 7? We know fully well that 7 is hept, right? So we have hept. And then let's look for the functional group. It's an alkane, right? Every carbon is essentially the functional group. So we don't put anything there for an alkane. We can just say heptane. You only put something when you have an alkene or you have an alkyne. And then all the other complicated organic compounds with other functional groups. Now you will realize that we have an ambiguity here. We have a halogen on the second carbon, right? When you start counting from the left, and then we have a branch on the third carbon when you start counting from the right, right? So which one do we prioritize between the carbon and the halogen? Between the carbon and the halogen, we prioritize neither. So whatever that counts first, it's what we take, right? If a certain path gives us methyl first, then we're going to take methyl. But then if we start counting from the left, then we get to bromo first. So we're going to take bromo, right? But then you can get a situation where on the left path, you get bromo, and then on the right path, you get methyl. What do you do when you have a situation like that? Then you have to check the alphabet, right? You have bromo and methyl. So you would take bromo because alphabetically wise, bromo comes first. But then now because bromo is on the second carbon from the left, and then the methyl is on the third carbon from the right, you just take bromo automatically. And then if the methyl was on the second carbon and the bromo was on the third carbon, then you would take the path that leads to the methyl first. So we have carbon 1, 2, 3. So on carbon 2 and 3, we have 2 halogens, right? So we're going to have 2,3 dash dibromo, right? Because we have 2. And then we can then look for the branch, right? Carbon number 4, carbon number 5, and then on carbon number 5, we have methyl, right? So we're going to have dash 5 dash methyl. And then there goes our UPEC name. And then last but not least, we have 2.23, which says let's write the UPEC name of compound F. In compound F, we have an alkyne, right? Because we have an alkyne, we have a functional group. So naming will be much easier because we always prioritize the functional group. So we're going to start naming from this carbon here. So we're going to have 1, 2, right? And then 3, 4, 5. Even if you go up, you still have 5 carbons, right? So now it's easy to see that we'll have pent, right? And then now let's look for the position of the functional group on the second carbon. So we're going to have pent 2YNE. Now we can look at the branches and so on. We have a branch on the fourth carbon. So we're going to have 4-methyl. Now let's do 2.3. So 2.3 says that compound D is prepared by reacting 2 organic compounds in the presence of an acid as a catalyst. And then 2.3.1, let's write down the structural formula of compound D. So let's go and look at compound D. So compound D is pentyl propanoate, right? We know that if it ends with propanoate, It's an ester, right? One thing about an ester, the first part of the name is the alcohol, and the last part of the name is the acid. So let's write the structural formula. We know fully well that pent is 5, right? So we're gonna have 1, 2, 3, 4, 5. We're saying that the first part is the alcohol, right? So here we were supposed to have OH, but then when it forms an ester, it loses this hydrogen here, and everywhere else where I'm putting a dash, you fill that with hydrogens, right? And then the last part, propanoid, that is the acid. So propanoic acid was supposed to look like this, right? But what happens is that when it forms an ester, it loses this OH here, right? The alcohol loses an H, and then the acid loses an OH, and then the byproduct is then H2O, right? So let's put it in our structural formula. So here we're gonna have dash a carbon, an oxygen, carbon, and then there we go. So like I said, everywhere when there's a dash, we just put hydrogens, right? For the sake of time. Now let's do 2.3.2. 2.3.2 says the UPAC name of the organic acid used to prepare compound A. Yeah, we went through it, right? I say that the last part comes from the acid and the first part comes from the alcohol. It is saying prop, so we know that the acid that was used there should be propanoic acid, right? So 2.3.2, the answer is propanoic acid. And then if the question was saying let's name the alcohol, then it was going to be pentanol. 2.3.3 says let's name or give the formula of the catalyst that is used, right? In esterification, we always use H2SO4 or sulfuric acid. Question 2, organic chemistry. We have a table there. We have 6 organic compounds. And then 2.1.1 it says write down the letters that represents the following. 2.1.1 says a ketone. So A is an acid, B is an aldehyde, C is an alkane, D it's a haloalkane, and then E is an alcohol, and then F is the ketone. Why am I saying F is the ketone? I'm saying that because of the functional group. Let me do something real quick so that I can show you what I'm talking about. So here's the functional group here. This is the functional group for ketone. So as soon as I see that, I know that I have a ketone. So that is F. We have 2.1.2. 2.1.2 says 2 compounds that are functional isomers. Functional isomer. A ketone is a functional isomer of an aldehyde, and then a ester is a functional isomer of carboxylic acid, right? These are the only 2 functional isomers we have. So the only ketone we have is F. It has 1, 2, 3, 4, 5. It has 5. It has 5 carbons. Let's look and see if we have an aldehyde that has 5 carbons. E is not an aldehyde. D is not an aldehyde. C is not an aldehyde. B is an aldehyde, and it says pentanol. You know that it says meth, eth, prop, bute, pent, right? So it has 5 carbons. So the functional 2 compounds that are functional isomers is B and F. It's aldehyde and ketone. Let's move ahead. 2.1.3. 2.1.3 says write down the letter that represent a hydrocarbon. That's a alkane, an alkene, or an alkyne. For this question, the only hydrocarbon we have is number C, which is which has 10 carbons and 22 hydrogens. Let's move ahead. 2.2 says for compound D. Let's look at compound D. There it is there. I just put some brackets over it to highlight it. It says write down the homologous series to which it belongs. We know that it's a haloalkane, like we've already said. So we're just gonna go ahead and write that down. Why are we saying it's a haloalkene? It's a hydrocarbon that has a halogen, or in this case it has halogens because it has two bromine. There we go. That was 2.2.1. Let's move ahead to 2.2.2. 2.2.2 says write down the UPEG name of compound D. So we're going to calculate the carbons. So we have 1, 2, 3, 4, 5, 6, 7. We have these 2 here on the outside, and then 8, right? So as soon as we get 8, we know that that is going to be oct. So we have oct, and then it's a haloalkane, so it's just going to be octane. And then now we look for where the halogens are positioned. If we count from the right hand side, it's 1, 2, 3, and then if we count from the left hand side, is 1, 2, 3, 4. So the closest path to a halogen is from the right hand side. So we're going to have 3 comma, and then the other position for the other halogen. So that's 1, 2, 3, 4, 5. So it's 3 comma 5 dash dibromo octane, 3.5 dibromo octane. There we have it. Let's move ahead. 2.3. 2.3.1. 2.3.1 says consider compound F. Compound F is a ketone. It's a ketone. Then 2.3.1 says write down the UPEG name of its positional isomer. Okay, so positional isomer, same molecular formula, but different position of the functional group. So we have 1, 2, 3, 4, 5 carbons, and then the functional group is on this second carbon from the right. If we for an element to be a ketone, the oxygen double bond should be sandwiched by carbons, right? So we cannot put an oxygen here. It becomes an aldehyde. It's no longer a ketone. But then if we come and we put it on this carbon here, then it's going to be the same name, because we'll start naming from this side. So it will still remain what it is. So we are supposed to put it in the carbon in the middle. It will have a different position of the isomer. That's different UPEG name, but it's still a ketone that has the same molecular formula. So that's how we draw it. So we no longer have these. The oxygen double bond is there, and then you can fill out the rest of the carbons. So now the name becomes 1, 2, 3, 4, 5. That is pent, right? Pentan, and then 1, 2, 3. 1, 2, 3. If you count from any way, from the left or from the right, you get to the oxygen double bond after you've moved past 2 carbon. So that is pentan 3 on. And then that's it. That's how you name the positional isomer of compound F. 2.3.2 says a chain isomer of compound M, compound F. So still same molecular formula, but different structural formula. So again, let's go back to the basics. We have 1, 2, 3, 4, 5. And then we know that the oxygen double bond should be sandwiched between 2 carbons. So let's say it's still here. If you take this carbon here and then you put it here, that's virtually impossible because the carbon can only support 4 bonds. If you put it here, then you're gonna count from you're gonna start counting from this one because it's not, there won't be anything else here, so you'll start counting from 1, 2, 3, so it will remain the same ketone. But then if you don't do that and you take this carbon here and then you put it here, you're thus going to get a different chain, a different name, but still the same molecular formula. Yeah, maybe there's another way that I'm not seeing that you can use, but as long as you play around with it, it has a different name, it still has the same molecular formula, then you're good to go. So in this instance, if this is what we are going to have, it's going to be, let me see, it's going to be butane 2-one, right? So if this is 1 and we're saying this is 2, then this is 3. So we're gonna have 3-methyl butane 2-one, and then that's a chain isomer for compound F. 2.4 2.4.1 says during the reaction of compound A with compound E. Compound A is an acid, right? And then compound E is alcohol. There we go. And then you know that when you mix an acid and an alcohol in the presence of an acid catalyst, you're going to get esterification. So let's see. 2.4.1 says okay, they have reacted. It says write the UPEG name of the organic compound formed. So you know that if you have an alcohol and then acid, you add the acid and then you get the ester. At the naming, you start by the alcohol, right? The alcohol is in this instance 1, 2, 3, 4, 5, 6 is hexanol, right? So we have hexanol for the alcohol, and then for the acid we have methanoic acid. If you mix these two and you form an ester, this is how you write the name. You take the alcohol is hexanol, it will become hexyl when you start writing the name of the ester. And then this one says methanoic acid, it will become methanoid. The spelling is just confusing me there for a second. But then, okay, it's not really visible. Methanoid. Yeah, so that's it. That's the name of the ester. So if you add butanol, you're going to have butyl methanoid, and then for a different acid, you know what to do. So we done with 2.4.1. Okay, 2.4.2 says the structural formula of its functional group. That's the functional group of ester. So you have a double bond, and then you have an oxygen here, you have a carbon, and then it can be bonded to something there. This is the functional group. There's really no trick. There's no formula. It's just the functional group of an ester. Yeah. But if you pay attention to detail, you can see that this part will come from the alcohol, and then this part will come from the acid. But other than that, just straightforward. 2.5.1 compound C, 10 carbons, 12 hydrogens, reacts at high temperatures and pressure to form a 3-carbon alkene. 3-carbon alkene, so that's propyl. It has formed propyl, and then some alkene Q. And then the first question is write down the type of reaction that takes place. this is cracking. You can see that is this big compound, and then now it has cracked to P and Q. It's cracking, or you can even write elimination. This is also acceptable. Then 2.5.2 says molecular formula of compound Q. Okay, so we start with 10 carbons, and then we have 22 hydrogens, right? And then we have a 3 carbon alkene. So that's 3 carbons is an alkene. So this is supposed to be H of 2N, N is 3 in this instance, so that will give us 6. So what's left? 10 carbons, and then we subtract 3 carbons. We're left with 7 carbons, and then 22 hydrogens, and then we subtract 6 hydrogen. We're left with 16. So that is CnH2n plus 2. So this is so this is the question says we should write the molecular formula. So this is the molecular formula. This is the molecular formula we're looking for. And then 2.5.3 structural formula of compound P. We already know that compound P is propyl. So C. We can put the double bond here, or we can put it there. It doesn't matter. I will still have the same name. And then carbon, saturated, carbon, and then saturated. So yeah, there we have it.
Learners investigate factors that influence the boiling point of organic compounds. The boiling point of some organic compounds obtained as shown in the table below. And then 3.1 says define the term boiling point. So we know fully well that the boiling point is the temperature at which the vapor pressure is equals to the atmospheric pressure, right? So the temperature in which the vapor pressure is equals to the atmospheric pressure. But you have to write it in full. I'm just writing it like this for the sake of time. And then 3.2 says the boiling points of compounds A, B, and C are compared. And then 3.2.1 says, how do the boiling points vary from compound A to C? So we come in here from compound A going to C. So we have minus 42, minus 0.5, and 36. Clearly, the boiling points are increasing, right? So for 3.2.1, we're going to write increases. And then we have 3.2.2, which says, explain the answer to question 3.2.1. So why are these boiling points increases? When you're coming from A to C, you will realize that A has 3 carbons, and then B has 4 carbons, and C have 5 carbons. So we can see clearly that the chain length is increasing, right? So we can say that the chain length increases. And then it doesn't end there. What is the consequence of the chain length increasing? When the chain length increases, we'll have an increase in the strength of the induced dipole forces, right? So we're going to say that the strength of induced dipole forces goes up, and then in conclusion, more energy will be required to overcome the forces. So that's exactly what you're gonna write. More energy required to overcome the forces. I'm just gonna leave it like this for the sake of time, but you have to write it in full when you sit for your exam. And then 3.3 says the boiling points of compounds B, C, and D are compared. Is this a fair comparison? So let's go look at B. Here's B, which is butane, C, which is pentane, and D, which is methyl butane. And then, is this a fair comparison? If we look at the molar mass of B, is 58. The molar mass of C is 72, and the molar mass of D is 72. So no, I don't think this is a fair comparison. And then obviously they're gonna ask us why, because compound B has a different molar mass, right? Has a different molar mass, because when we investigating, when we are doing these experiments in chemistry, we are only supposed to be changing the independent variable, right? We're not supposed to change the control, which we need the molecular mass to be. So if we were comparing only C and D, then that would be fine because they have the same molecular mass. Or if we were comparing A and F, but then as for B, it has a different molar mass, so it's not a fair comparison. So we have 3.4, which says the boiling points of compounds E and F are compared. So let's just erase this and look at E and F. So here's E, which is ethanol, and F, which is ethanol. And then 3.4.1 says state the independent variable for this comparison. So the dependent is what we're looking for, right? In this instance, it will be the boiling point. And now the control is what's kept the same, which is the molecular mass, right? We have 46 and 44. They're not really kept the same, but then they're pretty much close to each other. And then what we are changing here is the functional group, right? You can see that here we have ethanol, and here we have ethanol, alcohol, and then aldehyde. So the independent variable we can say is the functional group. You can even say is the homologous series, and it will still be fine. And then this is 3.4.1, my bad. And now we have 3.4.2, which says write down the name of the strongest van der Waals force present in compound F. So in compound F, the strongest is dipole forces. This question is more of content knowledge than solving any problem. And then 3.5 says which compound D or E has a higher vapor pressure. So the higher the VP, the lower the BP. BP being the boiling point, right? So compound D, which is methyl butane, has a boiling point of 28, and then compound E has a boiling point of 78. So the higher the VP, the lower the BP. Compound D has a lower boiling point compared to compound E. So we're gonna say D has the higher vapor pressure. As a consequence, they say give a reason. So the reason is what we just talked about. The higher the vapor pressure, the lower the boiling point. Clearly, methyl butane has a lower boiling point. As a result, it has a higher vapor pressure. If a compound has a higher vapor pressure, what does that say about the boiling point? What does that say about the melting point? Before we do that, let's do 3.1, which says let's define the term melting point. So melting point is the temperature at which the solid and liquid phase are at equilibrium, the temperature at which the solid and the liquid phase are at equilibrium. And then now 3.2 says, which one of C or D has the higher vapor pressure? Give a reason for your answer. So here we are given compounds and their melting point. So for you to be able to answer this question, you need to know the relationship between vapor pressure and melting point. So what is the relationship between the two? We know fully well that the higher the vapor pressure, the lower the boiling point. The same is true for melting point. The higher the vapor pressure, the lower the melting point. So between C or D, the one with the lower melting point has the higher pressure based on this relationship we're proposing. So which one between C or D has a lower melting point? It's clear to see that C has a lower melting point, right? At minus 16 degrees Celsius versus D, which has a melting point of 16.7. So our answer for 3.2, we would say C. And then why are we saying C? We are saying C because it has a lower melting point. We know fully well that the higher the vapor pressure, the lower the melting point. 3.3.1 says let's define the term structural isomer. So structural isomers are organic compounds that have the same molecular formula but different structural formula. The same molecular formula but different structural formula. Right? And then 3.3.2 says explain why B has a higher melting point than A. Refer to structure, intermolecular forces, and energy in your explanation. So A and B are structural isomers. They have the same molecular formula but different structural formula. So let's look at A. A is clearly branched, right? It says 2-methylhexane. So on the second carbon, we're supposed to have a branch. And then B just says heptane. So B is a straight alkane. That is the only difference between the two. And we're going to use that to explain our answer. So we are already told that B has a higher melting point. If B has a higher melting point, we will know consequently that it has a lower vapor pressure, right? Because the higher the vapor pressure, the lower the melting point. So here we have higher melting point, so we need lower vapor pressure. But why does it have lower vapor pressure but A doesn't have? So the difference between A and B is that B is less branched, right? As we are proposing, B is a straight alkane while A is a branched alkane. But then if it's less branched, then what will that mean? That will mean that we have stronger intermolecular forces. So we have strong IMF. Right? And then stronger intermolecular forces will mean that we need more energy to break bonds in compound B, right? So more energy are required to overcome IMF. Just to recap, we are comparing A and B. B has a higher melting point, so we know that it has lower vapor pressure. If it has lower vapor pressure, it has stronger IMF, and if it has stronger IMF, then it requires more energy to overcome the intermolecular forces, right? But then what's the difference between A and B? The only difference between A and B is that B is less branched. So this tells us that if you have two structural isomers, the one that is less branched will always have a higher melting point versus the one that is more branched. Now let's do 3.4. 3.4 says let's explain the difference in the boiling points of C and D, referring to the intermolecular forces and the energy in our explanations, right?
Let's go back to the basics real quick here. So we know that compound C, right, is an alcohol, and then compound D is an acid, right? So because compound C and compound D are with an alcohol and an acid, we know fully well that they both possess hydrogen bonding, right? We know that they both have hydrogen bonding, right? So we can say that they both have hydrogen bonding. But then if they both have hydrogen bonding, then why do they have different melting points and consequently different boiling points? That is because compound D, right, which is our acid, has two sides of hydrogen bonding versus compound C that has only one side of hydrogen bonding. Now the question you're asking yourself might be, wait a minute, what are we talking about? Why are you saying compound D has two sides of hydrogen bonding? That is because acids can go under a process called dimerization, right? And then alcohols cannot. So we say that compound D has two sides of hydrogen bonding, right? If it has two sides of hydrogen bonding, then what does it mean? It means our compound D has stronger intermolecular forces, right? And then what do we know about compounds that have stronger intermolecular forces? They require more energy. They require more energy to overcome the intermolecular forces. And if it requires more energy to overcome the intermolecular forces, then the boiling point of compound D, right, will be greater than that of compound C. But1 an unsaturated hydrocarbon, and compound X, a saturated hydrocarbon, reacts with bromine as represented by the incomplete equations below. 4.1.1 give a reason why but1 is classified unsaturated. It is classified unsaturated because it has double bonds, right? If an organic compound has double bonds or triple bonds, then it is unsaturated, right? It can still go under addition reaction. So 4.1.1, it contains a double bond. So it contains a double bond. Now let's move to 4.1.2, which says that what type of reaction, addition or substitution, takes place in the following. Reaction 1. Reaction 1, we have but1 plus bromine, right? Because this organic compound here is unsaturated, it can only go under addition reaction, right? And then now we can move to reaction number 2. Reaction number 2, we have X, which is said to be a saturated hydrocarbon, right? So it's an alkane. And then we are adding bromine. So an alkane can only go elimination or substitution, right? But then we are already told here that we have to choose between addition or substitution, right? So clearly our answer here will be substitution. So for B, we have substitution. 4.1.3, write down the reaction condition necessary for reaction 2 to take place. For reaction 2 to take place, we need heat, or we need sunlight. But from sunlight, we're still looking for heat from the sunlight, right? Or we need UV light. And then 4.1.4 says, write down the UPEC name of reactant X, right? Reactant X is a hydrocarbon, and when we substitute bromine, we get 2-bromobutane, right? It should be quite clear that the UPEC name of reactant X will be butane, right? A hydrocarbon. And then 4.1.5, write down the name or formula of product Y. Okay, so again, when we have a chemical equation, whatever that is on the left must be present in the right? It needs to be balanced. So we have butane, right? And then we add in bromine, and then we get 2-bromobutane. So in place of a hydrogen in butane, right, a hydrogen is replaced with bromine, right? And in place of bromine here, we're replacing it with the hydrogen. So Y will be hydrogen and bromine, right? So what is the it is the name of the formula of product Y. So let's not complicate our lives and try coming up with the name. Let's just say HBr, hydrogen bromide. 4.2 says 2-chlorobutane can either undergo elimination or substitution in the presence of a strong base such as sodium hydroxide. 4.2.1, which reaction will preferably take place when 2-chlorobutane is heated in the presence of concentrated sodium hydroxide in ethanol? Write down only substitution or elimination. So if you pay attention, you will realize that concentrated is in bold, right? So that will give us an idea of the knowledge we're supposed to apply. So what is the knowledge that we're supposed to apply? If the base is dilute, we go under substitution. If the base is concentrated, we go under elimination. So since here we are told that the base is concentrated, we are going to go under elimination. If it was dilute, we're going to go under substitution. And then 4.2.2 says write down the UPEC name of the major compound formed in 4.2.1. So we had 2-chlorobutane, right? And it is going under elimination. So when it goes under elimination, we are going to lose the chloro, right? And we're going to be left with but2-ene. So 4.2.2, we have but2-ene. And then 4.2.3 says use the structural formulae to write down a balanced equation for the reaction that takes place when 2-chlorobutane reacts with a dilute sodium hydroxide solution. Now we're using a dilute base, right? And I've said that if we use a dilute base, we go under substitution, and if you use a concentrated base, we go under elimination. So let's write a structural formula for the substitution reaction that would take place. I will start by writing the structural formula of 2-chlorobutane, right? So we have 4 carbons, 1, 2, 3, and 4. And then on the second carbon, we have chloro. So let's have our Cl there. And everywhere else, we just have hydrogens, right? So let me just fill them in real quick, and then we move to the next step. So we're saying that we're using dilute sodium hydroxide solution, right? So let's have plus NaOH, right? And this is going to give us, now the substitution happens, right? How does it happen? This OH here is going to replace the halogen Cl, right? So if that happens, we're going to get 4 carbons again, and then in place of the Cl, we have OH, right? Instead of a haloalkane, we now have an alcohol, right? And then we have a hydrogen, and then there goes another hydrogen. And then plus, we know that in a chemical reaction, whatever you have on the left, you should have on the right, right? So we're going to have NaCl. I want to talk about rate of chemical reactions, the speed in which the reactants turn into products. But how can we measure this rate of chemical reactions? Let's go ahead and take a look. We have reactions such as rusting, which can take years and even decades, and our usual reactions like the one between magnesium and zinc, right? And then in the extreme end, we have things like fireworks that take a split of a second, a fraction of a second to occur. In layman terms, the rate of reaction is how fast the reactants are being used, or how fast the products are being formed. That's what we mean when we say rate of chemical reactions.
in the day-to-day language. So we say that the rate of reaction is equals to the quantity of reactants used divided by the time taken, or the rate of reaction is equals to the quantity of products formed divided by the time taken. That can be in grams and sometimes centimeter cube. But what is the prerequisite for a reaction? When can we say a reaction has taken place? Let's take a look at the collision theory.
We use the collision theory to explain how chemical reactions occur and why reactions differ for different reactions. It states that for a reaction to occur, the reactant particles must, 1, collide, right? So we need a collision between the particles in order for a chemical reaction to occur. Not only do they need to collide, they need to collide while having enough energy, right? Well, maybe you can ask, what constitutes as enough energy? Is energy that is equals to or greater than the activation energy for that reaction. Remember grade 11, we talk about activation energy and reactions. So right, we are building up from that. We need these particles to collide, and then as they collide, they must have energy that is greater or equals to the activation energy for that particular reaction. And then the last thing that needs to occur is that they need the right orientation at the moment of impact. They don't just only need to collide with sufficient energy. They need to collide sufficient energy and they have the right orientation for a chemical reaction to take place. Right, so that is the collision theory. It explains to us how chemical reactions occur. So let's go ahead and take a look at factors that affect the rate of a reaction. The first thing that we're going to talk about is temperature. So think about those 3 points under collision theory that we say needed to occur or we need to meet in order for a chemical reaction to occur. Well, we need enough energy, a collision, and the right orientation. So think about temperature. When you increase the temperature, what are you increasing? You're increasing the average kinetic energy of the particles, right? So obviously that will have an impact on the rate of reaction per the collision theory. So let's take a look. Higher temperature increases kinetic energy of particles. Makes sense because we define temperature as the average kinetic energy of the particles, right? So let's take a look at what the collision theory says. Therefore, more molecules have enough or sufficient kinetic energy when the temperature is increased, because the temperature increases the kinetic energy of the particles. So more molecules will have kinetic energy equal to or higher than the activation energy. And as a consequence, if we have more molecules that have enough kinetic energy greater or equal to the activation energy, we are going to have more effective collisions per unit time. And then as a consequence, the rate of reaction increases. So when you increase the temperature, the rate of reaction increases. Why does it increase? It's these 3 points that you're looking for. More molecules will have sufficient kinetic energy that is equals to or greater than the activation energies. And as a consequence, we're going to have more effective collisions per unit time, right? You can see in the diagram provided that when the temperature is low, there isn't a lot of movement, there isn't a lot of kinetic energy in the particles. But when you increase the temperature, there's a lot of movement, there's a lot of collisions, therefore, as a consequence, right? So that is how temperature affects the rate of a reaction. Okay, and then the graph that we're seeing in front of us, what is that all about? So this graph is the Maxwell-Boltzmann distribution curve, okay? It shows you the kinetic energy on the x-axis and the number of molecules on the y-axis, right? This is how the distribution of energies looks like throughout the molecules.
in a substance. But take a look at this. When we increase the temperature,
we get this graph that is represented by y. We get that line that is represented by y. How does the line represented by y differ from the line written x? In y, the peak of the graph goes down, right, as you can clearly see, and then it shifts to the right. It shifts to the right. Most particles had low kinetic energy, but when we increase the temperature, you can see that most particles have more kinetic energy. So let's say, for instance, the activation energy for this reaction was somewhere here. Let me just erase that. Let's say the activation energy was somewhere here. You can see that in X, the area under the graph is much smaller than the area under the graph of Y, right? So clearly, we're going to have more particles that have energy equals to or greater than the activation energy, right? The area under the graph, as far as the activation energy is concerned, will be much greater when the temperatures increase compared to before it is increased. What I want us to talk about next is the concentration. How does the concentration affect the rate of reaction? We must still be thinking along the lines of the collision theory. Remember, we need a collision, enough kinetic energy, the right orientation. So how does concentration affect any of those three? Let's take a look. Increasing the concentration increases the number of moles per unit volume. Correct, because we know that concentration is equals to the number of moles divided by volume. So when you increase the concentration, you're increasing the number of moles per unit volume. Right. So the collision theory, more molecules have enough or sufficient kinetic energy. More molecules have kinetic energy equal to or higher than the activation energy. And lastly, more effective collisions per unit time. Why is that the case? Take a look at A. You can tell that we don't have a lot of particles in A compared to a lot of particles in B, right? But obviously, when you take a look at the B, because we have more particles in a very small volume, there's going to be a lot of collisions in there because we have more moles per unit volume, right? They are most likely to collide versus when we have a lower concentration versus when we have a very high volume and the number of moles is very small, right? So concentration increases the rate of reaction because when you increase the concentration, you're increasing the number of moles themselves per unit volume. So they are most likely to collide because there is more of the particles, right? There's just no way around that. They are most likely to collide. So that is a concentration. That is how it affects the rate of reaction. Let's take a look at the Maxwell-Boltzmann distribution curve and see how that looks like. We still have the kinetic energy on the x-axis. We have the number of molecules on the y-axis. But you can take a look at C1 before the concentration is increased and take a look at C2 after the concentration is increased. You can see clearly that you can see the graphs here. They've been shown clearly that there are more moles present at C2, meaning more have required activation energy and are able to react, right? There's more moles under the graph C2 when the concentration has been increased. So we're going to have more molecules with EK greater or equals to the activation energy and consequently more effective collisions per unit time and the rate of reaction increases. So you increase the temperature, rate of reaction increases. You increase the concentration, rate of reaction increases. And then when you increase the pressure, the rate of reaction also increases. Let's take a look. So increasing the pressure increases the number of molecules per unit volume, right? Very close to how concentration works. Even though here with pressure, you're not increasing the number of moles, you are decreasing the volume, right? As you can clearly see on the sketch that is shown, we are not increasing the number of moles here, we are decreasing the volume When we decrease the volume, we have that same number of moles, but now in a very small space, right? In a very small container, so to say. So they will be most likely to collide because they're in a very small volume. They're in a very low volume compared to when they are, let's say this is A, compared to when they are in A, right? In B, they are most likely to collide because that is very small. So what does the collision theory say? More molecules have enough or sufficient kinetic energy. More molecules have kinetic energy equal to or higher than the activation energy. More effective collisions per unit time. Let's talk about surface area. That is another thing that affects the rate of reaction. We usually talk about surface area a lot in exams and so on. Let's hear what it says. So increasing the surface area increases the number of molecules that are ready to react, right? That is the main point. That is the point that we need to understand, because everything after that is just the same. When molecules have enough kinetic energy, EK greater than or equals to the activation energy, more effective collisions per unit time. The main point is that increasing the surface area increases the number of molecules that are ready to react. So let's explain what that means. I think we can all agree that if you cut food into smaller pieces, the food tends to cook faster, right? We can all agree. But why is that the case? Why does the food cook faster when it is cut into small pieces? It cooks faster because you've increased the surface area, increasing the number of molecules that are ready to react. So your rate of reaction increases, which in turn the food cooks faster. Let's take a look at the nature of reactants. Substances have different chemical properties and therefore react differently and at different rates. We've talked about that at the very start. The rusting of iron, right, versus fireworks. That is based on the nature of reactants, right? If you increase the temperature of an iron by 5 degrees Celsius, it doesn't really affect its rusting process. The last factor that affects the rate of reaction is a catalyst. The catalyst provides an alternative route of lower activation energy. It provides an alternative route of lower activation energy, right? And then because now the activation energy has been lowered, more molecules have sufficient kinetic energy. That is, the kinetic energy is equals to or greater than the activation energy. And the more effective collisions per unit time will therefore okay. So the Maxwell-Boltzmann distribution curve. Let's take a look at it. So I've extracted this from a past exam question. This is like part of the memo. That's why it says making a criteria here. So take a look at this. Point X is the lower activation energy provided by the addition of a catalyst. So this is where the activation energy was located. But after the addition of a catalyst, point X, that's the lower activation energy, right? So because the activation energy has been lowered, more particles will have kinetic energy that is sufficient to make a reaction, right? A fruitful reaction, a fruitful chemical reaction, an effective collision, and hence the rate of reaction increases. We have just talked about the factors that affect the rate of a reaction. Now let's talk about different ways in which the rate of reaction can be measured. So in grade 12, more especially rate of reactions and chemical equilibrium, you're going to come across a lot of experiments, right? The questions that you're going to be answering will be based usually on experiments. So I'm about to show you different kinds of setups that you can expect as far as the rate of reaction is concerned. So let's take a look at the first setup. The volume of gas produced in a reaction may be measured by collecting the gas in a gas syringe. So take a look at this setup. We have the reactants, and on top of the conical flask, we have a gas syringe. So this setup will obviously work in a reaction where a gas is produced, right? So as more gas is produced, the plunger is pushed out and the volume of the gas in the syringe can be recorded. By measuring the volume at set time intervals, we can graph the data and hence determine the rate of a reaction. Right. So this is the graph you would expect after you've measured the gas produced at set time interval using a gas syringe system. Right. So as gas is produced and it's leaving the conical flask into the gas syringe, this part is going to be pushed out. This is the plunger, right? And then you can see these lines here. They will allow us to calculate the volume of gas produced. And then with the volume of gas produced and the given time intervals that we know, we can be able to calculate the rate of a reaction. This is the graph you would expect. So obviously at the start of the reaction, there is 0 centimeter cube of gas produced. But then as the reaction proceeds, gas is produced and then it fills it, and then it starts to fill the syringe. So at the very start of the reaction, we expect a steep gradient because that's where the reaction is at its fastest. And then as the reaction proceeds, the gradient decreases. And then ultimately, at the end of the reaction, we expect our line to be flat, showing that the reaction has stopped. There is no more gas that is being produced. Another technique we can use to measure the rate of a reaction is to calculate the change in mass, or measure rather, as you can see the setup. So for a reaction that produces gas, the mass of the reaction vessel can be measured over time. The mass loss indicates the amount of gas that has been produced and escaped from the reaction vessel. If the reaction vessel is sealed, this method will not work. So take a look at this. You take your conical flask, you put it on a scale, right? And then you put a cotton wool to allow gas to escape and not liquid. So because there's a cotton wool on the top, the gas will be able to escape, but everything else remain in the conical flask, right? So the decrease in mass will give you the amount of gas that is escaped. Because if there's gas that is being produced and you only have a cotton wool at the top, the gas is gonna leave the conical flask through the cotton wool. So the mass is gonna decrease. But then that decrease in mass, we can therefore use it to calculate the rate of a reaction. But obviously, if the reaction vessel is sealed at the top, this will not work. And lastly, there's reactions where a precipitate is formed. So in reactions where there's a precipitate, the amount of precipitate formed in a period of time can be used as a measure of the reaction rate. For example, when sodium thiosulfide reacts with an acid, a yellow precipitate of sulfur is formed, as you can clearly see in our reaction. So take a look at this. Take a look at the setup. So we have the reaction vessel, right, on top of a paper that has an X on it. There's a marking there on top of the paper. So from the top, right, looking down in the reactants, you can see the X clearly at the bottom of the reaction vessel. But then as the reaction proceeds and this sulfur precipitate is formed, it will cover the marking at the bottom of the vessel. You can see how it looks without the precipitate before it is formed. But after it is formed, then you're no longer going to see the cross. You can see that it is covered. So that is another technique that you can use to actually measure the rate of reaction. So expect to find this kind of setups in the exams and so on, but not only limited to these ones. The following reaction takes place, and after 2 minutes, 4 grams of lithium has been used. Calculate the rate of the reaction. So, there's different ways in which we can calculate the rate of a reaction. We can calculate the rate of a reaction using the mass, number of moles, volume, or concentration. Usually, the question is going to tell you which unit you need to use. But in our case, we are given the mass. So we can go ahead and calculate the rate of reaction using the mass. But because we can easily convert mass to number of moles, let's also do it using the number of moles. Let me show you how. So the first thing that you're going to do, rate of reaction is equals to. So what information are we given? We are given the mass of lithium that has been used. So because lithium is the reactant, we are going to say that the rate of reaction is equals to minus the change in the mass of lithium divided by the change in time. Why is there a minus sign? I'm putting that minus sign because it is the rate of reaction that you're calculating using the reactant. So the change in mass will be negative. So when I put the negative sign there, it ensures that my answer will be positive. If I was given information regarding one of the products, then I was just going to say the rate of reaction is equals to the change in mass divided by the change in time, because the change in mass would be positive given the mass of the product. So here the rate of reaction is going to be equals to minus mass final minus mass initial, right? That is what we imply by the change in mass. So after 2 minutes, 4 grams of lithium has been used. So we can say that now we have 0 as the final, and the initial we have is 4 grams, right? And then we divide that by the change in time. So this is happening over the course of 2 minutes. But obviously we know that the SI unit is seconds when it comes to time. So we're going to say 2 multiplied by 60. We are converting that 2 minutes to seconds. So now it's just a matter of me substituting that in my calculator. So let me go ahead and do that and see what I get. This is 0.033 grams per second. There we go. 0.33 grams per second. That is the rate of reaction when we are using the mass. If the question was specific and saying, let's calculate the rate of reaction in moles per second, we would therefore say, okay, it's fine. The mass that we have, the change in mass is 4 grams, right? So the mass is equals to 4 grams. So let's use this mass to find the number of moles. The number of moles using the mass obviously is equals to the mass divided by the molar mass. So the mass is 4 grams and the molar mass of lithium is 7. So that is 4 divided by 7. Let me just put that in my calculator. .5714. Right. So before you get to the final answer, you want to round off to 4 decimal places. And only when you get to the final answer will you round off to 2 decimal places. So there we go. We have the number of moles of lithium, right, that we used in that 2 minutes. So now we can go ahead and say that the rate of reaction will be equals to minus the change in the number of moles divided by the change in time. So the rate of reaction is going to be equals to minus the change in the number of moles is supposed to be minus 0.5714. Right. The time is still the same, 2 minutes. So we're going to have 2 multiplied by 60. So let me substitute that in my calculator. 0.5714 divided by 120. This is equals to 0.0048 moles per second. There we go. This would be the rate of reaction in moles per second. And what we calculated here above would be the rate of reaction in grams per second. Right. In the exam, most of the time, the question will be specific. Calculate the rate of reaction in terms of grams per second, in terms of moles per second, so on and so on. So this is just the very first example. Quite easy, straightforward, nothing complicated. Let's take a look at the example that follows. Right. So 5 grams of zinc pieces are added to 400 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. To investigate the average rate of the reaction, the change in the mass of the flask containing the zinc and the acid is measured by placing the flask on a direct reading scale. The reading on the balance shows that there is a decrease in mass during the reaction. The reaction which takes place is given by the following equation. There we go, we have the equation. So you can see that this setup, what is going on here, is one of those situations that we talked about when under measuring the rate of a reaction, that you can place your conical flask or whatever you're using, whatever contains the reactants, on top of a scale, and then that decrease in mass can therefore be used to calculate the rate of reaction. But anyway, stories. Let's take a look at the first question. A. Why is there a decrease in mass during the reaction? Right. So, like we talked about, that method only works if there's a gas produced, because you put your reaction mixture on top of a scale, and then as the gas is produced, it's going to escape. So there's going to be a decrease in mass, and that decrease in mass is going to give you the amount of gas that is actually produced. So why is there a decrease in mass during the reaction? Because this hydrogen gas is going to be escaping the vessel, the conical flask, whatever we're using to carry out our experiment. So that is the answer to A. Why is there a decrease in mass during the reaction? The gas that is produced is going to escape the reaction mixture. All right. So that is the answer to A. Let's take a look at the answer. Let's take a look at B. The experiment is repeated, this time using 5 gram of powdered zinc instead of pieces of zinc. How will this influence the rate of the reaction? Another conceptual question. Obviously, the rate of reaction is going to increase if we use powdered zinc instead of pieces. Why? Collision theory. We talked about this. If you use powder instead of pieces, you increase the surface area. So there is more number of moles that are exposed and ready to react. So more particles are going to have enough kinetic energy. What do we mean by that? Kinetic energy that is equals to or greater than the activation energy. More effective collisions per unit time, rate of reaction increases. That is the answer to B. Quite basic, it's just the concepts that you have went through. So that is A, B. What about C? Let's take a look at C. The experiment is repeated once more, this time using 5 grams of zinc pieces and 600 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. How does the average rate of this reaction compare with the original reaction rate? The experiment is repeated once more, this time using 5 grams of zinc pieces and 600 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. How does the average rate of this reaction compare with the original reaction rate? So what is the difference? The concentration of the hydrochloric acid is still the same. What has changed is the volume. Initially the volume was 400 centimeter cube, and now the volume is 600 centimeter cube. If you remember, the factors that affect the rate of reaction, there is no way where we talked about the volume. We only talked about the pressure. And when we were talking about the pressure, it was in relation to gases. In this situation, where the concentration is still the same, the rate of reaction will remain the same. It is not going to increase or decrease. But the reaction might go on for longer because we have more number of moles. But ultimately, the number of moles per unit volume is still the same because the concentration has not changed. So the rate of reaction when we've increased the volume to 600 centimeter cube will be the same to our initial conditions where the volume is 400 centimeter cube. That is C. Let's take a look at D. What effect will the catalyst have on the average rate of this reaction? So obviously the catalyst will provide an alternative path, an alternative route of lower activation energy, and the more molecules, more particles will have sufficient kinetic energy. So we expect the rate of reaction to therefore increase in this situation, right? So these were the conceptual equations. I hope you got most of them right, and you can still remember the section on factors that affect the rate of reaction. Well, let's move to the following example, right? So 5 grams of calcium carbonate powder reacts with 20 centimeter cube of a 0.1 mole per decimeter cube solution of hydrochloric acid. The gas that is produced at a temperature of 25 degrees Celsius is collected in a gas syringe that are set up and are measuring the rate of reaction. And then the first question, write a balanced chemical equation for this reaction. So let's go ahead and do that. We have calcium carbonate, which is CaCO3 plus HCl, hydrochloric acid. And then this is going to give us CaCl2 plus H2O plus CO2. There we go, right? And then now we just need to balance our equation by placing 2 here as a coefficient of HCl. So that is the first part of the equation. And then B says that the average rate of the reaction is determined by measuring the volume of gas that is produced in the first minute of the reaction. How will the average rate of the reaction be affected if, Roman figure 1, a lump of calcium carbonate of the same mass is used, right? So in our experiment, we used powder, right? And then our Roman figure 1, they're saying, what happens to the average rate if a lump of calcium carbonate is used? Obviously, the rate of reaction should go down, right? It should be lower as we are using a lump with less surface area, right? And then Roman figure number 2, 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid is used. So think about the last question. We said that the concentration has remained the same. The last question, I mean this one right here, right? We said that the concentration has remained the same. What has changed is the volume. We have more volume now, but the rate of reaction will remain the same. But in this situation, the volume have remained the same, but the concentration has increased. We have more number of moles per unit volume. So the average rate will actually increase in this situation, because even though the volume has remained the same, the concentration has increased. We have more moles per decimeter cube. But in the previous question, the volume had increased, but we still had the same number of moles per unit volume, per decimeter cube, right? So I hope you can see the difference there. Okay. The following question, consider the following reaction and calculate the reaction rates for the situations that follow. The first question A, Roman figure 1, 1.35 mole of N2O5 is used and the reaction goes to completion in 30 minutes. Okay, we're supposed to calculate the rate of reaction there. Obviously, we can do that in 2 ways. We can just use the number of moles that are given, or we can convert the number of moles to mass and actually use the mass. But it's preference at this point. We can use whatever we want to use. Okay, so let's go ahead and do that. Roman figure 1, we are supposed to calculate the reaction rate. Okay, so rate of reaction. What information are we given? Are we given the products or are we given the reactants? We're given the reactants, so we're supposed to have a minus sign, right? So minus the change in the number of moles of N2O5 divided by the change in time. So this is going to be equals to minus 0 minus 1.35. Everything divided by the time taken. So the reaction goes to completion in 30 minutes. Right. So we're supposed to have 30 multiplied by 60 because we want to convert that 30 minutes to seconds. So 1.35 divided by 30 multiplied by 60. This is equals to 0.00075 moles per second. Okay, there we go. That is the average. That is the rate of reaction in Roman figure 1. Let's take a look at Roman figure 2. Roman figure 2, the rate of reaction. So let's take a look at the information. We have 2.7 moles that are used, and they're used up in 60 minutes. Okay, so minus change in number of moles divided by change in time. This is going to be equals to minus 0 minus 2.7, right? 2.7 divided by 60 minutes. So that is 60 multiplied by 60. So substituting that in my calculator, I have 2.7 divided by 60 multiplied by 60. And then this is equals to 0.00075 moles per second. Right. So these are just the basics. We're just trying to get ourselves comfortable with calculating a rate of reaction and answering these conceptual questions. Let's take it a step further. Let's see how difficult it can get. But rest assured, we are going to be able to do it. Let's go ahead and take a look.
It is actually easy to see that the forward reaction is endothermic. The energy of the products is greater than the energy of the reactants. So the answer to 5.1.1, our reaction is endothermic. 5.1.2, calculate the heat of reaction for the forward reaction. So what is the heat of reaction, or the enthalpy change? Is the energy of the products minus the energy of the reactants. Let's look at the energy of the products first. Our products have an energy of 420 kilojoules per mole, while the reactants start with an energy of 0 kilojoules per mole. So our enthalpy change will be 420 minus 0, which is just equals to 420 kilojoules per mole. That is the answer to 5.1.2. Looking at 5.1.3, write down the activation energy for the reverse reaction. Now we are interested in the activation energy for the reverse reaction. So the activation energy for the reverse reaction will be this energy here at peak, which is 480 kilojoules per mole, minus the potential energy of our reactants. For the reverse reaction, that will be 420 kilojoules per mole. So we have the activation energy being equals to 480 minus 420, which is equals to 60 kilojoules per mole. Right, that is the answer to 5.1.3. Let's look at 5.2. The following graph represents the number of particles against a specific amount of kinetic energy of the molecules. The data for samples R and S was obtained at different temperatures, which affects the rate of reaction. There we have a graph for R and S. We have the number of particles on the y-axis and the kinetic energy of the particles on the x-axis. The first question, 5.2.1, is asking us to define the term rate of reaction. That is the change in concentration of the reactants or product per unit time. It is actually that easy. 5.2.2. What does the area to the right of line T represent? Let's go to our graph and see what we have. We have a line T there. So what does this area to the right of line T represent? You should know by now that that area there represents the number of particles. So that is the number of particles with a kinetic energy that is equals to or greater than the activation energy. The number of particles with sufficient energy, that is 5.2.2. Moving to 5.2.3, which sample was at a higher temperature? Write down only sample R or sample S. So we know that when temperature is increased, more particles will have sufficient kinetic energy. So the graph that has a lot of particles with sufficient kinetic energy was obtained when the temperature was increased. If you look at R, the number of particles with sufficient kinetic energy is given by this graph here. But if you look at S instead, you will realize that not only is it given by that graph for R, but even this portion right here. So we can conclude from that and say that the answer to 5.2.3 is actually simple S. Another way of seeing it is that when temperature is increased, the peak is gonna go down and it is gonna shift to the right, just like what happens with S. Let's move to 5.2.4. 5.2.4. Explain the answer to question 5.2.3 by using the collision theory. So we know fully well that when the temperatures increase, the particles will gain kinetic energy. The average kinetic energy of the particles is going to increase. And then more particles will have sufficient kinetic energy. That is the kinetic energy that is equals to or greater than the activation energy. So the area under the graph to the right of line T should increase, just like we saw with sample S. 5.3. In 5.3, the question is saying that 11 grams of magnesium ribbon reacts with a 0.25 moles per decimeter cube of hydrochloric acid solution at a temperature of 25 degrees Celsius according to the following balanced reaction. There we have it. A table of the results is given below. The first question, use the graph paper that is printed on the last page of the question paper and plot a graph for this result. So even though we don't have a graph paper, let's see what we can do here. So we have our y-axis and we have our x-axis. On our x-axis, we're going to have the time, obviously. So let's have an interval of 1. So we're going to have 1, 2, 3. And then on the x-axis, that is time in seconds. And then on the y-axis, we have the volume. We have the volume in centimeter cube. Right. And then we have 0 to 35. So let's move with an interval of 10. So let's say 1, 2, 3, 4. Those 4 blocks will give us 10. So we have 10 and then 1, 2, 3, 4. Let's have 20. 1, 2, 3, 4. Let's have 30. And then 1, 2. Let's say that is 35. Right. So our first coordinate, we have 0 and 0. So let's just put a bullet point here. And then we have 0.5 and 17. So 0.5 and 17 somewhere here. We have another bullet point right there. 1 and 25. So we have 1 and 25 somewhere here. 1.5 and 30. So midway between 1 and 2 and 30. So something like that. And then 33 and 2. So 33 and 2. 35 and 2.5. 35 and 2.5. And again, 3 and 35. we should have something like that. 5.3.2, use the graph paper and explain what happened with the reaction between 2 minutes and 3 minutes. So let's go ahead and look at that. We're interested in 2 and 3. We are interested in 2 and 3. So let's see what happens at that point. You can see clearly that our line flattens out. Our gradient goes to 0. Our reaction is completed. It is no longer taking place. So that's what happens between t is equals to 2 and t is equals to 3 minutes. Actually, here on the x-axis, it's actually not seconds, but minutes, right? 5.3.3. So in 5.3.3, the question is saying, in a second experiment, the concentration of the hydrochloric acid changed from 0.5 to 1 mole per decimeter cube. Draw a new curve on the same graph paper to show what effect it will have. Label the new curve X. So the concentration of hydrochloric acid has now increased from 0.25 to 1 mole per decimeter cube. So we would expect the rate of reaction to increase. The graph, the new graph that we are supposed to catch, should have a steeper gradient versus the graph we have already, right? So we expecting something like this. It should have a steeper gradient and it should reach completion before our initial graph. So that's what we're supposed to have. If your graph is below your initial graph, then that is totally wrong. You are saying that the rate of reaction is now decreased, which is not the case. Right, the last question, 5.3.4. Assume that the molar gas volume at 25 degrees Celsius is 24.47 decimeter cube per mole. Calculate the volume of acid that was used in the first experiment when the reaction was completed. So in the first experiment, we have a volume at the end of our reaction, which is 35 centimeter cube of H2, right? So let me just copy again. Let me just copy down that equation again. So we have Mg plus what? Plus 2HCl, and we get MgCl2 plus H2. At the end of our reaction, we have some volume of H2, which is 35 centimeter cube. And we are also given the molar gas volume. So we can use that information to find the number of moles of H2. And then from the number of moles of H2, we can find the number of moles of HCl using the balancing coefficient. The concentration initially is given to us as 0.2 moles per decimeter cube. So it should be easy to actually find the volume like we are asked to do. Let's go ahead and do that. So for H2, we're saying that the number of moles is equals to the volume divided by the molar gas volume. So that will be equals to, so the SI unit for our molar gas volume is in decimeter cube. So we have to convert the volume of H2 to decimeter cube. That will give us 35 divided by 1000, and then everything divided by 24.47. Now it is just a matter of putting that in a calculator to get 1.43 times 10 to the minus 3 moles. Right. So now balancing coefficient, the number of moles of H2 divided by the number of moles of HCl is equals to 1 divided by 2. So the number of moles of HCl will be equals to the number of moles of H2 multiplied by 2. And if we do that, we're going to get 2.86 times 10 to the minus 3 moles as the number of moles of HCl. And the last step, concentration, is number of moles divided by the volume. So the volume will be equals to the number of moles divided by the concentration. The number of moles is 2.86 times 10 to the minus 3. The concentration is 0.25. That is 0.011 decimeter cube.
The following apparatus was used by a group of learners in an investigation to find out how surface area affects the rate of reaction between excess solid magnesium ribbon and dilute nitric acid with a concentration of 0.05 mole per decimeter cube. During the reaction, the gas formed is collected in the measuring cylinder. The balance equation for the reaction is given to us right here. The summary of the investigation is tabulated before. So let's take a look. We have experiment 1 and experiment 2, where the mass of magnesium is the same. What is different is the state of division, as we are investigating the effect of surface area. The results for experiment 1 are plotted on the graph below. We can clearly see the graph here where the results are plotted. On the x-axis we have the time, and on the y-axis we have the volume of gas produced. Okay, let's take a look at our equations. The first equation, 5.1, besides the mass and the volume of the reactants, give one other variable that must be kept constant during this investigation. Okay, so besides the mass and the volume of the reactants, we also need to keep the temperature constant. So the answer to 5.1 can be temperature. Why do we need to keep the temperature constant? Temperature affects the rate of reaction. So if you don't control the temperature, then your results will not be conclusive. You're not going to know whether your results are influenced by the state of the division or they're influenced by the temperature. So we need to keep all the other variables constant. We need to control them, hence control variable, and then have a fair test. Okay, that is 5.1. What about 5.2? Write down the dependent variable in this investigation. Well, the dependent variable is essentially what we are measuring, right? We are taking a look at the effect of state of division on the rate of reaction. So what you're measuring here is rate of reaction. It is our dependent variable. It is depending on that which is changing the state of division, which is our independent variable. Okay, 5.2. Let's take a look at 5.3. Use the graph to calculate the average rate of the reaction in centimeter cube per second between 2 and 2.5 minutes. Okay, let's go to our graph. So between 2 and 2.5 minutes, 2 minutes is 120 seconds. Okay, so let's take a look. This is 100, this is 150. 1, 2, 3, 4. So one block represents 10 centimeters. Oh, well, 10 seconds, not centimeters. So 1, 2. So 120 seconds should be here. This is where we have 120. 2 to 2.5 minutes. 2.5 minutes, that will be 150 seconds. So it's just 2 minutes plus half of a minute, which is 30 seconds. So 120 and 150 seconds. All right. So let's go ahead and find the corresponding y values. So let's go up. That is 120 seconds. And this is 150 seconds. And then we can extend this line. So that we can read off our value accurately. Okay, we just don't want to use our naked eye here. We want to take accurate measures. So there we go. So the rate of reaction. So rate of reaction will be equals to the change in the volume divided by the change in the time. All right, why are we using change in the volume? We are given the SI unit we are supposed to use for a rate of reaction is centimeter cube per second. So I'm just respecting that. So let's go ahead and find the gradient. We need to read off these values here. So from 40 to 50 we have 1. We have 1, 2, 3, 4, 5. So it means that one block is 2 units. This will be 42, 44, 46, 48, 50. So it means that here at 120 seconds, we have 42. And at 150 seconds, we have 48. So the change in the volume, we're going to have 48 minus 42 divided by 150 minus 120. Okay, there we go. So let me just put that in my calculator. 48 minus 42 divided by 150 minus 120, that is 0.2. So we have 0.2 centimeter cube per second. There we go. That is the average rate between those 2 points. Okay, that is question 5.3. Let's take a look at 5.4. So 5.4, will the rate of the reaction at 250 seconds be greater than, less than, or equal to the rate of reaction in question 5.3? Give a reason for the answer. So in 250 seconds, it is going to be less than. It is going to be less than. Okay. Why do we say that it is going to be less than? Because as the reaction progresses, of which in our case it is not reversible, as you can see, the amount of reactants gets smaller and smaller. And as we have less number of moles, we're going to have less effective collisions. So we expect the rate of reaction to actually decrease. 5.4. 5.5. Predict how the gradient of the graph for experiment 2 will compare to that of experiment 1. So in experiment 2, we have ribbon as one large piece. And then in experiment 1, we have 5 smaller pieces. So the rate of reaction in experiment 1, we expect it to be higher than that in experiment 2. But what is the question saying? The gradient for the graph for experiment 2, it will decrease. The gradient will decrease in experiment 2 because the rate of reaction will also decrease. And yes, the rate of reaction depends on the gradient. If the gradient is very steep, then the rate of reaction is very high. Okay, that is 5.5. 5.6. 5.6. Calculate the mass of magnesium metal that remains in the conical flask when the reaction is stopped. Assume that the molar volume is 24 decimeter cube per mole. So the molar volume is 24 decimeter cube per mole at room temperature. Okay, fine. Let's go to our equation. Right, our equation, we have magnesium plus HNO3, and then we get in magnesium NO3 2. This 2 is here, it's not there. NO3 2 plus H2. Okay, this is the reaction we have. What is the mass of magnesium that you start with? Because it seems like here we are looking for the mass that is remaining. We start with a mass of 2 grams for both reactions. We start with a mass of 2 grams. So we are bound to use that. So what is the mass of the remaining magnesium at the end of the reaction? How can we possibly do that? Well, we have a graph that shows us the volume of gas produced, right? So what we can do, we can find the number of moles of the gas produced. With the number of moles of the gas produced, we can find the number of moles of magnesium used. With this number of moles of magnesium used, we can find the mass used consequently, and with the mass used and the mass initial that we have, we can find the mass of magnesium that remains. Okay, so these are the steps that we need to take. I keep emphasizing that with this kind of questions, you need your plan fully laid out before you can put pen to paper. Right, everything just becomes extremely simple. You know what you're going to do, when and why. So go ahead and do that. Number of moles of gas produced. We are given our graph, so we need to see where our graph ends here. And can we say that it ends here? I think, yeah, from there on until forever, essentially, our gradient is 0. So we have reached the end of our reaction. So let's take this part. Okay, let's take this part. This is where our reaction ends. Okay, and then we're supposed to extend the line and read off the volume from the graph. So this is the beautiful, well, a beautiful tool. But this is the interesting thing about these questions. You are always given an experiment and you are being a scientist, essentially. You are answering these questions in real time. You've never seen it before, but you have all these skills that you learned, which you need to apply. Okay, so let us see what happens here. Let me join these two lines so that we can read off the value. Okay, I think it will be easy to see here that the volume of gas produced is 60 centimeter cube. Okay, so we will say that number of moles is equals to V divided by Vm. Right, we've said that we're going to do that. We're going to calculate the number of moles of hydrogen gas, of which V is 60 times 10 to the minus 3. That times 10 to the minus 3 converts centimeters to decimeters cubed. I must emphasize, because when you're converting centimeter to decimeter, it's not the same thing as you converting centimeter cube to decimeter cube, right? And then the Vm, it is given to us as 24. Okay, so let's take a look. 60 times 10 to the minus 3 divided by 24. This is 0.0025 moles. So this is the number of moles of the gas produced, hydrogen gas. So now the number of moles of hydrogen gas is to the number of moles of magnesium. We have a 1:1 relationship, right? The balancing coefficients is 1:1. So here, the number of moles of magnesium should also be equals to 0.0025 moles. So there we go. We have the number of moles of magnesium that were used. So we can go ahead and calculate the mass of magnesium. So the mass of magnesium that was used will be the number of moles multiplied by the molar mass. The number of moles is 0.0025. The molar mass of magnesium is 24. So we're going to have multiplied by 24, which is equals to 0.06 grams. So not much of that magnesium was used. So the mass of magnesium that remains will be equals to the mass of magnesium that we started with, 2 grams, minus that which was used, 0.06. So we end up having the mass of magnesium that remains being equals to 1.94 grams. There we go.
Calculate the value of P in the table. So what is the value of P? 0.07, 0.08, 0.09, or you skip the question. Let's find out. So 5.1, we were supposed to define a reaction rate. I'm going to leave that one for you. And the question that follows, 5.2, write down the independent variable for this investigation. So let's go ahead and read through our question statement and sort of figure out what is happening. The reaction between excess dilute hydrochloric acid and sodium thiosulfate is used to investigate factors that influence the reaction rate. We are given the equation as you can clearly see. The concentration of HCl used is 1 mole per decimeter cube. The same volume of HCl is used in each run. The time taken for the cross on the paper under the flask to become invisible is measured. Okay, the table below summarizes the reaction conditions and the results of the experiment. So okay, we have the volume of sodium thiosulfate, that of H2O, that of Na2S2O3, the concentration and the time. 5.2, write down the independent variable. So the independent variable is the variable you are willingly changing, and then the dependent variable is the variable you are measuring. Okay, here we're measuring the time it takes for the cross to be invincible. The variable that you are willingly changing is the volume of sodium thiosulfate. So 5.2, the answer here is volume, the volume of sodium thiosulfate. Okay, Na2S2O3. Okay, so we are willingly changing that volume and we are measuring the time. So we can say that the volume of sodium thiosulfate is our independent variable. Okay, let's take a look at 5.3. 5.3, we're supposed to find the value of P in our table. Okay, that's the determining the value of P is actually not an easy task. Yeah, I had to spend a lot of time trying to figure out. Okay, but then let's pay our attention to run 1. If we pay our attention to run 1, we are given the volume and the concentration. If we were to find the number of moles there, we would have 0.13 multiplied by 50 divided by 1000. Let me put this in my calculator. So 0.13 multiplied by 50 divided by 1000 is 0.0065. So in 50 centimeter cube of sodium thiosulfate, there is 0.0065 moles. How many moles are we going to have? Let's take a look at round 2. In round 2, we're going to have 0.0065 multiplied by 40 divided by 50. This is because now we're no longer using a volume of 50, but a volume of 40. Okay, so 0.0065 multiplied by 40 divided by 50 will give us 0.0052. So these are the number of moles of sodium thiosulfate we have in round 2. To find the concentration in round 2, we would say the concentration is equal to number of moles divided by volume. The number of moles is 0.0052. Okay, the volume is not 40, the volume is still 50 because volume is additive. So 40 plus 10 should give us 50. So we have 50 times 10 to the minus 3. Okay, let me put that in my calculator. When I do that, I get 0.1, just like we have here. Okay, so let's go ahead and determine P. So for P, the number of moles in round 3, we need the number of moles in round 3 first. So those number of moles are going to be equal to 0.0065 multiplied by 30 divided by 50. Okay, so 0.0065 multiplied by 30 divided by 50 will give us 0.0039. So the concentration in reaction, not reaction 3, but round 3 will be number of moles divided by volume. This is 0.0039. The volume is additive. We have 30 plus 20, so that will be 50. Okay, 50 times 10 to the minus 3. That is the same as dividing by 1000. Okay, when I put that in my calculator, I get 0.078. So P should be equal to 0.078. That is the concentration of sodium thiosulfate in round 3. That is 5.3. Let's go ahead and do 5.4. So 5.4, when 0.21 grams of sulfur has formed in round 1, the cross becomes invincible. Calculate the average rate, the average reaction rate with respect to sodium thiosulfate in grams per second. Okay, so we want the reaction rate in grams per second. So that is the change in mass divided by the change in time. Let's take a look at the information we have. For round 1, we're given the time is 20.4 seconds. So we know that delta T is equal to 20.4 seconds. So we're just looking for the change in mass. But we know the number of moles we started with in run 1, right? So in run 1, the number of moles we started with, we calculated it in 5.3. We started with 0.0065 moles. So let's find the mass we started with, so that using this information we have about sulfur, we can find the mass we ended up with, or not the mass we ended up with, but the mass of sulfur that was formed. Okay, so in run 1, the mass, so we're gonna have number of moles is equals to the mass divided by the molar. So the mass will be the number of moles multiplied by the molar mass. Okay, this is the mass we started with, mass initial. The number of moles 0.0065 multiplied by the molar mass. So sodium 23 multiplied by 2 plus, so that is Na2S2. Sulfur is 32, so I have 32 multiplied by 2 plus 16 multiplied by 3. Okay, I already have the answer, but I'm just gonna put it in my calculator once more to verify. Okay, so 23 multiplied by 2, 32 multiplied by 2, 16 multiplied by 3. I'm getting 1.027. 1.027 grams. Initially, I got 1.0478. So I'm just gonna put it back and see where I'm making the mistake. I think this one is the correct one. The one I got initially was wrong. I used 0.0066 instead of 0.0065. Let me see. Yeah, it's 0.0065. Well, so this is the mass initial. This is the mass initial. Okay, we need to be aware of that. So now we know that for sulfur we have a mass of 0.21 grams that is formed. If we convert this mass to number of moles, mass divided by molar, 0.21 divided by 32. So what is 0.21 divided by 32? I'm getting 0.0066. Okay, 0.0066. There's some issue here. Okay, but let's just carry on. How do we move now? We have the number of moles of sulfur that were formed. Okay, 0.0066. With our reaction, let's look at the balancing coefficient. The balancing coefficient of sodium thiosulfate is 1, that of sulfur is 1. So we started with 0.0065 moles of sodium thiosulfate, and 0.0066 of sulfur was formed. Okay, and the balancing coefficient we have 1:1. So the entire sodium thiosulfate was used in reaction 1, not reaction 1, but run 1. Okay, so we know that the mass of sodium thiosulfate goes to 0. So what are we gonna have? We're gonna have the reaction rate being equals to the change in mass divided by the time. The change in mass, we started with a mass of 1.027, and we ended up with a mass of 0 because all number of moles have been converted to sulfur, divided by the change in time, which is 20.4. So let me go ahead and put that in my calculator. I'm getting 0.05 grams per second. Yeah, there we go. That is the reaction rate with respect to sodium thiosulfate. 5.5. Let's take a look at 5.5. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees Celsius. Label this curve as A. On the same side of axis, draw the curve that will be obtained at 35 degrees Celsius and label it B. Okay, I think these are easy marks to get. Let me show you why. Because it's the basics. It has nothing to do with this question per se. It's just the basics. Okay, they just want to see if you know what your graphs looks like if temperature is increased. So here we're gonna have the kinetic energy on the x-axis, and then on the y-axis we have the number of molecules. We have the number of molecules on the y-axis. Okay, now we need to increase the temperature. What happens when you increase your temperature? The peak will go down and shift to the left. That's what the examiner is expecting to see, right? The peak goes down and it shifts to the left. So that's exactly what you're supposed to have on your graph, something like this. So it goes down and it shifts to the left, right? Yeah, as you can see, this is A and this is B. B is for 35 degrees Celsius. Yeah, so that's what happens when you increase the temperature. You will have something that looks like that. Yes, we have A and B. Can we move to 5.5? Yes, we can. Explain the effect of temperature on the reaction rate in terms of the collision theory. Okay, we know fully well that when you increase the temperature, the average kinetic energy of the molecules is gonna increase. More molecules are gonna have kinetic energy equals to or greater than the activation energy. More effective collisions per unit time. Rate of reaction increases. Basics.
The reaction of 15 gram of an NPO sample of calcium carbonate with excess hydrochloric acid of concentration 1 mole per decimeter cube is used to investigate the rate of a reaction. And then we're given the balanced equation for the reaction. And then it goes on to say that the volume of CO2 produced is measured at regular intervals. And then we have the sketch with the volume of the CO2 on the y-axis and the time on the x-axis. And then the first question, 5.1, says define the term reaction rate. We know that the reaction rate is the change in concentration of the products per unit time. The change in concentration of the products per unit time, or the change in concentration of the reactants per unit time. So that is given by the reaction rate equals to the change in the concentration of the products per unit time, or the change in the concentration of the reactants per unit time. I hope you get that. And then 5.2 says, give a reason why the gradient of the graph decreases between T2 and T3. This is the part we're talking about that I just highlighted in yellow on the left hand side. The question is saying, give a reason why the gradient of the graph decreases between T2 and T3. Because now we are T2 and we're going to T3, the amount of the reactants is getting depleted, right? So from T2 to T3, the gradient is decreasing because the amount of the reactants is getting depleted and the reaction rate is going down, right? So the amount of the reactants is getting depleted, and as a consequence the reaction rate is going down. And then we can move to 5.3. We have 5.3.1, and then it says changes in the graph between T1 and T2 are due to temperature changes within the reaction mixture. And then 5.3.1 says, is the reaction exothermic or endothermic? The reaction is exothermic. It's exothermic. Why are we saying that it's exothermic? Because the temperature change is within, right? And then from T1 and T2, the reaction rate increases. Okay, so let me go a bit deeper on that and further try and explain the concept. So in an exothermic reaction, there's a temperature change within, right? The temperature within increases. And then we know that if we increase the temperature in a reaction, the reaction rate goes up, right? And then from T1 to T2, we have a very steep gradient, which shows that the reaction rate is high, right? So the only time a reaction mixture will increase its internal temperature. It's if the reaction is exothermic. And then let's move ahead and go to 5.4. 5.4 says the percentage purity of the sample is 82.5%. And then calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius. So we have T equals to 25 degrees Celsius, and the molar gas volume Vm equals to 24,000 centimeter cube. So we're supposed to calculate the volume of CO2 at X. You can see that at X, that's where the graph start flattening out, right? So what does the graph flattening out tells us? It tells us that at X, the reaction is complete, right? But then we have CO3 calcium carbonate plus 2 HCl, right? We know that the HCl is in excess, so the reaction will complete when the calcium carbonate is depleted. So we cannot use I'm sorry, here I wrote HC instead of HCl. We cannot use the number of moles of HCl to determine the number of moles of CO2, because the HCl is in excess. Even after the reaction is depleted, we still have HCl. But then we can use the number of moles of calcium carbonate to determine the number of the corresponding moles of CO2 that we're going to have. And then after we find the number of moles of CO2, we can then convert that to the volume and determine the value of X. So we're going to start by calculating the number of moles of calcium carbonate, because we have the mass, right, and the percentage purity. So the first thing we're going to do, we're going to say that the mass that's reacted is equals to the mass initial multiplied by the percentage purity, right? So that will be equals to, we know that the initial mass is 15 grams multiplied by 82.5%, which is going to give us, so 15 multiplied by 82.5%, that gives me 12.375 grams. So that's the mass of calcium carbonate that reacted. And now I can convert this mass to the number of moles, and then from there I can then find the number of moles of CO2 produced, which I'll therefore be able to find the volume, which is the X we are interested in. So we know that the number of moles equals to the mass divided by the molar mass. What is the mass? The mass is what we just determined right now, which is 12.375 gram, and then we're supposed to find the molar mass of calcium carbonate. So let me pull up my periodic table and see what that leads us to. So for calcium, we have a molar mass of 40, and then for carbon, that's 12, so that's plus 12, and then for oxygen, that is 16, but then we have 3 oxygen atoms, so that's 16 times 3, which is going to be 12,375 divided by 40 plus 12, that's 52, plus 16, 32, 48. So we have 52 plus 48. So we just have 12,375 divided by 100, which is giving me 0.12375 moles, right, of calcium carbonate. And now we can relate the number of moles of calcium carbonate to the number of moles of CO2 using our balanced equation. We know that the number of moles of the calcium carbonate divided by the number of moles of CO2 will be equals to 1 divided by 1, right? 1 being the balancing coefficient in our balanced equation. We can see that we just have 1. We don't have a number, but we know that we have 1 there on calcium carbonate, and then on CO2 it's also true. For the number of moles of calcium carbonate, we say that it's 0.12375 divided by the number of moles of CO2, and then this is just equals to 1 divided by 1, right? So the number of moles of CO2 equals to 0.12375 moles. So now we have determined the number of moles of CO2. We can then find the volume of CO2. But then how do we find the volume? We know that you can determine the number of moles by dividing the volume by the molar gas volume, right? So we have N equals to V divided by Vm. We know what the number of moles is. That's 0.12375 equals to the volume divided by the molar gas volume, which is 24,000. So if we cross multiply the two, we can then determine our volume, the value of X. So we're gonna get V equals to 0.12375 multiplied by 24,000. And then let me put that in my calculator real quick and see what I get. Multiplied by 24,000. That is giving me 2,270 centimeter cube. So the value of X for our equation, that is 2,970 centimeter cube. So let's carry on and do 5.5. 5.5 says, how will the reaction rate change if 15 gram of a pure sample of calcium carbonate? Initially, the mass that was pure was 12.375 grams. Now the mass that is pure is 15 grams. So what will happen to the reaction rate? The reaction rate will increase. And then 5.6 says, explain why you say it is increasing using the collision theory. So we know that if the mass increases, we're gonna have more particles, right, that are ready to react. And then with more particles, we'll have more collisions per unit time. And then as a consequence, the rate of the reaction will go up, right? Will be high. So that's how you'd explain 5.5. Calcium carbonate is reacting with excess dilute hydrochloric acid, right? And then that is used to investigate one of the factors that affect reaction rate. And then we have some balance equation, right? And then it goes on to say the same mass of calcium carbonate is used in all the experiments, and the temperature of the hydrochloric acid in all experiments is 40 degrees Celsius. And then we have a table there for experiment A, B, C, and then 5.1.1 says, for this investigation, write down the dependent variable. So if you read the question again, you will realize that it says used to investigate one of the factors that affect reaction rate. So the dependent variable here is the reaction rate, because it's what we are investigating, right? The factors that affect the reaction rate. And then 5.1.2 says what is the independent variable. So independent variable is more like, what are we changing to investigate that which we are investigating? If you look at our table, in experiment A, we used granules for calcium carbonate, and then for experiment B we used lumps, and for experiment C we used a powder, right? So the independent variable here is the surface area, because it's what we're changing to determine its effect on reaction rate. And then it goes on to say the carbon dioxide gas CO2 produced during experiment A is collected in a gas syringe. The volume of gas is collected. The volume of gas collected is measured every 20 seconds, and the result obtained as shown in the diagram below. And then we can see the diagram clearly. And then we have 5.2 and 5.2.1. 5.2.1 says what can be deduced from the graph regarding the rate of the reaction during the time interval. And then for 5.2.1 we have 20 seconds to 40 seconds. So let's go and look at this time interval. So from 20 to 40, it starts flattening out, right? It's not really flat, but it's no longer as steep as from 0 to 20. So we can see that reactants are getting used up, right? Are getting used up. And then as a consequence, the reaction rate is decreasing. And then 5.3 says calculate the average rate in centimeter cube per second at which CO2 is produced in the experiment. So for CO2 we are given the volume, right? So our reaction rate will be the change in the volume divided by the change in time, and then we want the average. So when we want the average, we have to consider the entire time interval. If it says between 20 and 40, then we just use the interval 20 and 40. But then it said the average, so we have to use the entire interval. So we're gonna have volume final minus volume initial equals to T final minus T initial. So what is the volume final? The volume final is 500 centimeter cube, right? So we're gonna have 500 minus by 0, because initially it was 0, right? And then we're gonna divide that by T final, which is 60 seconds, and then minus 0 seconds, or second, so to say. So let me just punch that in my calculator. So we have 500 divided by 60 in a way, which is 8.33 recurring centimeter cube per second. And then we are done. And then we can move to 5.4, which says, how will the volume of CO2 produced in experiment B compared to that produced in experiment A? Choose from greater than, smaller than, or equal to. This is a tricky question because let's look at experiment A and experiment B, right? So we have the same volume of HCl for A and B, same concentration of HCl, and then instead of granules, they're using lumps, right? So the reaction rates will be different of these two reactions, but then at the end of the day, the volume of CO2 at the end will be the same because it is said that they use the same mass, right? So for one reaction, to be more precise, experiment A, it will complete quicker than experiment B, but then at the end of the day, they're gonna produce the same amount of CO2. So the answer is equal to, right? And then we can move on to 5.5. 5.5 says a graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the graph for experiment A? So this is experiment A, right? And then this is the graph, and they use granules. So experiment C is powder. So we expecting experiment C to shoot up also, right? Let me use a thinner line to also shoot up, but then the reaction ends quicker compared to experiment A, where they're using granules. So our question is asking us about the gradient. So we're gonna say that the gradient will be greater than, right? Which sound a bit weird. It will be greater than in value, but it's not very scientific. It's the gradient will be steeper. Yeah, but then, well, that's what they want from us. So it's greater than. And they're saying that let's back it up using the collision theory. So again, experiment C is powder, right? And experiment A is granules. So basically, in experiment C, there is more surface area, and as a result of more surface area, we have more particles that are exposed, and then we'll have more effective collisions per unit time, and as a consequence, the reaction rate will increase, right? And then now we can move to 5.6, which says assume that the molar gas volume of at 40 degrees Celsius is 25.7 decimeter cube per mole. Calculate the mass of CaCO3 used in experiment 1. So the information we have is information about CO2, right? So if we determine the number of moles of CO2, then we will use the balancing coefficients to determine the number of moles of calcium carbonate and ultimately calculate the mass, right? So we can say the number of moles of CO2 is equal to the volume divided by the molar gas volume. So what is the volume of CO2? Let's check. It's 500 centimeter cube, right? So we're gonna say 500 divided by 1000, converting to decimeter cube, divided by what? By 25.7, like we are told. So we have 0.5 basically divided by 25.7, which is equals to 0.01946 actually moles. So now let's go to our equation. So now we can see that the number of moles of CO2 will be equal to the number of moles of calcium carbonate, right? Because the balancing coefficients are the same. So this will be 0.01946. So the mass will there be for
the number of moles multiplied by the molar mass. So we have 0.01946 multiplied by 100. This will give you 1.946 grams.
Two experiments, 1 and 2, are conducted to investigate one of the factors that affects the rate of the reaction of aluminum carbonate with excess hydrochloric acid. And then we have the balance equation there for the reaction on the left hand side. Let me just go ahead and write it down. So just give me a second. Plus 6 HCl is going to give us 2 Al 3 H2O plus 3 CO2. And then we have the setup in the image given there. There we have the hydrochloric acid. I think it's been put in slowly, and then we have the aluminum carbonate at the bottom, and then we have a syringe. So one of the products here is a gas, right? So that means that all the gas that will be released as the reaction is taking place is gonna end up in the syringe. The syringe will be sucking out the gas, right? So we're given some information for experiment 1 and then some information for experiment 2. And then the first question says 5.1, define the term rate of a reaction. That is the change in concentration of the products or reactants per unit time, right? The change in concentration of the products or the reactants per unit time. So formula wise, you write it like this. The rate of the reaction equals to the change in the concentration of the products per unit time. And then 5.2 says, using the experimental setup above, state the measurements that must be made to determine the rate of this reaction. So again, look at the picture on the left hand side. Look at the setup. As I've already stated, one of the products of the reaction is a gas, right? It's a gas. And then the time, you can always measure the time manually, right? So for you to calculate the rate of a reaction, we know that this is we need the change in concentration of the products or the reactants divided by unit time. So one of the things you'll need to measure obviously is delta T, which you measure manually. Maybe you use a stopwatch or something. And then now the change in products or reactants. That's sort of like the trick of this question. Because we have this syringe here on the question, on the setup. We are going to measure the volume of the gas that is released. The gas is one of the products, right? So that's how we will use this equation to calculate the rate of this reaction. So the answer will be, we need the time, which we're going to measure manually, and then we need the volume of the gas, right? Volume of the gas, of which we're going to determine from the syringe. Syringes usually they have like what do you call this? They already have markings on them that show the volume and stuff. So you just measure the time, and then the syringe will give you the volume of the gas, and then from there you can calculate the reaction rate. Let's move forward. 5.3 says, using the collision theory use the collision theory to explain how the average reaction rate in experiment 1 differs from the average rate in experiment 2. So if you pay attention here, in experiment 1 they use a volume of 100 centimeter cube for 1.5 mole per decimeter cube of HCl, and then for experiment 2 they use 50 centimeter cube, and then the concentration is 2 moles per decimeter cube, right, of HCl. So now the question is saying, let's use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. So here you can see that here there's less volume, right? Yeah, less volume will mean greater concentration, because concentration is inversely proportional to volume, right? And then here we have more volume. So the rate of reaction of experiment 2 is greater than the rate of reaction of experiment 2. Experiment 2 will take less time because there is more molecules, right? So to put it nicely, the first point you'd say that more HCl particles, right? There will be more HCl particles because the concentration is higher. And then what does more particles give us? More particles give us more effective collisions, right? And then what will more effective collisions give us? More effective collisions, effective collisions is a prerequisite of a reaction, right? So the more the effective collisions, the higher the reaction rate. So the reaction will take less time. And then I've gone through this on a video I made in the past. I'll put it up here. If it will pop up in the screen, you can click and watch it. Here it is on the top left hand side of the screen. Let's move ahead. On that video I talk about how other factors affect the reaction rate, like the surface area, the pressure of a gas, and all that nice stuff. And then 5.4 says the average rate of the reaction in experiment 2 during the first 2.5 minutes is 4.4. So let's write that down. We have delta T, which is 2.5 minutes, right? And then we have the average rate of reaction, which is 4.4 times 10 to the minus 3 moles per minute, right? And then the question says calculate the number of moles. So we need the number of moles of what? Let me see, of aluminum carbonate. So that is, let me just write down the formula. Then we have CO3 there, and then we have this 3 there. So we need the number of moles of this aluminum that remains in the flask after 2.5 minutes. So after 2.5 minutes, the reaction is not completed. The equation then says, what are the number of moles that are remaining? So, okay, we know that the rate of a reaction is given as the change in the concentration of the products divided by the time it takes. We have the reaction rate, it is given to us. We have the change in time, the time it takes for the reaction to get to our point of interest. And then now, if we can calculate this change, right? This change here, then we can then be able to calculate the number of moles. But then even if we were not able to do that, is the information we have. We had to start there and then we'd look for, other ways of doing the question. I'm still gonna do more questions on this topic. So if you wanna see more of that and how we tackle different problems, subscribe to the channel and like the video. So, okay, let me move on. The reaction rate, it is said to be 2.5 minutes. And then the change in the products is what we're given. But then if you pay close attention here, aluminum carbonate is actually not the product, but the reactant, right? So here we're supposed to have of the reactant. And then, okay, there we go. Divided by Oh, actually, I put time where it's not supposed to go. Time is supposed to go here, 2.5. And then here we have the reaction rate, 4.4. Times 10 to the minus 3, that is the same as divided by 1000, right? And then now if you make this reaction, this change in the concentration of R, we get 2.5 multiplied by 4.4, everything divided by 1000. So let me go ahead and put that in my calculator real quick and see what I'm getting. So we have 2.5 multiplied by 4.4 divided by 1000. That is giving me 0.011. So what's the SI unit now? We're getting 0.011, but then what's the SI unit? We know that 2.5 is in minutes, right? And it's been multiplied by the reaction rate, which is in, what's the SI unit? Which is in mole divided by minute, right? So the minute and the minutes cancel out. So the change in the concentration, in the number of moles, is thus 0.011, right? So that's how we are getting to how I'm getting to 0.011 moles instead of moles per decimeter cube. Number of moles in excess equals to, I'm going to explain why I'm doing this in a second, right? It equals to 0.016 minus 0.011, which will give us 0.005 moles in excess, right? So why I'm doing it like this? Let's say you have 8 apples, right? And then here you've eaten 0, and then after some time, now you don't have. After some time, you have eaten 2 apples, right? So, and then you're like, what's the change? What's the change in the apples that I had initially? You're going to subtract the number of apples you started with by the change in the apples you eaten. So here you had eaten 0, now you've eaten 2. So you're going to say 5 minus 2, which will give you 3. And then the 3 will be the axis. So the same thing with this equation. That's the same idea I'm using. Now let's move to 5.1. 5.1 says calculate the maximum volume. So we have volume of CO2 that can be prepared at a temperature of 25 degrees Celsius in experiment 1. Take molar gas volume at 25 degrees Celsius as 24,000 centimeter cube per moles. Okay, we know that the number of moles can also be given by the volume divided by the molar gas volume. So right, so that is N equals to V divided by Vm. In this question, we are given Vm, the molar gas volume, as 24,000 centimeter cube per moles. And then the question says, let's find the maximum volume. So this is what you're interested in. And then what we don't have is the number of moles, right? So if we determine the number of moles, we can then use this formula to calculate the maximum volume of CO2 that can be prepared for experiment 1, right? But then to find the number of moles, it's not really complicated because we can use the equation to do so. We know that in our balanced equation, we have CO2 which is balanced with by 3, right? And then we have aluminum carbonate, which is Al2C CO3, and then we have that 3 on the outside, which is balanced by nothing, which is basically just 1. So what we can do here, this is the number of moles, this is the number of moles. We can calculate the number of moles of CO2, not CO3, I'm sorry for that. We calculate the number of moles of CO2 by cross multiplying. So we're gonna get the number of moles of CO2 equals to 3 multiplied by the number of moles of aluminium carbonate, right? That is 0.016, right? Because the number of moles of aluminium carbonate is 0.016, and then the HCl is in excess. So at the end of the day, all the aluminium carbonate is gonna get used up. So this will give us let me just put that in the calculator real quick. That is going to give us 0.048 moles. So now we have the N we were looking for here. Now we can just calculate V, right? So we're gonna say V equals to the number of moles multiplied by the molar gas volume, which is given as 24,000. So we're gonna have 0.048 multiplied by 24,000 mole per decimeter cube, right? And then this is the SI unit of this is we have an SI unit of mole for moles, and then here is mole per decimeter cube, right? So moles and mole cancel out. We end up with let me put that in the calculator real quick. 24,000. We end up with 1,152. Am I doing that right? Yeah, 1,152 decimeter cube. Oh no, I just realized that the number. Okay, I wrote this wrong. I just realized that here it is given as a centimeter cube divided by mole, right? So mole and mole cancel out, and then we are left with centimeter cube. 5.1. So we're given a Maxwell-Boltzmann distribution curve for a certain reaction, and then we have Q on our y-axis, we have P on our x-axis, and then we have some point R, right? And then 5.1.1 says P and Q are the labels on the axis. What quantity is represented by P? We know that on the x-axis of the Boltzmann distribution curve, we have kinetic energy, right? So 5.1.1 will be kinetic energy. And then 5.2.2, we are supposed to give the name for Q, which is the number of particles. The number of particles. Yeah, this is the same curves we use when we determine the factors that affect a reaction rate, right? And then if you haven't done that, look at the description. I'll put a link to a video where I was explaining that. And then 5.2 says line R represents the minimum energy required for the reaction to take place. And then 5.2.1 says write down the term of the underlined phrase, minimum energy required for the reaction to take place. That's the activation energy. Activation energy is self-explanatory because activation energy, so to say. And then 5.2.2 says, how will the shaded area on the graph be affected when a catalyst is added? Choose from increase, decrease, or remain the same. Now, obviously, it's going to increase, right? Increase. And then I'm going to explain that in a second. Actually, 5.3 asked me to explain why I'm saying it increases. When you add a catalyst, it provides an alternative path, right? So let me just write that down. Alternative path of lower activation energy. Activation energy. So after we have an alternative path of lower activation energy, then more particles will have enough kinetic energy to react, right? Yeah, to react, and as a consequence, we will have more effective collisions, and then the reaction rate gets high, right? And then you have your 4 marks. When you add a catalyst, the alternative path, there will be an alternative path of lower activation energy. So particles that previously didn't have enough EK, now they do, and they will form reactions, right? And then the more the number of reactions, the more the number of effective collisions, and then the reaction rate will go up. And then we move ahead to 5.4. So we have a reaction between powdered calcium carbonate and excess hydrochloric acid. It's used to investigate reaction rate at 25 degrees Celsius. And then we have a balance equation down there. And then several experiments are conducted using the same mass of impure calcium carbonate, and then with different initial concentration of dilute hydrochloric acid. Then the graph represents the results. And then, okay, it is said that we should assume that there are impurities that do not react. Okay, fine. And then 5.4.1 says controlled variable. By control variable, they mean the variable that is constant, is not being changed in any way, right? So if you pay attention to details, when I was reading that statement, it said same mass of calcium carbonate. I just highlighted it in blue on the left hand side. Same mass of impure calcium carbonate. So for 5.4.1, we'll have mass of CaCO3, and then that's the one option you have. And then the other option you have is the temperature, right? They didn't say anything about the temperature, so you can go ahead and see that. And then 5.4.2, it says let's have a conclusion for this investigation. Okay, look at the graph. Look at the x-axis. As the initial concentration of HCl is going up, the average rate of production of CO2 is also going up. And CO2 is our product, right? So that means that concentration is directly proportional to reaction rate. As we increase the concentration of HCl, the average rate of production of CO2 increases. We have more CO2, right? So that means the reaction rate is higher. And then let's move ahead to 5.4.3. It says the calcium carbonate in 6 grams of the impure sample reacts. So we have CaCO3, and then that which is pure is 6 grams, right? And then they say that it reacts with HCl, obviously, of concentration 0.03 moles per decimeter cube in 26 minutes. So we have delta T equals to 26 minutes, right? And then 5.4.3 goes on to say, use the information in the graph to calculate the percentage purity of the calcium carbonate. So we want to calculate the mass of the impure calcium carbonate, and then after we do that, we can go back and calculate the percentage purity. Then they say, assume that the molar gas volume at 25 degrees Celsius is V molar gas 24 1,000 centimeter cube. So, okay, let me just write down the equation down again. So we have calcium carbonate plus 2HCl giving us, okay, let's ignore all the other products and just put CO2, right? Because CO2 is what we're interested in, because that's what we were measuring. So the question is saying, let's calculate the mass of CaCO3, right? And then what do we have? So for CaCO3, we only have the mass of the pure substance, right? And then for 2HCl, what's the information we have for HCl? We only have the concentration. And then for CO2, we have the molar gas volume, we have the average rate, we have the reaction rate, so we have the reaction rate, and then we have the time of the reaction. So it seems like CO2 is what we can use to calculate everything else, because this is where we have the most information. So we can use the reaction rate to calculate the volume of CO2, right? And then after we've used the reaction rate to calculate the volume of CO2, we can use the volume of CO2 to calculate the number of moles of CO2. After we've calculated the number of moles of CO2, we can use the number of moles of CO2 to calculate the number of moles of CaCO3 and ultimately calculate the mass. The thing about this question is that there's no formula I can give you to use in every situation. You have to read the question and understand it, and then you can take it from there. So we know that for a gas, the reaction rate is equal to the change in the volume divided by the change in time. And then if we take this bullet point at the top, where HCl is 0.03, the average rate of production is 50 centimeter cube per minute, right? So we're gonna have 50 equals to the change in volume divided by the change in time. We are told that it takes 26 minutes, so we're gonna have 26 here. And then if we cross multiply, we're gonna get the volume equals to 50 multiplied by 26, which is gonna give us 50 multiplied by 26. That is 1,300 centimeter cube, right? So now we have determined the volume of CO2, like we said. The second step is now to determine the number of moles of CO2. That is given by number of moles equals to the volume divided by the molar gas volume, which is equals to the volume we just determined is 1,300, and then the molar gas volume is 24,000, right? And that is equals to, so we have 1,300 divided by 24,000, which is giving us 0.05417, right, moles. So now we can use the number of moles of CO2 to determine the number of moles of CaCO3 that reacted using the ratio of the balancing coefficient, right? So from our equation, we know that the number of moles of CO3 divided by the number of moles of CaCO3 is equals to 1 divided by 1, right? Because those are the balancing coefficient. So the number of moles of CaCO3 will just be equal to the number of moles of CO2, right? So that will be also 0.05417 moles. So now we've done step 2 to calculate the number of moles of CaCO3. Now we can take a formula and calculate the mass of CaCO3. So we know that the number of moles is also equal to M divided by the molar mass, right? And then we want the mass. So the mass will be equal to the number of moles divided by the molar mass. which is equals to 0.05417 multiplied by, let me check the number of moles of CaCO3. That is 100, right? You can check it on the periodic table. So we're gonna have, let me just put that in the calculator real quick. And then that will be equals to 5.417 grams, right? So now we have the mass of CaCO3 that reacted and the mass of the impure sample, right? So to find percentage purity, we're gonna say it's percentage purity equals to pure substance divided by impure, right? The whole substance. So this is going to be equals to 5.417 divided by 6, which is, let me just put that in my calculator real quick, which is equals to 0.9027. And then after that, you can just multiply that with 100 so that you get it in percentages. So that will be 0.9027 multiplied by 100. That is 90.27%.
Write down the meaning of the term reversible reaction. So a reversible reaction is a reaction where the products can be turned back into reactants. That is the answer to 6.1. 6.2, state Le Chatelier's principle. Okay, this is very key to chemical equilibrium. Chemical equilibrium is basically based on Le Chatelier's principle. Well, it says that when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring a reaction that opposes the change. That is Le Chatelier's principle. Let's take a look at 6.3 and 6.3.1. A change was made to the equilibrium mixture at T is equals to 80 seconds. 6.3.1, write down the change made at T is equals to 80 seconds. So let's go ahead and have a look. This is T is equals to 80 seconds. We have a reaction to AB giving us and getting A2 plus B2, right? At T is equals to 80 seconds, you can see clearly that the concentration, not the concentration, but the number of moles. The number of moles of A2 are increased. There's an increase in the number of moles of A2. And then as a consequence, when the system wants to reinstate a new equilibrium, the reaction that reduces the number of A2 is going to be favored, which is the reverse reaction. That is why we see the number of moles of B2 decreasing and the number of moles of AB increasing. So the answer to 6.3.1, number of moles of A2 are increased, okay? So the number of moles of A2 increase. That is the change that is made at T is equals to 80. 6.3.2, use Le Chatelier's principle to explain how the system reacts to this change. Okay, I think I've touched on that, but let's just go through it again. So let's take a look at our reaction. If you increase the number of moles of A2, the system will want to reinstate a new equilibrium by favoring the reaction that reduces the number of moles of A2. Clearly, the reverse reaction reduces the number of moles of A2 because A2 plus B2 will be turned to AB. So that is how the system will react to this change. It will reinstate a new equilibrium by favoring the reverse reaction that leads to less number of moles of A2. 6.3.2. 6.4. Let's take a look at 6.4. So in 6.4, calculate the equilibrium constant Kc at T is equals to 120 seconds. And then the allocation is 4 marks, right? Yeah, this is a nice question, unlike the questions we usually have where you have 8 marks, 9 marks, so on and so on. So to find the Kc, we need to say that the concentration of the products, so we have A2 and B2, divided by the concentration of the reactants. We have AB. We have to take the concentration of AB to the power 2, We are doing that because of this balancing coefficient. Okay, so Kc will be equals to, we're interested in T is equals to 120. T is equals to 120. We have the number of moles of AB, the number of moles of A, and the number of moles of B2. And we are given the volume in our question statement. It is said to be 4 decimeter cube. Okay, so let's go ahead and find the number of moles, not the number of moles, but the concentration of A2. How many number of moles do we have? We have 8 number of moles for A2. We have 8 moles, right? So we're going to have 8 divided by 4. Number of moles divided by volume will give you the concentration. Multiplied by the concentration of B2. How many moles do we have? We have 2 moles. So that is going to be 2 divided by 4. Everything divided by the concentration of AB. We have 10 moles of AB when the temperature is 120 degrees. So that's going to be 10 divided by 4 to the power 2 because of the balancing coefficients. So now it's just a matter of putting that in my calculator. So let me go ahead and do that fairly quick. Divided by 10 divided by 4, everything to the power 2. I have 0.16. So there we go. That is our Kc at T is equals to 120 seconds. Okay, 6.5. At T is equals to 130 seconds, the temperature of the system is decreased to 100 degrees Celsius. Okay, and then 6.5.1, let's draw a potential energy diagram for this reaction. Okay, let's make sense of the situation we have. Let's go to our graph and look at T is equals to 130 degrees because that is where the temperature is decreased, and see how our reaction is reacting to that change. We have 2AB to give and to get A2 plus B2. Let's go to T is equals to 130 degrees. Let me just erase all this for the sake of clarity and draw a line at T is equals to 130 degrees. Okay, at T is equals to 130 degrees. Let's take a look at the amount of AB. The amount of AB increases. The amount of A2 decreases. Same is true with regards to the amount of B2. So our reactants, the amount of reactants we have decreases while the amount of products increases. Okay, so let's make sense of that. Temperature was decreased and the reverse reaction was favored. If the number of moles of A2 and B2 are decreasing, it means that that reaction was favored. A2 and B2 were converted to AB. So decrease in temperature, let's make sense of that. So when the temperature was decreased, reverse reaction was favored. Which reaction is favored by decrease in temperature? That is exothermic. So the reverse reaction is exothermic because it was favored by decrease in temperature, which tells us that the forward reaction is endothermic. Okay, right. So now we need to draw a potential energy diagram for a endothermic reaction, for a reaction where the forward reaction is endothermic. So what are we going to have? Let me show you. We have our y-axis and we have our x-axis. So cost of reaction and potential energy in kilojoules per mole, usually. Okay, so if we're saying that forward is endothermic, then we're going to have something that looks like this. We have our products A2 plus B2. We have our reactant AB. Okay, I think that is all we need. We can obviously show that this is our activated complex. Let me show clearly that the energy of the products is greater than that of the reactants. Let me show that, okay? So that when I show my enthalpy, it's easy to see, right? So this is my enthalpy. Energy of products minus energy of reactants. 6.5.2, will the equilibrium constant Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150 degrees Celsius. Explain the answer. Okay, it will be less than. It will be less than. Okay, let's explain why it will be less than. It will be less than because when the temperature is decreased at 100 degrees Celsius, we're going to have less product compared to at 150. Because if you increase the temperature from 100 to 150, your forward reaction is going to be favored. You're going to have more products versus the reactants. So 6.5.2, we have less than. And the reason I just gave you right now. Forward reaction is endothermic. So if you decrease the temperature, reverse reaction is going to be favored. We have less product, so the value of Kc goes down. Okay, because Kc is products divided by reactants. That is why we are seeing less than. 6.6. Let's take a look at this one. The initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius. Describe the changes that will be observed on the graph between t is equals to 0 and t is equals to 60. So let me know in the comments, how did you answer 6.6? What I'm currently thinking is that if we add a catalyst, then we will provide an alternative path of lower activation energy. So both the forward and the reverse are going to be favored, right? The rate of reaction is going to be increased. So we are going to reach equilibrium quicker, right? Before t is equals to 40, if we are reaching equilibrium at t is equals to 40. I wonder how you phrased 6.6. So just leave a comment and let me know how you answer the question.
When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is 6.1, Le Chatelier's principle, and we're going to use that to answer 6.2. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balance equation. We can clearly see that we have methane, H2O, to form the hydrogen gas and carbon monoxide. Okay, and then the question is saying 6.2.1, how will the following changes affect the yield of hydrogen gas? Adding more methane. So in our reaction, you can clearly see that CH4 is one of the reactants. So if you increase the amount of CH4, the forward reaction will be favored so that CH4 is used up. The system reinstates a new equilibrium by favoring the reaction that opposes the change. So 6.2.1, adding more CH4, more methane, would increase the yield of H2. So it increases the yield of hydrogen gas. It increases the yield of hydrogen gas. Why is that so? Per Le Chatelier's principle, when there's a disturbance in a closed system, the system reinstates a new equilibrium by favoring the reaction that opposes the change. We have the amount of CH4 increasing. So the system will favor the forward reaction so that CH4 can be used up. And as a consequence of that, the amount of hydrogen gas produced would increase. And then 6.2.2, a decrease in the volume of the container. So this is what we need to understand. A decrease in the volume means an increase in the pressure. Right. So there's an increase in the pressure in our system. How will the system reinstate the new equilibrium? It wants to decrease this pressure. And how does it achieve that? How does the system decrease pressure? It favors the reaction that leads to less number of moles of gas. Okay, but if you take a look at our reaction, we can see that we have methane as a gas, H2O as a gas, carbon monoxide as a gas, and hydrogen gas as a gas. So we need to take a look at the left hand side and at the right hand side, the products and the reactants. In the products, we have 4 moles of gas, right? 3 from hydrogen gas and 1 from carbon monoxide. And then on the reactants, we have 2 moles of gas, right? 1 from methane and 1 from H2O. So it means that if the volume has been decreased and the pressure has went up and we want to decrease the number of moles of gas, then we need to favor reverse reaction. We need to favor reverse reaction because the reactants have less number of moles of gas compared to the products. So in this case, the yield of hydrogen gas would decrease. So we have decrease in the yield of hydrogen gas. And why is that so? For the reasons I just gave, right? We are decreasing the volume, the pressure increases. The system wants to reinstate in equilibrium by favoring a reaction that opposes the change. Since we have increased the pressure, the system wants to decrease the pressure. So reverse reaction will be favored because it leads to less number of moles of gas, hence less pressure. So that is 6.2.2 right there. Okay, let's take a look at 6.3. The sketch graph below shows the changes in the number of moles of methane, steam, and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 decimeter cube container. Okay, 6.3. Write down the reason why there is no change in the number of moles of each of the gases between T1 and T2. Okay, we can see that the number of moles of all those gases between T1 and T2 remains the same. There is no change. Why is that? That is what we need to explain. The reaction has reached chemical equilibrium. The rate of forward reaction is equals to the rate of reverse reaction. So here we just reached chemical equilibrium. That is why we see no change in the number of moles of the gases. Okay, 6.3. Let's take a look at 6.4. 6.4 says, use the information on the graph and calculate the equilibrium constant Kc for this reaction at temperature T. Okay, there we go. So that table, I think that table takes away from chemistry because most people can sketch that table, the feelings and values, but they don't really understand what is going on. You can actually answer these questions in the absence of tables, right? But most people use a table. So let's just go ahead and do that also. What do we start with? Okay, let's have our methane gas, CH4, and then H2O, carbon monoxide, and then the balancing coefficient of hydrogen gas is 3. And then this is the initial number of moles. This is the change, number of moles at equilibrium, and the concentration. So let's take a look at our graph. We can see that initially at T is equals to 0, we start with 1.4 number of moles of methane. So this is 1.4. And then that of H2O is 1.2. So we have 1.2. Carbon monoxide starts at 0, same as hydrogen gas. Okay, and then take a look at this at T2 or T1. When we have reached our equilibrium, we find that the number of moles of carbon monoxide is 0.6. The number of moles of carbon monoxide at equilibrium. So we have 0.6. So clearly, the forward reaction was favored, right? We have more products than we had initially. So it means that here there was an increase of 0.6, right? Meaning that for H2O, there was a decrease of 0.6 as the balancing coefficient is 1:1. If the balancing coefficient was, let's say, maybe 2:1, and then carbon monoxide is 1 and H2O is 2, then we would have minus 0.6 multiplied by 2. But here it is just 1. And then minus 0.6 also because it goes down. And here we have plus 0.6 multiplied by 3. 0.6 multiplied by 3. Right, we are multiplying by 3 because of the balancing coefficient. Right, so this is 1.8. So 1.4 minus 0.6, that is 0.8. And then 1.2 minus 0.6, that is 0.6. And then 0 plus 0.6, 0.6. 0 plus 1.8, that is 1.8. So we have the number of moles at equilibrium. we need to find the concentration by dividing with 2 decimeter cube the volume of the container. If we do that, 0.8 divided by 2, 0.4. 0.6 divided by 2, 0.3. 0.6 divided by 2, once more, 0.3. 1.8 divided by 2, that is 0.9. We have the concentrations at equilibrium. We can go ahead and find Kc by saying that Kc is equals to the products divided by the reactants. Carbon monoxide, hydrogen gas to the power 3. The power is coming from the balancing coefficient. And then CH4 multiplied by the concentration of H2O. So there we go. The concentration of carbon monoxide is 0.3. That of hydrogen gas is 0.9. And we take that to the power 3. Everything divided by methane. 0.4 multiplied by water, which is 0.3. So we put that in our calculators. Let me just do that real quick. 0.3 multiplied by 0.9 to the power 3 divided by 0.4 multiplied by 0.3. And then I get 1.82. So 1.82. Right, that's it. We don't have an ISI unit for Kc. So there we go. That is the Kc. That is the equilibrium constant for this reaction. That is 6.4. So tell me, here's a question for you. 6.5. The temperature T is decreased. The temperature T is decreased. How will this change affect the Kc value for the above reaction? Right, only increase, decrease, or remain the same. The temperature T is decreased. How will this change affect the Kc value? Let me know in the comments what you think the answer to this question is and why. Here we go.
We have a reaction between carbon and sulfur. The system reaches equilibrium at a temperature T in a sealed 2 decimeter container. The Kc value is 9.4 at a temperature T. The first question, 6.1, we're supposed to state Le Chatelier's principle. It says that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is Le Chatelier's principle. 6.1. 6.2, on the other hand, at equilibrium, 1 mole of CS2 is present in the container. Calculate the concentration of S present at equilibrium. What is the information we have? We have the Kc is equals to 9.4. We have the number of moles of CS2 at equilibrium. So the number of moles is 1 mole. But we are given the volume. It is said to be 2 decimeter cube. So we can find the concentration of CS2 at equilibrium. So the concentration of CS2 will be equals to the number of moles divided by the volume. This is going to be 1 divided by 2, which is 0.5 moles per decimeter cube. So we have the Kc and we have the concentration of CS2 at equilibrium. How can we possibly find the concentration of S at equilibrium? We can simply say that Kc is equals to the concentration of the products. So that is the concentration of CS2 divided by the concentration of the reactants. On the reaction side, we have carbon and sulfur. But carbon is a solid, so we don't include it in our Kc expression. In the denominator, we are only going to have sulfur to the power 2. Where is the power of 2 coming from? The balancing coefficient. If we go ahead and substitute, we're going to get 9.4 being equals to the concentration of CS2, 0.5 divided by the concentration of S, sulfur squared. So the concentration of sulfur will be equals to 0.5 divided by 9.4. Everything to the power 1 divided by 2. We're taking square roots on both sides. If you put that in your calculator, you're going to get 0.23 moles per decimeter cube as the concentration of sulfur. There we go, 6.2. Let's go ahead and take a look at 6.3. So in 6.3, the volume of the container is now doubled. After a while, a new equilibrium is established. 6.3. How will the amount of sulfur change as this new equilibrium is established? Choose from increase, decrease, or remain the same. Okay, let's take a look at our equation. We have carbon plus 2 atoms of sulfur to give us CS2. Well, our reaction is reversible. What is happening? We are increasing the volume, right? So let's just note that we increase the volume. According to the Chartelie's principle, if you increase the volume, the system will try to decrease the volume by favoring the reaction that opposes the change. The volume is increased. Increasing the volume decreases the concentration. This decreases the concentration. How can the system react to this change by increasing the concentration? It is going to favor the reaction that leads to more number of moles so that the concentration can increase again. Let's take a look at our reaction. On the right hand side, we have a balancing coefficient of 1 on our gas. And then on the left hand side, on the gas, we have a balancing coefficient of 2. If reverse reaction is favored, that is going to lead to more number of moles, as we have a balancing coefficient of 2 versus 1. So here, the reverse reaction is favored when the volume is doubled. When the reverse reaction is favored, then the amount of sulfur is going to increase. So the answer to 6.3 is increases. We don't have to answer 6.4 because in answering 6.3, we actually addressed it. Let's take a look at 6.5. If the concentration of CS2 changes by X mole per decimeter cube, write down an expression for the equilibrium constant Kc in terms of X. Show all your workings. No simplification or solving for X is required. Let's go ahead and take a look. The Kc is not going to change because in order to change the Kc value, we need to change the temperature, right? So the Kc is still equals to 9.4. The only change that is occurring is with regards to the concentration. Well, let's go ahead and draw our table. There we go. Before we doubled the volume, the concentration of sulfur was 0.23 and the concentration of CS2 was 0.5. When you double the volume, the concentration of sulfur is now going to be equals to 0.23 divided by 2, which is equals to 0.115. On the other hand, the concentration of CS2, 0.5 divided by 2, which will give us 0.25. This is because the volume is being doubled, so the concentration is being halved. So the initial concentration of sulfur, we have 0.115, while the initial concentration of CS2, we have 0.25. We are told that the concentration of CS2 changes by X. In 6.3 and 6.4, we've already explained that the reverse reaction is going to be favored. So this is going to be minus X. The concentration of CS2 is going to decrease by X. While on the other hand, the concentration of CS2 is going to increase by plus 2X. Why plus 2X? The balancing coefficient of sulfur is 2. So that's why we have that there. When I have 0.25 minus X, 0.115 plus 2X. We're going to have Kc being equals to the concentration of CS2 divided by the concentration of sulfur squared. So 9.4 is equals to 0.25 minus X divided by 0.115 plus X squared. this is our KC expression.
Define the term chemical equilibrium. I'm actually not reading the question, but telling you to define the term chemical equilibrium. That is 6.1.1. Let's take a look at 6.1.2. At T1, oxygen, O2, was added to the container. Write down the letter that represents O2. Choose from X, Y, or Z. Let's go through the question statement and see what is happening. So the reaction of carbon monoxide gas CO with oxygen gas O2 is investigated. The reaction reaches equilibrium in a closed container at constant temperature T degrees Celsius, according to the balanced equation below, as we can clearly see here given to us. Changes to the conditions of equilibrium are made at different times. The graph shows the results obtained, X, Y, and Z, that represents the gases in the above reaction. Back to our equation. At T1, oxygen O2 was added to the container, rather than the letter that represents O2. So when we look at our reaction here, X, Y, Z, it should be easy to see that Z is what is added at T1, right? So that answers our question 6.1.2. We're supposed to write down the letter that represents O2 from X, Y, or Z. So the answer to 6.1.2, we have X. That is the letter that represents O2. Yeah, clearly there is a spike with regards to X at T1. So clearly it is oxygen, because that was what is added at T1, we are told. We're not supposed to give a reason, but I've sort of told you why that is. 6.1.3. At T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? How many marks? 1. Okay, I wish it was 2 or 3, because we really have to think. Well, 6.1.46 we must explain, so I guess the 1 mark is justified. So let's take a look at T2. At T2, X goes down, right? So O2 goes down at T2. And then we have one other substance, Y, that goes down, and Z that goes up. Okay, so we are told that the change that was made is with regards to pressure, right? So let's take a look at our reaction. On the right hand side, we have 2 plus, let me use something lighter. We have 2, okay, that is even worse. What is happening? We have 2 plus 1 moles of oxygen on the right hand side, right? We have 3 moles of oxygen on the right hand side. And then on the left hand side, we have 2. Okay. Why are we doing this? We want to sort of see how our reaction will react, how our system will react to a disturbance, because the system wants to oppose the disturbance, right? So what happened to O2? O2 at T2, it went down. Okay, so we're saying that the concentration of O2 goes down, okay? And then look at Y. Y also goes down. But after Y goes down, it doesn't bounce right up, because if you take a look at O2, O2 bounces up after it goes down. And then Y goes down, but keeps on going down. And then Z goes down, but bounces up together with O2, right? So because the changes with regards to pressure, we can say that O2, it's X, and Z is actually carbon monoxide. Z has to be carbon monoxide. So this is CO. And then Y should be carbon dioxide, CO2. So, okay, O2 did go down, but ultimately it went up. So let's change that. O2 actually goes up ultimately, because when the pressure is changed, right, they all go down. Now we can conclude and say that the pressure was decreased here. How do we know that the pressure was decreased? The pressure was decreased because the rate of reaction
the concentration of all the reactants went down momentarily, as we can clearly see here. So O2 goes down for a moment and then it goes up. Carbon monoxide goes down for a moment and then it goes up, as we can clearly see in the diagram that we're given, right? But CO2 goes down and stays there. It goes down and stays there. So the pressure was decreased here, right? And then as the pressure was decreased, reverse reaction was favored. Reverse reaction was favored. Reverse reaction is favored because it is the one that leads to more number of moles of gas, hence increasing the pressure. So what is our equation again? Was the pressure increased or decreased? The pressure was decreased. The pressure was decreased. 6.1.4. Why are we saying that the pressure was decreased? Reverse reaction was favored. Well, I'm not going to write. Let me just tell you. Reverse reaction was favored. And then reverse reaction, when it is favored, it leads to more number of moles of gas, hence increasing the pressure. The only way our system would react in this manner, where it leads to more number of moles of gas where the pressures increase, is if there was a decrease in the pressure, right? So that is the answer to 6.1, 6.1.3 and 6.1.4, right? They look like they all go down momentarily, but you have to see beyond that and see, oh, okay, well, O2 ended up going up, CO ended up going up, and then it is CO2 that goes down ultimately. So reverse reaction has to be favored. Pressure has to have been decreased because the reverse reaction leads to more number of moles of gas, hence increasing the pressure. Okay, 6.1.5. Let's take a look at that one. Write down the letter or formula of the gas that is represented by the letter Z. We already have the answer. 6.1.6. Give a reason for the answer to equation 3.1.5. Well, can I say we already have the answer? Can I say that we already have the answer? We already have the answer. Why am I saying that we already have the answer? We can see that when the pressure was decreased, the concentration of the reactants goes up, right? And we can see that concentration of X went up, which we know to be oxygen gas, and concentration of Z went up. It has to be carbon monoxide because that's the other reactants that we have. So write down the name or formula of letter Z, CO, carbon monoxide. You have the freedom of choice there. So that is 6.1.6. 6.1.7. What change in temperature is made at T is equals to 3? Choose between increase or decrease. T is equals to 3. So at T is equals to 3, O2 goes down. Carbon monoxide goes down. What does that mean? Forward reaction is favored, right? CO2 goes up, we can see. So forward reaction is favored. Let's go to our reaction and see whether our reaction is exothermic or endothermic. The forward reaction is exothermic, right? Forward reaction is favored. So it is the exothermic reaction that is favored, right? So which change in temperature favors exothermic reaction? Well, let's think. Endothermic absorbs heat, right? So if you increase temperature, endothermic is going to be favored so that it can absorb some of that heat, mitigating, right? And then if exothermic is favored, it means that temperature was reduced, and exothermic is favored so that it can release energy and the temperature can increase. So what change was made to the temperature at T3? If exothermic is favored, temperature was decreased, and if temperature is decreased, exothermic must be favored so that the temperature increases, because exothermic releases energy. That is 6.1.7, and we have answered 6.1.8. Use the Gas principle to explain the answer to 6.1.7. And now the elephant in the room, 6.2. Carbon monoxide reacts with water, H2O, at T degrees Celsius. The reaction reaches equilibrium according to the balance equation. We have carbon monoxide plus H2O to give us CO2 plus H2. And then we're given the initial number of moles of carbon monoxide,
of H2O, of carbon dioxide, and of hydrogen gas. And then we're given the volume, which is 2 decimeter cube. How often do we find the volume of 2 decimeter cube? It's like it's an examiner's favorite, this volume of 2 decimeter cube. But anyway, stories. If the equilibrium constant Kc for this reaction at T degrees Celsius is 4, calculate the mass of carbon monoxide present in the flask at equilibrium. Okay, so let's go ahead and have our table, right? So yeah, obviously you can answer the question in the absence of a table, you know, but for the faint-hearted ones, me included in this case, let's use a table. Yeah, it's quite hectic when we don't have a table. Yeah, it's quite hectic when we don't have a table. Yeah, but it's doable. It's doable. I've been convinced that we can do it without a table, but I still prefer a table. Okay, so this is carbon monoxide, this is H2O, this is CO2, and then this is H2. The balancing coefficients, we have 1, 1, 1, 1, so we don't have to worry about that. And then here I'm going to put my initial number of moles. Here I'm going to put the change. Here I'm going to put the number of moles at equilibrium. Here I'm going to put the concentration at equilibrium. So the number of carbon monoxide that I start with is 0.6. H2O 0.6. Carbon dioxide 0.1. H2 0.1. Our Kc is greater than 1. Right? Our Kc is greater than 1. It is 4 actually. Way greater than 1. So the forward reaction needs to have been favored in order for the Kc to be close to 4. That is the first thing that we have to see, right? So what will be the change? With respect to the balancing coefficient, here we can have minus x, because the reactions, they're going down, they're getting used up. And then the products, we have plus x. So at equilibrium, we're going to have 0.6 minus x, 0.6 minus x, 0.1 plus x, 0.1 plus x. And then the concentration, we just divide by the volume. 0.6 minus x over 2, 0.6 minus x over 2, 0.1 plus x over 2, 0.1 plus x over 2. So Kc is equals to concentration of CO2 multiplied by the concentration of H2. Everything divided by concentration of carbon monoxide multiplied by the concentration of H2O. So what is the Kc? The Kc is 4. Concentration of CO2, that is 0.1 plus x over 2. And then H2, 0.1 plus x over 2. Everything divided by concentration of carbon monoxide, 0.6 minus x over 2, 0.6 minus x over 2. So let's solve for x. First thing first, 4 is equals to 0.1 plus x over 2 to the power 2, because they are multiplying each other, right? Divided by 0.6 minus x over 2, everything to the power 2. We can take square roots on both sides. I'm not going to write it down, but hopefully you can see that. You can see the consequence of taking square roots on both sides here. We will have 2 is equals to 0.1 plus x over 2, right? Everything divided by 0.6 minus x over 2. So 2 is equals to 0.1 plus x over 2 multiplied by 2 over 0.6 minus x. 2 and 2 cancels out. 2 is equals to 0.1 plus x over 0.6 minus x. So 1.2 minus 2x is equals to 0.1 plus x. So 1.2 minus 0.1, 1.1. Okay, I feel so stupid, but I don't want to make any mistakes. X plus 2x is equals to 3x. So x is equals to 1.1 divided by 3, which is 0.3667. What are we looking for again? The mass of carbon monoxide at equilibrium. So number of moles of
carbon monoxide at equilibrium. Let's go to our table. Carbon monoxide at equilibrium, we have 0.6 minus x, is that right? So this is 0.6 minus 0.3667. Let me put that in my calculator. I get number of moles being equals to 0.2333 moles. So the number of the mass rather is equals to the number of moles multiplied by the molar mass. So we have 0.2333 molar mass of carbon monoxide. I think just 12 plus 16. So multiplied by 12 plus 16. This is 6.53. So 6.53 grams is equals to well, that's the mass of carbon monoxide at equilibrium. There we go. Iodine molecules dissociating to form iodine atoms in a reversible reaction. And then we are given the balance equation, the Kc, and the corresponding temperature. And then 6.1 says write down the meaning of the term reversible reaction. A reversible reaction is a reaction in which not only does the reactants form the products, but even the products form the reactants, right? And then 6.2 says at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. And then how will each of the following be affected? Choose from increases, decreases, or remain the same. So 6.2, 6.2.1, the value of the equilibrium constant. We know fully well that the only thing that can change the value of the equilibrium constant is the temperature and nothing else. So we will easily say remains the same. And then 6.2.2 says the number of moles of iodine atoms, right? So we have I with the I2 basically, which is giving us 2I, right? So the number of moles of the products are greater than the number of moles of the reactants. And how do we know that? We can see using the balancing coefficients, right? Because we know fully well that the number of moles of I divided by number of moles of I2 will be equals to 2 divided by 1. So the number of moles of I is equals to 2 multiplied by the number of moles of I2. So we know that the number of moles of I are greater than the number of moles of I2. So when we increase the pressure, the system wanna decrease that pressure, right? So it does that by favoring the reaction that leads to less number of moles. And the reaction that will lead to less number of moles is the reverse reaction, because it has the most number of moles, right? So 6.2.2 will say increases. So if it was vice versa and we were decreasing the pressure, then the forward reaction would be favored and we'd have a decrease in the number of moles of I2. And then 6.3 says explain the answer to question 6.2.2 by referring to Le Chatelier's principle. That is basically what I just did, right? What I just explained. The system wanna go back to a state of equilibrium. So if we increase something, the reaction that decreases that something will be favored. So we increase the pressure. So the reaction that leads to the less number of moles will be favored. That is the reverse and more number of I2 molecules. I hope that's clear. And then 6.4 says at 227 degrees Celsius, the Kc value for the reaction is 5.6 times 10 to the minus 12.
Is the forward reaction endothermic or exothermic? So let's make sense of the Kc value first. So at 727, right, the Kc value is 3.76 times 10 minus 3. And then now we told that at 227, the Kc value is 5.6 times 10 to the minus 12, much less than at 727. So we decreased the temperature and the Kc value went down, right? But what does the Kc value tells us? We know that when we want to calculate Kc, we say Kc is equals to basically the products, right, divided by the reactants. That's what we are essentially saying. Although we'll square based on the balancing coefficients and all that, but then this is what we are essentially saying. So if we decrease temperature and the Kc value goes down, it means that now we have less products, right? We have less products. So the reverse reaction was favored by the decrease in temperature. Which reaction is favored by a decrease in temperature? That reaction is exothermic, right? So we're saying that the reverse reaction is exothermic. So that tells us consequently that the forward reaction is endothermic. And the question is asking us to explain whether it's endo or exo, right? The forward reaction. So we're gonna say for our answer endothermic, because we know fully well that the reverse reaction is exothermic because it was favored by a decrease in temperature. And then again, it says fully explain your answer, which is what I just did, right? So when you're explaining your answer, you can start by writing down these K values, explaining that Kc is basically products by reactants, and then you can see that when we decrease the temperature, there is less products, so the reverse reaction is favored. Which reaction is favored by decrease in temperature? That's exothermic. So the forward reaction is consequently endothermic. So let's do 6.5. 6.5 says a certain mass of iodine molecules, I2, is sold in a 12.3 decimeter cube flask at a temperature of 727 degrees Celsius, and we are given the corresponding Kc value. And then it goes on to say, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.9 times 10 to the minus 3 mole per decimeter cube. And then we're supposed to calculate the initial mass of the iodine molecules. So before we go anywhere else, let's have our equation. So we have I2 giving us and getting back from 2I, right? So if we draw our table, we're gonna have the number of moles initial, the change in the number of moles, the number of moles in equilibrium, and the concentration, right? It says that for the concentration of the iodine atoms at equilibrium, we have 4.79 times 10 to the minus 3. So if we have this concentration here, we can then calculate this number of moles here, and then consequently get the change in the number of moles, because initially we had 0 here, right? So now we're gonna say the number of moles is equal to the concentration multiplied by the volume. What is the concentration? It's given as 4.79 times 10 to the minus 3, and then we're supposed to multiply it by a volume of 12.3. So if we do that, we're gonna get 0.058917, right? Is the number we get in here, 0.05817. So from 0
to 0.058917. It means we had a change of plus 0.05817. And then as a consequence, if we have a plus on the products, then we're supposed to have a minus on the reactants, right? Initially, we don't know the mass of the iodine molecules, so we cannot calculate the number of moles. But what we can do is just put N instead, right? And we're gonna solve it when we go forward. So here we're gonna have minus 0.05817 divided by 2. What is this 2 here for? This is because for I we have a balancing coefficient of 2, and then for I2 we have a balancing coefficient of 1. So if you do that, so we're having 0.05817 divided by 2. So we're gonna have N minus 0.02985, right? And then the volume is 12.3. So here we're gonna have N minus 0.02985 divided by 12.3. So now that we have the concentration at equilibrium, we can have Kc is equals to the concentration of I to the power of 2, because that's the products, right? Divided by the concentration of I2 to the power of 1, because that's the balancing coefficient of I2. But we are given the Kc as 4.79, actually as 3.6 by 10 to the minus 3, right? So we're gonna have 3.76 by 10 to the minus 3 is equal to the concentration of I squared, which is 4.79 by 10 to the minus 3 divided by the concentration of I2 to the power of 1. That will be N minus 0.02985 divided by 12.3. So basically, for us to find the initial mass, we have to solve for N first, and then we're gonna use N equals to the mass divided by the molar mass to calculate the mass, right? So if we do that, we're gonna have so I'll write it as N minus 0.02985 divided by 12.3 equals to 4.79 multiplied by 10 to the minus 3 squared. We have a square here, I forgot to write it. And then we're going to divide all of this by 3.76 multiplied by 10 to the minus 3. So we can actually break this N minus 0.02985 divided by 12.3, right? If we do that, we get N divided by 12.3 minus 0.02985 divided by 12.3, which is equals to this same expression. Nothing is changing, so I'm just gonna duplicate it instead of writing it again. So now we can take this term to the right hand side. So we're gonna get N divided by so we're gonna get N divided by 12.3 is equals to, I'm gonna just duplicate the term instead of copying it again. So that term plus 0.02985 divided by 12.3. So now I'm gonna multiply the left hand side and the right hand side by 12.3 so that I can get the value of N, right? So I'm multiplying this whole expression by 12.3. So N will be equals to, if you do the multiplication, you're gonna get 0.105. And now we know fully well that N is equals to the mass divided by the molar mass. So what is the molar mass of I2, right? So we're gonna have 0.05 equals to the mass divided by 127 multiplied by 2. So the mass is 0.105 multiplied by 254, which is equals to 26.6 recurring grams.
Steam H2O reacts with hot carbon at 1000 degrees Celsius according to the following balanced equation. And there we have it. Initially, 36 grams of steam and a certain amount of carbon were placed in a 2 decimeter cube sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225 moles. And then 6.1 says define the term dynamic equilibrium. Dynamic equilibrium is the same as chemical equilibrium. It's the stage in a chemical reaction when the rate of forward reaction equals the rate of reverse reaction. Then 6.2 says calculate the equilibrium constant Kc for the reaction at 1000 degrees Celsius. So again, like we did on the other video, if you haven't watched it, subscribe to the channel and go check it out. So we're going to start by writing the equation down. We have 2 H2O plus carbon in solid form, which is giving us 2 H2 plus CO2. So we're going to draw the table I did on the other video. Please, if you haven't watched it, please go watch it. So we have H2O, we have the carbon, we have the hydrogen, and we have the carbon dioxide. So what we're gonna have first is the initial number of moles, right? And then after we have the initial number of moles, we're gonna have the change in the number of moles. After the change in the number of moles, we're gonna have the number of moles in equilibrium, and then after that we're gonna determine the concentration so that we can calculate the Kc. So it is said that initially we have a mass of 36 kg for H2O, right? And then the volume is equals to 2 decimeter cube. We know that the number of moles is given by the mass divided by the molar mass. The mass is 36, and then the molar mass for H2O is 18. So what is 36 divided by 18? That is 2 moles. So initially we have, let me change the color so that it's more visible. So initially we have 2 moles of H2O, and then we have 0 moles of H2, and then we have 0 moles of CO2. And then it is said that the amount of CO2 at equilibrium is 0.225, right? So that means that the change was also 0.225. And then for H2, we can determine that by using the balancing coefficients, right? So we're gonna see the number of moles of H2 divided by the number of moles of CO2 equals to the balancing coefficient of H2, which is 2, and then the balancing coefficient of CO2, which is 1. So basically, you multiply the number of moles of CO2 by 2, and that will give us 0.45. And then the same is true for H2O, because the balancing coefficient is 2, right? Just like in H2. But then instead of adding for H2O, we're going to subtract, right? 0.45, because at that instant the reaction that was being favored is the forward reaction, right? If it was vice versa, then we're gonna add on H2O and subtract on CO2 and H2. So here we're gonna have 0.45 because we're adding 0.45 and 0, And then for H2O, we're subtracting 0.45 from 2, and that will give us 1.55. And then the concentration at equilibrium, we know that the volume is 2, right? So we're just going to divide 1.55 by 2, and that will give us 0.775. We divided 0.45 by 2, it gives us 0.225. And then 0.225 by 2, that is going to give us 0.1125. And then the question would be, why am I not putting anything for the carbon, right? The carbon is a solid, and in chemical equilibrium, we are only interested in gaseous and aqueous solutions, right? We don't regard solids. So now we can write our equation. We can say that Kc is equals to the products, right, divided by the reactants. So what's the products? We know that we have H2, and then we're supposed to square it. Why are we squaring it? We're squaring it because it has a balancing coefficient of 2. And then we have CO2. And then the reactants, we're going to have H2O, and then we also square it because it has a balancing coefficient of 2. And then we don't regard the carbon because, like I've said, it's a solid. So we can go ahead and substitute those concentrations. So for H2, we have 0.225. So we're going to have 0.225 squared multiplied by the concentration of CO2. The concentration of CO2 is 0.1125. So we're going to have 0.1125. And then divided by the concentration of CO2 of H2O, which is 0.775. And then we square it. After we square it, we can then put it in a calculator, and we have determined our Kc. And that is 0.00942. And then we don't have any SI unit for Kc. So now we can move forward. We have 6.3.1. Then it says the graph shows how the rates of the forward and reverse reactions change with time. These are like the really interesting questions. And then 6.3.1 says, give a reason why the rate of forward reaction decreases between T0 and T1. The rate of the forward reaction is decreasing because the reactants are getting used up, right? So we have reactants are getting used up. And then 6.3.2 says, what change was made to the equilibrium mixture at T3? If both a forward reaction and reverse reaction are favored, they all go up at the same time, then a catalyst was added, right? So they added a catalyst. That is the only way both forward and reverse reaction can be favored at the same time. 6.3.3 says, is the forward reaction exothermic or endothermic? You can see that at T2, forward reaction shoots up, right? It goes up dramatically, and then it eventually starts going down because the reactants are starting to get used up. So at T2, the forward reaction is favored by the increase in temperature. And we know that an increase in temperature only favors endothermic reaction. So we're going to say 6.3.3, the forward reaction is endothermic. Why are we saying it's endothermic? We're saying it's endothermic because it was favored by an increase in temperature. And that's only true for an endothermic reaction. And then 6.3.4 says, refer to the chartelie principle to explain the answer to 6.3.3. That's what we just explained. The forward reaction is favored, and an increase in temperature only favors an endothermic reaction. Consider the balance equation below.
for a hypothetical reaction that takes place in a sealed 2 decimeter cube container at 300 kelvins, that is. So our hypothetical reaction is happening between 2 atoms of P and 2 atoms of some element Q, which is giving us 2 atoms of PQ. Right, I'm calling P not phosphorus and just P because it's a hypothetical reaction. And then 6.1 says define the term chemical equilibrium. Chemical equilibrium is a stage in a chemical reaction when the rate of forward reaction equals to the rate of the reverse reaction, right? And then 6.2 says the amount of each substance present in the equilibrium mixture at 300 K is shown below in the table. And there we have the table there. And then it goes on to say the temperature of the container is now increased to 350 kelvins. When a new equilibrium is established, it is found that 1.2 moles of P is present in the container. And then 6.2.1 says, is the heat of the reaction positive or negative? So at our initial equilibrium, the amount of the reactants, 2P and Q2, it's 0.8 and 0.8 moles, right? And then at 350 K, when the temperature is now increased, right, we have more products. We have more P from 0.8 to 1.2. That tells us that the reverse reaction was favored by the change. So that's why now we have more reactants. So if you increase the temperature, the reaction that will be favored is endothermic, and that's the reverse reaction. So the enthalpy, or the heat of the reaction of the forward reaction, is negative. So our answer for 6.2.1 will be negative because the reverse reaction was favored by an increase of temperature. If the forward reaction was favored, then we're going to say the heat of our reaction is positive. So 6.2.2 says use the Chartelie's principle to explain the answer to 6.2.1. I guess that's what I just did. I just, explained 6.2.2 as I was trying to justify 6.2.1. So 6.2.3 then says calculate the equilibrium constant at 350 kelvins. We know that when we talk about the equilibrium constant, we use the concentration. So the first thing is for us to determine our volume, right? That will help us when we calculate the concentration. The volume is given in the equation as 2 decimeter cube, right? So that's something to note because we're going to use that all the way going down. So now that we want to calculate the Kc, the equilibrium constant of the reaction, we have to form some sort of a table so that we can end up calculating the quantity at equilibrium. So what we're going to do, we're going to say 2 atoms of P plus 2 atoms of Q, they're giving us 2PQ. And then let me take out my ruler and just create that table. Yeah, so there we go. And then we have our initial number of moles, right? It is given on our table at 300K. For P, the initial is 0.8, and then for Q it's also 0.8, and then for PQ is 3.2. And then we are told that at the new equilibrium, for P, we have 1.2. So here we'll have our change, and here we'll have our equilibrium concentration. So we are told that here at equilibrium for 2P, it's 1.2. So what's our change? If we find the change for P, then we can use the balancing coefficients to find the change for everything else. And then from there, we can find the concentration. We get our formula for Kc, we sub it in, and then we're basically done with the equation. So the change for P, to determine it, we'll subtract the moles at equilibrium by the initial moles. That will be 1.2 minus 0.8, which will give us 0.4, right? So if you wanna find the change, you subtract final from initial. Only makes sense. You do the same in physics. If you wanna find the change, you subtract the final by the initial. So now that we know the change for P, we can use the balancing coefficients to find the change for Q and the change for PQ. So we can see that for P and Q, for every is a 2:1 relationship. So let me just write that. So we have the number of moles of PQ, right? If we divide them by the number of moles of Q2, the balancing coefficients will be 2 divided by 1. So if you wanna find the change for Q, you divide the change for P by 2. So 0.4 divided by divided by 2, that will give us 0.2. And then for P and PQ, the balancing coefficients are the same. So in our equation here that we establishing, we just gonna, this was supposed to be P and not PQ. So here for PQ, we just gonna have 2 divided by 2, which is just 1, So the change for P and the change for PQ is the same. It's also 0.4. So for Q2 at equilibrium, we'll get 0.8 plus 0.2, which will give us, which is gonna give us 1, right? And then for PQ, we're gonna have 3.2 minus 0.4, which will give us 2.8. So why are we saying for Q? Why are we saying that for Q it's a plus and then for PQ it's a minus? Okay, this is what's happening. We have a reaction. If the products are increasing, the reactants are decreasing. So it is clear that the reactants are increasing, right? The reverse reaction is being favored. So for all the reactants, the change will add it to find the moles at equilibrium. But then from the products, because the reverse reaction is the one that's being favored, meaning that the products is getting depleted and is forming the reactants, we're going to have a minus instead. So that's why we're not saying plus 0.4, but we're saying minus 0.4, which is thus giving us 2.8. So when we get to this step, all we are left to do with is to find the concentration, and then we can substitute it in our equation. So we have already established that our volume is 2 decimeter cube. So for 2P, we're going to say 1.2 divided by 2, that will give us 0.6. And then for Q2, it will be 1 divided by 2, which will give us 0.5. And then for 2PQ, that will be 2.8 divided by 2, which will give us 1.4. So at this step, we can then say Kc equals to the products, the concentration of the products divided by the concentration of the reactants, right? And then this will be equals to the concentration of PQ squared. Where is the squared coming from? The squared is the balancing coefficient. When you put the concentration, you have to square it by the balancing coefficient. So for Q, which is in the denominator because it's the reactants, you can see that the balancing coefficient is 1. So we're just going to say to the power 1, or you don't have to write that because it's always assumed true. And then for P, we're going to have P to the power of 2 because the balancing coefficient is 2. So what's the concentration of PQ? That's 1.4. So we have 1.4 squared divided. Concentration for Q2 is 0.6 squared, and then the concentration for P is 0.5. And then after that, it's just a matter of putting it in the calculator, which I'm gonna do real quick. So we have 1.4 squared divided by 0.6 squared multiplied by 0.5, which is equals to 10.89. And then we don't have any units for KC. Another thing to be aware of is that when we write in this formula for KC, we only regard reactants or products that are in gaseous or aqueous form. We don't consider solids. Okay, so that is that for that question. Let's move ahead. 6.2.4 says, how will the equilibrium constant in question 6.2.3 be affected when the volume of the container is decreased at constant temperature? Choose either increase or decrease or remain the same. Give a reason for your answer. It will remain the same. Let me just write that down. So it's gonna remain the same. It will remain the same because only temperature can change KC. That's always true. Only temperature can change KC. Because if we increase or decrease the volume, then we have done that for both the reactants and both the products. So if it slows down the forward reaction, it's also going to slow down the reverse reaction equally. So KC at the end of the day is going to remain intact. The only thing that affects KC is the temperature. 6.3 says, more Q2. Q2 is a reactant. So the reactant Q2 is now added to the reaction mixture at a constant temperature. How will each of the following be affected? Choose from increase, decrease, or remain the same. PQ. PQ is a product, so it's gonna increase, right? Because if we increase the reactants, then the forward reaction will be favored so that we can establish our state of equilibrium. So the yield of PQ will increase. So basically what I'm saying is that if you increase the reactants, then the yield of the products will increase. If you increase the product, then the yield of the reactant of the reactants will increase, so the reverse reaction will be favored. And then 6.3.2 says the number of moles of P 2P and Q2, and then they're saying we increased Q2, right? So what will happen to P? The number of moles of P will go down because the forward reaction will be favored if you increase the reactants, right? So 2P will be getting depleted at a higher rate. So for 6.3.2, that will be decreases.
The following equation represents a key reaction in the preparation of sulfuric acid. the process of the reaction is controlled in such a way that the temperature inside the container remains between 370 degrees Celsius and 550 degrees Celsius at all times. 6.1 says, what is represented by the double arrow in the equation? In chemistry, we know fully well that if we have a double arrow, it simply means that the reaction is reversible, right? So 6.1, you just write the reaction is reversible, and you get your 1 mark. And then 6.2 says, why is this reaction known as the contact process? It is known as the contact process because the reaction occurs in the presence of a catalyst, right? So the reaction is in contact with the catalyst, and therefore is known as the contact process. Now the question you might ask is, which catalyst do we need for this reaction? We need vanadium oxide, right? So the catalyst for our contact process is vanadium oxide, spelled vanadium oxide. But that's not what the question is asking us. The question just wants us to explain that it is known as the contact process because you are in contact with a catalyst, and you get your 1 mark. And then 6.3 says, explain what the temperature is preferably not, and then 6.3.1 lower than 370 degrees. So they're telling us that for this reaction, we need the temperature to be at least greater than 370 degrees. We need the reaction to be greater than 370 degrees because if the temperature, is too low, right? If the temperature is too low, then the yield from the reaction will not be enough, right? Because you know that to increase the reaction rate, we need to increase the temperature, right? So that our yield can go up, right? So the temperature, if it's too low, the yield won't be enough. 6.3.2 says, explain why the temperature is preferably not higher than 550 degrees Celsius. Let's look at our equation. Delta H is less than 0, right? So if you increase the temperature too much, then the reverse reaction will be favored. So you'll be basically converting your products back into reactants. And that's not what we want to achieve, right? So you must keep the temperature high enough, but you must not make it too high, because now the reverse reaction will be favored and we will get the reactants again. So here we're saying that a high temperature favors an endothermic reaction, right? A high temperature temp favors an endothermic reaction, right? Endothermic reaction. And then clearly the reverse reaction is endothermic, right? So our reverse reaction is endothermic. So if we increase the temperature, less products will be formed, right? So we're gonna have less products being formed. And then let's move to 6.4. 6.4 is saying, for the process above, the following information is obtained from the analysis of the equilibrium mixture at 400 degrees Celsius. The volume of the container is 200 decimeter cube. The initial quantity of SO2 is 50 moles. And then the equilibrium quantity of SO3 is 22 mole. And then the Kc at 400 degrees Celsius is 7.328. Use the information above to calculate the initial mass of oxygen that was used for this reaction. So we're still going to follow the usual technique we use when we want to find Kc, right? But then the only difference here is that we're going to have a value for Kc. We're going to be solving for the oxygen, basically, right? For the number of moles of the oxygen. And then from the number of moles of the oxygen, we're going to be able to determine the mass, therefore. So we have 2SO2 reacting with O2, and then this is giving us 2SO3. We know that the reaction is reversible, so let's have that there. So here we need the initial number of moles, right? Here we need the change, and here we have the moles at equilibrium, right? And then here we have the concentration. So initially we had 50 moles of SO2, so there goes our 50. And then for O2 we're not given, right? That's what we need to find so that we can consequently find the mass. And then for SO3 we're starting with 0, right? And then at equilibrium we have 22. So at equilibrium for SO2 we have 22, right? So the change here was plus 22. So now we need the change for O2, right? The balancing coefficient here is 2 and here it's 1, right? We usually don't write it, but we know there's a 1 here. So we basically dividing 22 by 2, which will give us 11, right? So if we were given 11 here and we're finding the number of moles of SO3, then we're gonna multiply by 2. For SO2, the balancing coefficients are the same, so we're gonna have 22 here, but we're converting the reactants to products, right? So here we're gonna have minus 11, here we're gonna have minus 22. So what is 50 minus 22? That is 28. And then what is x minus 11? X minus 11. And then now the concentration at equilibrium, right? So we're dividing by a volume of 200 decimeter cube. So we have 28 divided by 200, x minus 11 divided by 200, and then we have 22 divided by 200. So now we can see that the Kc is equals to the concentration of the products divided by the concentration of the reactants. So if we go on with that, our product will only have SO3, right? So we're gonna have 22 divided by 200 to the power 2, right? The balancing coefficient divided by the reactants. So we have 28 divided by 200 for SO2, right? To the power 2 multiplied by x minus 11 divided by 200 to the power 1, the balancing coefficient. But we given the value of Kc, we know that it is 7.328. So now we have to solve for x. How are we gonna do that? What we can do here, we can say that x minus 11 divided by 200 is equals to 22 divided by 200 squared divided by 28 divided by 200 squared multiplied by 7.328, right? This step here might be confusing to some, but it's mathematically true, right? You can check it out and see if it works. So every time when you're solving a question like this in Kc, you can just take a term in the denominator and swap it with the term on the other side of the equation, right? It's true. And then from here, so let's multiply both sides by 200 so that we can get rid of this 200 here, right? So if we do that, we're gonna have x minus 11 is equals to 22 divided by 200 again squared divided by 28 divided by 200 squared multiplied by 7.328, and then we multiply in everything by 200, right? So now you can see that you just add 11 to both sides and you determine x. So if you add 11 to both sides, so let's take this entire expression, right? And then we say plus 11. So now we can erase this minus 11 here. We get x being equals to 27.849, right? So now we can use those number of moles to calculate the mass of O2 initially, right? So we know that the mass is equals to the number of moles multiplied by the molar mass. So that will be 27.849 multiplied by 16 multiplied by 2. Yes, so that will give you 891.167 grams. This is a bit lengthy. You can rewind the video so that you can get more clarity. So 6.5, last but not least, says the temperature for the process above is increased to 500 degrees Celsius. Consider the graph, and then there we have a graph. Which reaction, forward or reverse, is represented by the dotted lines? First of all, let's focus on the reverse reaction. We know that the reverse reaction is endothermic. So when we increase the temperature, the reverse reaction should be favored the most, right? More especially above 500 degrees Celsius. When we're close to reaching that 550 degrees Celsius, we're not supposed to reach for this reaction because the products will be too little, right? So when we increase the temperature, the reverse reaction will be favored, but the forward reaction will also be favored, but the reverse reaction will be favored more because it is endothermic. So hence the dotted line and the other line, they all go up, right? But then you can see clearly that this solid line goes up way above the dotted lines, right? So it is more favored. Hence, the solid line is the reverse reaction. So the forward reaction is the dotted line. So the question is asking us to determine which line is the dotted line. The dotted line is the forward, right? Because we know that the reverse will be favored more than the forward if the reverse reaction is endothermic. There's a lot of weird things in this question. For instance, 6.2.1, we have 1 mark being awarded, and 6.2.2, that is still the case. But 6.3.3 is out of 8 marks. It doesn't make any sense. Let me show you why I'm saying that. So 6.1, we are asked to state Chartelie's principles. So what it essentially says is that if an equilibrium is disturbed, then the system will favor the reaction that opposes that disturbance, right, in attempt to reinstate a new equilibrium, right? So that is 6.1. Let's go ahead and do 6.2 and 6.2.1 so that you can see exactly what I'm talking about. So if we go through our equation statement again here, you're gonna see that it says that 1 mole of pure hydrogen iodide gas is sealed in a 1 decimeter cube container at 721 kelvins. Equilibrium is reached according to the following balance equation. So let's just copy down that balance equation real quick. So we have 2HI, and then we have H2 and I2. Right. So if we set up our table to calculate Kc, we're gonna have something like the following. So let me just do that real quick. So here we're gonna have the initial number of moles, right, on the first column, and then here we're gonna have the change, and then here we're gonna have the number of moles in equilibrium, and the last one we're gonna have the concentration. So what we're given here is the initial number of moles of hydrogen iodine, right? It is said to be 1 mole, and then from there we're given the number of moles at equilibrium of I2. So the number of moles at equilibrium of I2, we have 0.11. Initially we didn't have any H2 or I2, right? So we had 0 and 0 here. So it means that the change of I2 is plus 0.1, right? Not 0.1 but 0.11. Yeah, so we have 0.11 here, and then that is the change in the number of moles of I2. But then the change in the number of moles of I2 is the same as the change in the number of moles of H2, right? So we can put 0.11 here. We're saying that they're the same because we have the same balancing coefficient. But then when we come here, because now we have 2, we're gonna have 2 multiplied by 0.11, right? Which is 0.22. So we have 0.22 right there. So with that 0.22, we can then find the number of moles of HI at equilibrium, right? So it's gonna be 1 minus 0.22. That's how you do it. And then in the product signs, you just add. So 1 minus 0.22, I'm getting 0.78. So we have 0.78. Here we have 0.11. So 6.2.1, we're looking for the number of moles of H2 at equilibrium. We're looking for the number of moles of H2 at equilibrium. So here they are 0.11. So we have 0.11 moles. And then the number of moles of HI at equilibrium, here they are, we have them now, right? We have 0.78 moles, right? And all this work just for 1 mark. That's what I was talking about when I say, yeah, I don't really understand the mark allocation in this question. Maybe there's a quick way of finding those number of moles at equilibrium. You can say that for H2, right? But then for HI, you really need to, take it a step further to find those number of moles at equilibrium. But anyway, stories. Let's move to the second question, to the third question, by the way. 6.3.1. The equilibrium constant Kc at 721 kelvins is 0.02, and then the temperature of the container is now increased to 850 K. The equilibrium constant Kc is now 0.09. So it has increased with an increase in temperature. What does that mean? Let's go ahead. So the first question is the forward reaction exothermic or endothermic? It is endothermic. It is endothermic. And why am I saying that? 6.3.2. We need to fully explain that. So what we know, right, just from the basics, is that an increase in temperature, let's not forget, let me just write this first. Kc is equal to the concentration of the products divided by the concentration of the reactants, right? So if Kc increase, it means that now we have more products. The forward reaction was favored. So the question is saying, is the forward reaction exothermic or is endothermic? The forward reaction is endothermic. That is because when the temperature was increased, we had more products, right? So it only makes sense that the forward reaction is endothermic. Because if you increase temperature, endothermic is favored. And as we can see that our Kc value has went up, we can clearly see that the forward reaction was indeed favored. Right. And then 6.3.38 marks. Right. Let's calculate the mass of HI present at the new equilibrium at 850 K. Right, so let's start with the initial number of moles. So the initial number of moles, we have 1, right, as we've already talked about. And then for H2 we have 0, for I2 we have 0, right? So we have that there. But then now we don't know the change anymore, because that change we had was for 721 kelvins. Now we're at 850. We don't know the change anymore, so we can put a variable in place of the change, right? We know that for the reactions you have to subtract. So let's say minus 2x, right? And then if this is minus 2x and we have a balancing coefficient of 2, then for H2 it should be plus x, because the balancing coefficient there is 1, and then plus x again, right? And then for HI at equilibrium we're gonna have 1 minus 2x, and then for H2 we're gonna have 0 plus x, then 0 plus x. And now we move to the concentration. So the concentration, the volume is 1, right? And we know that concentration is equal to number of moles divided by volume. So the concentration will just be 1 minus 2x x again. And now we have our concentration at equilibrium in terms of x. Yeah, we can go ahead and set up our equation, our expression for Kc. It will be the concentration of H2 multiplied by the concentration of I2 divided by the concentration of HI squared. We're squaring that because our coefficient here is 2, right? So let's go ahead and substitute. In place of Kc, we're gonna have 0.09 being equals to the concentration of H2, that is x, concentration of I2, that is x again, and then everything divided by 1 minus 2x to the power 2, right? So we're gonna have 0.09 being equals to x squared divided by 1 minus 2x squared. So what you can do here, you can cross multiply and complicate your life, or you can take square root on both sides. Let's take square root on both sides so that I can show you what I'm talking about. So we can take the square root of 0.09, and then on the right hand side we can take the square root of this entire thing. So what is the square root of 0.09? That is 0.3. So we have 0.3 being equals to square root of x squared, that is x, and then in the denominator we're just gonna have 1 minus 2x. And just like that, we don't have a square anymore, because if we kept the square there, we would have to solve a quadratic equation, which is something I'm not really looking forward to. So if we cross multiply here, we're gonna get x being equals to 0.3, and then what is 0.3 multiplied by minus 2x? That is minus 0.6x. Right, so you can see that we can take this term to the left hand side. If we do that, we're gonna get 1.6x being equals to 0.3. So x is equals to 0.3 divided by 1.6. So what is 0.3 divided by 1.6? I'm getting 0.1875 moles. So the value of x is 0.1875 moles. But we're not looking for x, we're looking for the mass of HI present at new equilibrium. The mass of HI present at new equilibrium. So let's go ahead and find the number of moles of HI at equilibrium. It's 1 minus 2x. So we can say that the number of moles will be equals to 1 minus 2x, but we now know what x is. It is 0.1875. So what is the number of moles I'm getting 0.625, right? So we have 0.625. So we have the number of moles of HI at equilibrium. Lastly, the mass will be equals to the number of moles multiplied by the molar mass. The number of moles is 0.625. I know that the molar mass of hydrogen is what? What's the molar mass of hydrogen again? I know that it is 1, right? How can we forget that? Now we just need the molar mass of I. That is 127, right? And then if I multiply those two, I'm getting 80 grams.
In this video, I want us to talk about acids and bases. So we have two theories that we're going to base our definitions on. The Arrhenius theory and the Lorentz-Bronsted theory. So under Arrhenius theory, an acid is a substance that produces hydrogen ions, while a base is a substance that produces hydroxide ions. But that's very vague. Let's go ahead and take a look at how that actually looks like. So Arrhenius theory. An acid produces hydrogen ions. Let me show you what I'm talking about. So for instance, let's take HCl as an example, and then plus H2O. What are we going to get? We're going to get Cl minus plus H3O plus. This presence of H3O plus is what we refer to as hydronium ions. But the definition says hydrogen ions. So why are we now talking about hydronium ions? Well, they, for the most part, treated the same. Take a look at this. HCl can give us H plus plus Cl minus. So if a substance produces H3O plus or H plus, then it is considered an acid. It produces hydrogen ions or hydronium ions. So this is how we define an acid under Arrhenius theory. Let's go ahead and take a look at a base once more. So we say that a base is a substance that produces hydroxide ions or OH minus when it dissolves in water. So let's go ahead and take a look at that. So which base can we use? Let's take NaOH. We're going to come across this base so many times. It is sodium hydroxide. So NaOH, let's dissolve it in water. What are we going to get? We're going to get Na plus plus OH minus. This is a base. When dissolved in water, it produces hydroxide ions. Do you understand what is going on?
Not really, especially on acids.
Okay, what is the issue there with the acids?
Okay, so it was said that HCl plus H2O give us H3O plus Cl minus, right?
Yeah.
So here he said HCl gives us H plus Cl minus. Does it mean that the H plus that HCl gives is dative covalently bonded to H2O?
Oh, yes. Yeah, that is grade 11 knowledge right there, covalent bond. I forget about that sometimes. Yeah, I think we can say that. We can even go ahead and draw a low structure diagram and see if we're gonna get H3O plus. But I know this to be true. It's just that in grade 12 physical sciences, we don't even think about it. We just know that HCl plus H2O will give you Cl minus plus H3O plus. So these two equations, they're gonna lead to the same consequence all the time. So whether in an exam you decide to use this equation 1 or you decide to use this equation 2, the consequences are going to be the same. That is going to be clearly demonstrated when we solve some problems. Can you take a look at the second definitions? Okay, Lorentz-Bronsted theory. This is actually the easier between the two. Arrhenius theory, well, still easy, but
Lorenz-Bronsted theory is relatively easy compared to Arrhenius theory. So what does Lorenz-Bronsted theory say? Let's take a look. An acid is a proton donor and a base is a proton acceptor. That's it. That's the definition. You can come across this in the exam for 2 marks. What is an acid? And then you say proton donor and then you get 2 marks. So 1 word, 1 mark. And then a base is a proton acceptor. Alright. And then obviously, if you talk about the acceptance of a proton and the donation of a proton, then we go ahead and talk about what we refer to as an conjugate acid-base pair. We talk about what we refer to as a conjugate acid-base pair. Okay, but before we can just talk about acid conjugate base pairs, let me just show you what we're talking about when we say that an acid is a proton donor and a base is a proton acceptor. Maybe before we can do that, tell me, is H2O an acid or a base?
It is a neutral substance.
Okay, right. Most of the time, if it is reacting with an acid, it is going to act as a base, and then if it is reacting with the base, it's going to act as an acid. And we can show this idea of an acid being a proton donor and a base being a proton acceptor clearly using a reaction between an acid and the H2O, a reaction between a base and H2O, and even just a reaction between a common acid and a base. We can still demonstrate that fully well. So let me show you what I'm talking about here. Let's say, for instance, we have HCl plus H2O. There we go again, to give us Cl minus plus H3O plus. Okay, so take a look at this definition. An acid is a proton donor. What do we mean by proton donor in our case? H plus. And the base is a proton acceptor, H plus. So take a look at HCl. We start with HCl and then now we have Cl minus. So what has happened there? From HCl to Cl minus, what has happened there? Well, we had a proton, we had H plus, and now it's no longer there anymore. It would imply that this HCl is an acid because it is a proton donor. It has donated a proton. It was HCl, now it is HCl, it is Cl minus. Initially it was HCl, now it is Cl minus. So clearly it has donated a proton. So we would refer to it as an acid.
Okay, does it mean that to classify SPs as an acid or a base, we do not consider the hydrogen?
You'd have to explain to me what you mean by that when you say we don't consider the hydrogen. In this example that we have, what is leading you to say we don't consider a hydrogen when we consider a species an acid or a base?
Okay, it is because to consider HCl an acid, we spoke about Cl being negative, and we did not talk about H being positive.
Okay, our definition is that an acid is a proton donor. So the only reason why we're saying that HCl is an acid is because it has donated a proton. Because take a look at this. HCl is made up of H plus and Cl minus. So this is HCl, right? And then after it reacts with H2O, we now have Cl minus plus H3O plus. So it has donated a proton. That's why we're referring to it as an acid.
Okay.
Okay, so let's get rid of this. So HCl in this case is our acid. Okay, and then if this is an acid, then the H2O will act as a base. But is it clear that it's a base without putting that into context? What is a base? A base is a proton acceptor. So tell me, does H2O accept a proton?
Yes.
Yeah, it accepts a proton to become H3O plus. So because it accepts a proton, we refer to it as a base.
That's it. That is Lorentz-Bronsted theory. So HCl is an acid because it donates a proton, and H2O in this case will be a base because it accepts a proton. Right. So that is acid, that is base. We're about to talk about conjugate base pairs in a few, but let me just give you another example of a reaction between an acid and a base. Right, so instead of using H2O, let's just go ahead and use NH3 plus H2O. So NH3 is a common base, and H2O in this case will act as an acid. But what are we going to have ultimately? We're going to have NH4 plus OH minus. So let's go ahead and break this down. Take a look at NH3. Is NH3 acting as an acid or a base in this situation?
It is acting as a base.
Why do you say that it is acting as a base?
That is because here it accepted a proton.
And then H2O on the other end?
It is acting as an acid.
And why is that so?
Because if we have a base here, H2O will act as an acid, and it has also donated a proton.
Right. Okay, so we say that this is a base because it accepts a proton, and then this is an acid because it donates a proton. Right. Okay, so if this reaction was reversible, so we're taking a look at it from the product side going to the reactants. What would you classify OH as?
I would classify it as a base because according to Arrhenius theory, it says that bases are substance which produces hydroxide ions.
Okay, right. That is according to Arrhenius theory. If you were to classify it as a base and have to explain according to Lorentz-Bronsted theory, what would you say in that case?
I would say that OH negative, OH minus is a base, and that is because according to Bronsted-Lowry, a base is a proton acceptor. Ooh.
Yeah, that's true.
This one,
Yeah.
clearly, we have OH minus, which has become H2O, meaning that it has accepted a proton, and NH4 will become NH3, losing a proton.
Okay, so OH minus is our base, and NH4 is what?
It's an acid.
When we break down a reaction in this way, this is what we refer to as an acid-base conjugate pair. This is an acid-base conjugate pair. Right, so if a question says identify a conjugate acid-base pair in the reaction above or in the reaction below, this is what you need to do. By definition, an acid-base pair consists of two species in an acid-base reaction. One acid and one base that differ by the loss of or a gain of proton. Right, so the difference between these base, let me change my color here. The difference between these base and this acid is a loss of a proton or a gain of a proton, depending on how you look at it. And then the difference between H2O and OH minus, still the same, is a loss or a gain of a proton, depending on how you look at it. So this is an acid-base conjugate pair. Right, so we've touched on the Arrhenius theory, we've touched on Lorentz-Bronsted theory, and we've touched on conjugate acid-base pairs. Now, let's take a look at an amphiprotic species. So it is a species that can act as either an acid or a base. A species that can act as either an acid or a base. A good example of an amphiprotic species, we used to call it an ampholyte back in the days, is H2O. Clearly, you've seen that when H2O reacts with a base, it acts as an acid. And then when it reacts with an acid, it acts as a base. So it is amphiprotic because of that. It can act as either an acid or a base. H2O is not the only species that can act as either an acid or a base. We'll see that as we progress. We're going to come across examples where we have an amphiprotic species, or we're supposed to identify an amphibolite and it's not H2O. So for the time being, just remember that an amphiprotic species is a species that can act as either an acid or a base. But anyway, storage, let's go ahead and take a look at the following concept. Different acids and different bases have different strength and so on. That is our next aspect. That is what I want us to touch on. So we'll talk about strength of weak and strong acids, dilute and concentrated solutions, and Ka and Kb values. Ka and Kb values derived from Kc, right? Chemical equilibrium. And then acid-base reactions and neutralization reactions. Right, so let's go ahead and take a look at it. A weak acid or base is one where only a small percentage of molecules will dissociate to form ions in a solution. A weak acid or a base is one where a small percentage of molecules will dissociate to form ions in a solution. Right, so weak acids ionize incompletely in water to form a low concentration of H3O+, while weak bases dissociate or ionize incompletely to form a low concentration of OH-. So if a base or an acid produces a low concentration of H3O+ or OH-, then it is considered weak. An example of a weak acid is hydrofluoric acid, HF, of which when it ionizes, it produces a low concentration of H3O+. We can see that denoted by the arrow here, that in the forward reaction, not much products are formed. Right, it produces a low concentration of H3O+. An example of a weak base is magnesium hydroxide, which only dissociates partially into Mg2+ and OH ions. Let's talk about this Ka value and Kb value that is derived from chemical equilibrium. So Ka will always take the products if they are aqueous or gases, no liquids or solids. So Ka in this case will be H3O+, and then multiplied by the concentration of F-, everything divided by the concentration of HF. Obviously, we're not going to include H2O because it is a liquid. In these expressions, we only consider gases and aqueous solutions. So let's take a look. Ka. So we're saying that this is a weak acid. So the Ka value, we expect it to be less than 1 in weak acids. So in weak acids, the Ka value is less than 1. For HCl, for instance, which we know to be a strong acid, the Ka value would be greater than 1. Why will the Ka value be greater than 1? Because our denominator will be greater than our numerator because it produces a higher concentration of H3O+, right? Here we have Ka being less than 1 because it is a weak acid. We're gonna have a proper fraction. If we have a proper fraction, it is a weak acid. But then if we have an improper fraction, then it is a strong acid. Our Ka value will be greater than 1. So this is for strong acids, right? And then we can also derive almost the same from bases. We have what we call the Kb value for bases. So it is the ionization or dissociation constant, of which still the same thing applies. If Kb is less than 1, then we have a weak base. And then if Kb is greater than 1, then we have a strong base, not a weak, but a strong base. We have a strong base, right? And then whether it is greater than 1 or less than 1, it is going to be decided by the concentration of OH-. Right, so this is weak and strong bases.
if you have a strong acid and you want to use it, most of the time you have to dilute it first just to weaken it a bit, because it is too corrosive to use in its original state. So let's touch on diluted and concentrated. It is clearly depicted in this picture. Take a look at concentrated and take a look at dilute. When you take a look at dilute, you can see that we have a few molecules of whatever substance we have there, and then in concentrated, well, it is concentrated. Let's take a look at the definitions. A concentrated solution is one where there is a high ratio of dissolved substance, right, solute to solvent. And then dilute solution is one where there is a low ratio of dissolved substance to solvent, right? So that is concentrated and dilute. This is what we are essentially saying. An acid is strong if there is a high percentage of ions formed in the solution, and a base is strong if there is a high percentage of ions in the solution. An acid is going to be H plus and the base is going to be OH minus. And then a weak acid, only a small percentage of ions are formed in the solution, while a weak base is the same, right? Just different ions. In acid, we know that it is H plus, and then in bases, it is OH minus. Now let's talk about concentrated and dilute. Concentrated, large number of molecules of acid in a solution, while dilute, we have a small number of molecules in a solution. And then the base, well, quite the same, large number of molecules in a base solution, and then a small number of molecules of base in the solution. That is dilute. So we have talked about the strength, and we've talked about concentrated and dilute. What we're about to touch on now is what acids and bases is all about. You'll come across a question in the exam, 8 marks, 9 marks, in some cases even 10 marks, requiring all the things we are about to talk about now. So when an acid and a base react, they form a salt. There's something cool that we're going to talk about with regards to that. If the base contains hydroxide ions, then water will also be formed. The word salt is just a general term which applies to the products of all acids and base reactions. A salt is a product that is made up of the cation from a base and an anion from an acid. Cation, just positive ion, and anion is a negative ion. Right. A salt is a neutral ionic compound composed of cations and anions. It is the result of acid-base neutralization reaction. Right, so we know that when you have an acid and a base, one of the products that you're going to have is salt, right? Stories. And then when an equivalent amount of acid and base react, so that neither the acid nor the base are in excess, the reaction is said to have reached the equivalence point. At this point, neutralization has been achieved. So if we have equal amounts of acids and base, and then they react completely, and there's no base or acid in excess, we say that we have reached a equivalent point, right? And then that is where we can say neutralization has been achieved, right? Just to touch on this, if you have ulcers, your stomach produces too much acid, and the medication you take is just a base that goes and neutralizes that acid, and then you're just left with salt in your stomach and not the acid anymore. So these acid-base reactions, they're very key to a lot of medication that you take, to a lot of household uses. Right. And then equivalence point, let's take a look at the technical definition. When a stoichiometrically equivalent number of moles of both reactants has been added to the reaction. If the base contains hydroxide ions, then water will also be formed. Right? You've seen from the reactions we have covered up to so far that most of the time water is one of the products, or is one of the reactants. And there is something profound about H2O that I want us to take a look at. Take a look at this reaction between
H2O and H2O. We literally have H2O plus H2O. So what's going to happen? One H2O will act as an acid and the other one will act as a base. And then consequently, we have H3O plus and OH minus. Right. H2O plus H2O to give us H3O plus OH minus. This is what we call autoprotolysis. It's the transfer of a proton between two of the same molecules. Right, we have a transfer of a proton here between H2 and H2O essentially. But what is the consequence of this? It leads us to the autoionization of water. Well, this is what we're talking about here. It's the reaction of water with itself to form H3O plus ions and OH minus ions. What is the equilibrium constant for the autoionization of water, or what we refer to as Kw? Oh, well, clearly you can see that it is equals to H3O plus multiplied by OH minus, right? These are our products. And then for the reactants, we're not going to have anything because we have H2O and H2O, which are in liquid phase. And like I've said, we only consider aqueous solutions and gases, right? There's quite a difference between liquid and aqueous, which a lot of people don't realize, right? So H3O plus multiplied by OH minus, this gives us 1 times 10 to the minus 14, right? This is the equilibrium constant for the autoionization of water. This right here is very consequential. We're going to use this time after time. We are going to derive a lot of things from this concept. H3O plus multiplied by OH minus, it's 1 times 10 to the power minus 14. Well, from this, we can actually get to showing that pH is equals to 14 from this. This is where a lot of things stem from, right? You'll see that in a few. But for the time being, let's take a look at how we can use that to calculate ion concentration, right? Although you normally ignore the autoionization of water in calculating the H3O plus concentration in a solution of the strong acid, the autoionization equilibrium still exists, and it is responsible for a small concentration of OH minus ion, right? Let's take a look at example. Calculate the concentration on OH minus ion in 0.1 mole per decimeter cube. Well, you can see that this question doesn't make much sense. I think there's a typing error here. So let's take a look at example 2 instead. The concentration of a solution of NaOH, a strong base, is 0.01 mole per decimeter cube. Calculate the OH minus and H3O plus concentration in this reaction. Okay, let's go ahead and take a look at that. So we have NaOH, and we're supposed to calculate the concentration of OH minus and H3O plus. So how can we possibly do that? We know that NaOH associates or dissociates to form Na plus OH minus. We know this to be true, right? So NaOH minus and OH minus, well, they are in the same, they have the same volume, right? Because we are getting this OH minus from the NaOH, right? They're not reacting with anything else that would increase or decrease the volume. Even if that was the case, they would still be in the same container, so to say. So the volume would be the same. So the volume is the same, right? Is the number of moles, are the number of moles going to be the same? Well, the balancing coefficient of NaOH and OH minus is 1. So the number of moles are going to be the same also, right? So the volume is the same, the number of moles are the same, right? So are the concentrations going to be the same? Yes, they should be, because concentration is just number of moles divided by the volume. So what is the concentration of NaOH? The concentration of NaOH is 0.01 moles per decimeter cube. So the concentration of OH minus should also be equals to 0.01 moles per decimeter cube. Right, so we have the concentration of OH minus, but using this concentration of OH minus, can we find the concentration of H3O plus using the concentration of OH minus? Yes, we can, using the auto ionization of water. That's why I was saying that that concept is very consequential in what we are going to be doing. Take a look at this. So OH minus multiplied by H3O plus, we had said that this is equals to 1 times 10 to the minus 14. Well, it should be easy to see what we are going to do here. The concentration of H3O plus is going to be equals to 1 times 10 to the minus 14 divided by the concentration of OH minus, which is 0.01. Well, do I need to put that in my calculator, or I can just do it in my head? I think I can. So H3O plus is going to be equals to, let's take a look, 1 times 10 to the minus 12 moles per decimeter cube. Well, let me just verify that. So we have 1 times 10 to the minus 14 divided by 0.01. Right, I think we are good to go. So that is how you can calculate the concentration of H3O plus if you have the concentration of OH minus. This is not something that is optional. You are going to use this at some point of time. There is no way you're not going to use it. So yeah, it is better if you familiarize yourself with this concept. So right, I've said that the auto-ionization of water is what leads to the pH value, well, the max on the pH scale being 14. So let's go ahead and take a look at pH scale. Right. A secondary way of expressing hydrogen ion concentration, avoiding using very small number of exponential notation, is the pH scale. So right, the pH scale is just there to express the concentration of hydronium ion without using smaller number. Right, pH is used to measure the concentration of H plus and therefore whether a substance is acidic or basic. Solutions with the pH less than 7 are acidic, while those with the pH greater than 7 are basic. The pH scale ranges from 0 to 14, and a pH of 7 is considered neutral. See the figure below. Well, there's no figure to see here, but yeah, that's the pH. We are ranging from 0 to 14. Less than 7, it's an acid, and greater than that is a base. Nothing new there. We've been talking about that since grade 9. pH is used to measure the concentration of H plus, but in such a way that doesn't include using very small numbers. Right, so pH, the formula for pH is equals to minus log of H plus. Right, you can see here that the only input we have is the concentration of H plus. So the only thing that is affecting the value of pH is H plus and nothing more. And then this log here is what ensures that we don't have very smaller numbers, because if we just said pH is equal to H plus, we would still have consistency, right? We would still have consistency. We wouldn't have any issue per se, but then we use log so that those small concentrations can be presented or represented in digestible numbers, right? We don't have to use 1 times 10 to the minus 12, because think about what 1 times 10 to the minus 12 means. It means 0.00011 zeros until 1. That is very strenuous. So instead of doing that, we introduce log, right? And then we get numbers from 0 to 14, and that is easy to work with. So pH is equals to minus log of H plus. But pH is not the only thing that we talk about here. We also talk about pOH. So this is how we measure the concentration of OH minus the 4. So POH, as you've guessed, will be minus log of OH minus. So this is pH and this is POH. Remember that we said H plus multiplied by OH minus is equals to 1 times 10 to the minus 14. Okay, let's introduce log on both sides. I want to show you something very cool. So if we were to introduce log on both sides, we would have log of H plus multiplied by OH minus, right? We can, if what to do on the left, we must also do it on the right. So here we're going to have log of 1 times 10 to the minus 14, right? But log of A multiplied by B is equals to log of A plus log of B. That is a log law, right? So what are we saying? We're saying that we're going to have log of H plus log of OH minus. We have applied a log law there. And then log of A to the power B is equals to B log of A. So A, well, let me not use B. B in our case is minus 14. We're going to have minus 14 log of 10, right? But we know that log of 10 is 1. So let's just replace this with 1. 1 times minus 14 is just going to give us minus 14. If we divide both sides by minus 1, we're going to get, if we divide both sides by minus 1, we're going to get minus log of H plus minus log of OH minus being equals to 14. But what is minus log of H plus? This is pH. And then minus log of OH minus, this is POH, and all of this is equals to 14. So there we go. pH plus POH is equals to 14. We are also going to use this concept at some point of time. Okay, let's solve some problems. Calculate the pH of a solution where the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube. So what is hydronium ions? Hydronium ions is H3O plus, and I've said that in place of H plus we can always use OH, not OH but H3O plus, right? So if you're given the concentration of H3O plus, you just treat it as H plus, right? So here we're supposed to calculate the pH. There isn't much to do, it's just direct substitution really. So we're gonna have pH being equals to minus log of H3O plus, right? We can use H3O plus and H plus interchangeably. This is going to be equals to minus log of 1 times 10 to the minus 3, right? So let me just go ahead and put that in my calculator. So minus log of 1 times 10 to the minus 3 is equals to 3. So the pH in this case would be equals to 3. If the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube, well, the pH is equals to 3. It's easy to see that the POH should be equals to 11, because the pH and the POH, if you say pH plus POH, you get 14. So if pH is 3, then POH should be 11. We can easily prove that, but you know, stories. I'm sure we're gonna have a question where we're gonna have to do that as time goes. Example 4: in a 162 centimeter cube solution of ethanoic acid, the following equilibrium is established. We are given an equation here, and then the question says the number of moles of CH3COO minus is found to be 0.001 moles. Calculate the pH of the solution.
So we've been given the number of moles of CH3COO minus, and it has been given as 0.001 mole. So the balancing coefficient of CH3COO minus is the same as the balancing coefficient of H3O plus. And the balancing coefficient of H3O plus is the same as that of ethanoic acid. So the number of moles of H3O plus and the number of moles of ethanoic acid is equal. We've been given the volume of the ethanoic acid as 162 centimeter cubed. But using the formula of C equals to N over V, the volume of ethanoic acid should be in decimeter cubed, not centimeter cube. To convert centimeter cube into decimeter cube, we will have to divide 162 by 1000, which will give us 0.162. Therefore, the volume of H3O plus will be 0.162 decimeter cubed. So, to calculate the concentration of this H3O plus, we will have to divide the number of moles, which is 0.001, by the volume, which is 0.162. And that will give us 0.006. 0.006 moles per decimeter cubed. So the formula of pH is equals to negative log of H3O plus, which can also be H plus. pH will be equal to negative log of 0.006, which will give us 2.22.
It is as if every time we touch a different aspect, I keep on saying, oh, this is very important, we're going to use it at some point of time. And I just have to say it again, titrations of acids and bases. This is very key. We are going to use this time after time. I think you're even going to do a practical on this, acid and base reactions. Or you should do it at some point of time in your high school years, either grade 11 or 12. But yeah, it's very rare that you're going to finish high school without doing titrations. Yeah, this is very important. So let's take a look and see what is really happening here. The neutralization reaction between an acid and a base can be very useful, as we have talked about previously. If an acidic solution of known concentration is added to a basic solution of unknown concentration until the solution is exactly neutralized, it is possible to calculate the exact concentration of the unknown solution. Right, so that is what titration is all about. We are using the concentration and volume of a known substance to calculate the concentration and volume of the unknown. Right, titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. This process involves the gradual neutralization reaction of an acid by a base, or of a base by an acid. Right, so if you're given an acid with known properties, you can find the properties of an unknown base. And then if you're given the properties of a base, then you can find the properties of an acid that are unknown at that point using this reaction. Right, titration is a method used to determine the concentration of a known substance using another standard solution. So what is a standard solution? A standard solution is a solution of known concentration. Okay, the titration of an acid in a aqueous solution with a base is illustrated in the series of photographs below. Right, the titration of an acid in a aqueous solution with a base. Okay, so let's take a look at this. It is a titration of an acid with a base. Okay, so here in our beaker, we have our acid, right? And then here in our burette, we have our base, right?
So we don't know the properties of this acid, right? But we know the properties of a base. So what are we gonna do? We keep pouring a bit of base in our acid, just a bit, right? We have an indicator here in our acid. We have put an indicator inside it. And then when the color of the indicator changes, well, different indicators change color when the reaction has reached an equivalence point. So when the color of the indicator changes, we know that we have stoichiometrically equal number of moles of acid and a base. We know that neutralization has occurred. So because we know the amount of acid that we have poured in, we can then determine the amount of acid that should have been in the beaker to begin with. That is what titration helps us with, right? So we have an acid of unknown properties, and we keep pouring a small amount of base until the indicator changes color. When the indicator changes color, we know that neutralization has been reached. We are at the end of our reaction now, and using that information we have with regards to the base, we can then determine the properties of an acid. So this is essentially what titration is all about. But which indicator do we use and when do we use it? Because we have a couple of indicators. Let's talk about that. An indicator is used to determine the endpoint of neutralization. Okay, let's go ahead and take a look. We have three indicators: methyl orange, bromothiamyl blue, and phenolphthalein. Alright, those are our three indicators. So if you're expecting your endpoint, the endpoint of neutralization, to be reached when the pH is between 3 and 4.4, then you use methyl orange. And then if you expect your reaction, the point of neutralization to be reached when the pH is around 7, you use bromothiamyl blue. And then if you expect your pH to be around 8, around 10, when the point of neutralization has been reached, then you use phenolphthalein. So how do you know that the pH at which the endpoint of the neutralization is going to be reached is going to be around 3, and you use methyl orange, around 7 and you use bromothiamyl blue, around 8 and then you use phenolphthalein? How do you know all that? If we have a strong base and a strong acid, then we would expect the pH to be around 7 at the end of our neutralization reaction. In this case, we would then use bromothiamyl blue. And then if we have a weak acid and a strong base, you expect the pH to be greater than 7, around 8, around 9, around 10, even around 11. And then the suitable indicator in this case would be phenolphthalein. And then if you have a strong acid and a weak base, you expect the pH to be less than 7, right? And then in this case, we would use methyl orange. So there we go. This is how you can have an idea of which indicator you need to use based on the strength of the acid and the base you have at hand. Let's solve some problems. So what we have in front of us is acids and base topic test. So I will do the test myself. That will be the first try. And after doing the test myself, then you are gonna do the test. You can ask questions, I can help you out and so on. But I want to do the test first myself. So let's go ahead and take a look at it. If I'm doing something and then you don't understand where it is coming from, then you can ask me. Right. So question 1. We usually don't read these instructions. We just know what to do, but let's take a look and see what is happening. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question numbered 1 to 1.1 to 1.5 in the answer book, right? And then, for example, we have 6 with an answer being E, right? 1.1, consider the following chemical reaction. Let's take a look at that chemical reaction. Which one of the following correctly identifies the order of Florey-Bronsted acids and bases in the above reaction? Okay, so let's take a look at that. What do we have? We have H HCO3 minus plus HC2O4 minus, giving us and getting H2CO3 plus C2O4 to the 2 minus. So let's go ahead and dissect this. Okay, so we start with HCO3 to the minus. So if this is an acid, in the product side we must get CO3 2 minus. It would have donated a proton and we would therefore refer to it as an acid. That is if and only if it is an acid, right? So let's go and check and see if that is actually the case. So let's take a look. We start with, let me just erase this. We start with HCO3 minus, and then we end up with H2CO3. So it is not an acid because it is not donating a proton. It actually looks like it has accepted a proton. It was HCO3 minus, now it is H2CO3. Right, so clearly it has accepted a proton. So if it is a proton acceptor, then this is our base because it has accepted a proton, and then this is going to be a conjugate acid, right? That is going to be a conjugate acid. And in doing that, I think we have for the most part answered our question, because if that is the base, then this is the acid where we are getting the proton from, and then this is going to be the conjugate base. So there we go. Our order, we have base, acid, acid, base. So let's go ahead and look at our question and see which option is that. So okay, B and C, well, B and D starts with a base, followed by an acid, right? It's still true in both B and D. And then the third, what fills the third spot is acid, right? So that is option B. So option B seems to be the correct answer here. We have base, acid, acid, base. So there we go. You essentially, for the most part, you just need to identify one acid. As soon as you identify one acid, everything else, it's easy to figure out, because if you have an acid, then it's the reaction with the base, and then the conjugate acid and the conjugate base. But anyway, stories, that is 1.1. So for 1.1, the answer is B. What about 1.2? Let's go ahead and take a look at that. Which of the following species cannot act as a Bronsted-Lowry acid and cannot, right? Cannot. I was thinking can, right? Cannot act as a Bronsted-Lowry acid and as a Bronsted-Lowry base. So we are looking for a species which is not an amphilite, amphiprotic. We are looking for a species which cannot act as a base and act as an acid. We know H2O. We know fully well that H2O is an amphilite. It can act as both an acid and a base. So option B cannot be our answer, because we are looking for a species which cannot. And then HSO4 minus can act as both an acid and a base. Well, let me show you how it can act as an acid. So let's say we have HSO4 minus plus H2O. This can give us SO4 2 minus plus H3O plus. As you can clearly see here, it is acting as an acid because it donates a proton. But H2SO4 plus H2O gives you HSO4 minus plus H3O plus. Clearly here we have H2SO4 as our acid and HSO4 minus as our conjugate base. So in the first reaction it is acting as an acid, and then in the second reaction it is acting as a base. So clearly this is an amphilite. It cannot be our answer to 1.2. It acts as both an acid and a base. And we can do the same for D, right? D will also act as an acid and as a base. That is if we are really sticking to the basics. But we know that A is ethanoic acid. A is ethanoic acid. It is an acid. It doesn't act as a base. A is ethanoic acid. So the answer here in 1.2 is A, right? Whether you are getting to that answer because you know fully well that A is an ethanoic acid, or you just use this concept, you just dissolve the compound in water and see what you end up with, right? So that is 1.2. 1.3, the compound which will react with sodium hydroxide in a neutralization reaction is. So right, a neutralization reaction is a reaction between an acid and a base. So essentially, what the question is asking us here is, between A, B, C, and D, which one is an acid? Because if we have a base and an acid, we have a neutralization reaction. So take a look at this. We have NaOH as our base, that is sodium hydroxide. And then option A is KOH. KOH is potassium hydroxide. This is also another strong base. So we cannot have base plus base and call that neutralization. No, we need a base and an acid. So this can't be our answer. And then we have CaCO3. This is the compound you find in shells, right? And then it is basic. CaCO3 is basic. So CaCO3 and NaOH, they also can't form a neutralization reaction because they are two bases, right? So B cannot be our answer. And then C2O4 to the 2 minus. This is not a very usual compound, well, ion in this case, that we come across. So maybe this one can be a bit confusing. But if we just take a look at question 1.1, because we're not sure whether C2O4 to the 2 minus is an acid or base, right? Let's say it's not easy to see, but we can actually use 1.1 and see that C2O4 to the 2 minus is a base, as you can clearly see here. When we were identifying our conjugate acid base pair, we say that C2O4 to the 2 minus is a base. So this cannot be a neutralization reaction between a base and a base. 1.3, we have ethanoic acid. So this is our answer. The answer to question 1.3 is A. Not A, but D. It's D. It is ethanoic acid because we have a base in NaOH and then we have an acid in CH3COOH. So clearly, this is going to be a neutralization reaction because it is a reaction between an acid and a base. Right, that is 1.3. Let's take a look at 1.4. 1.4, when sulfuric acid reacts with water, it ionizes in 2 steps as shown in the 2 balance equations below. Well, there's a special term we use for acids that ionizes in 2 or 3 steps, right? So sulfuric acid, it says H2, so it is diprotic. It can donate 2 protons. In reaction 1, it donates the first proton, and then in reaction 2, it donates the second protons. While HCl is monoprotic because it can only donate 1 proton, right? So that is another concept that we brushed over when we were touching on the basics. So right, back to the question. 2 steps of which sulfuric acid ionizes. And then what is the question saying? The species are represented by letters Q and R. Okay, let's take a look. So reaction 1, we have H2SO4 plus H2O to give us H3O plus what we are referring to as Q. Well, let's put it here, what we are referring to as Q. So how can we possibly identify Q? We know that there is no element that is just going to disappear in our reaction. Everything needs to be accounted for. So take a look at this. We start with H2O. Now we have H3O plus. So clearly H2O has gained a proton. But where is the proton coming from? It's coming from H2SO4. There is no other species. That should be easy to deduce that the proton is coming from H2SO4. But when H2SO4 donates the proton, what are we going to be left with? We're going to be left with 1 proton, 1 hydrogen, right? And then SO4 minus because we have donated 1 proton, and then here it is plus because it has accepted 1 proton. So we know that Q is HSO4 minus, right? So at this point we know that A cannot be our answer because it says Q is SO4 to the 2 minus, and then we know that, let's take a look, HSO4 minus, we know that D cannot be our answer because D says that Q is HSO4 to the 2 minus, and Q is clearly HSO4 to the minus 1, not to the 2 minus, right? So we have figured out what Q is. Let's go ahead and do the same for R. So for R, we're starting with Q. What is Q? Q is HSO4 minus. There we go. And then plus H2O. And then what is the product? The product is H3O plus R. Okay, so let's take a look. Back to the basics again. We will start with H2O. Now we have H3O plus. It has accepted a proton. Where is the proton coming from? The proton is coming from HSO4 minus. So when it donates another proton, and well, let me not say another proton because now we are in a different reaction here. When it donates a proton, we're gonna be left with SO4 2 minus. So this is Q and this is R. The answer to 1.4 is C, and let's do 1.5. Right. So 1.5. Let's take a look at what's happening here. Consider the incomplete chemical equation below. There we go. Looks a bit complicated, but there ain't nothing to it but to do it. Which one of the following is represented by X in the above equation? So I think here we're just following the same technique we've been trying to, well, we've been using to answer 1.4 and 1.5 and 1.1. So let's take a look. We have some X plus 2HNO3 to give us CaOH2 or OH, no, NO3, right? NO3 2 plus H2O plus CO2, right? I think this is quite easy. It is easier than it looks because we can just use brute force here. Let me show you what I'm talking about. So okay, the hydrogens, let me just change my color. So we have 2 hydrogens on the left, on the right we have 2 hydrogens. Okay, all is well there. Okay, let's do nitrogen. In nitrogen we have 2 atoms of nitrogen, right? And then in the right, that's on the left hand side, and then on the right hand side the same is true. We have N2. So there's no issues with regards to nitrogen. They are balanced. What we have on the left is what we have on the right. And then oxygen, we have 2 multiplied by O3. So this is O6 on the left. And then on the right hand side we have O3 multiplied by 2. This is O6. And then this oxygen from H2O, which will make that O7. And then on CO2 we have 2 oxygen atoms, so this will give us a total of O9. So we can see that issues are arising at this point. 6 oxygens on the left, 9 on the right. So we know that in X, some way somehow we need to have an oxygen, right? We know that for sure. We're just following the basics. What's on the left must be on the right. Okay, so that is with regards to oxygen. And then when we move to the right hand side, we have calcium on the right hand side, and then on the left hand side we have no calcium. So we know that at least we need Ca as part of X, some way somehow, right? We don't know how it will look like, but we know that we at least need calcium on the left, right? So that is Ca. And what else do we have? I think we've covered hydrogen and all is well. We need carbon. On the right hand side we have a carbon, and then on the left we don't have a carbon. So it is easy to see that we also need a carbon on the left hand side. So we have calcium
we have oxygen, and we have carbon. Okay, how many carbons, how many calciums do we have on the right? We have 1. How many oxygen do we have? Well, let's start with carbon. How many carbons do we have on the right? We have 1. How many do we need on the left? We need 1, obviously. And then let's come to oxygen. On the right, we have 9 oxygens. And then on the left, we have 6. The difference is 3. So here we need 3 oxygen. So on the left, in place of X, we have CaCO3. So the answer to 1.5 is D. We are using brute force here. Even if you don't have an idea of what chemistry is all about, even if you just look at the mathematical, if you just solve this problem basing it on math, we should end up with CaCO3. So the answer to 1.5 is D. Let's do question 2. So question 2, consider the following acid-base reaction. And then 2.1.1, define an acid in terms of the Lorentz-Bronsted theory. Also, the Lorentz-Bronsted theory is the easy one. So an acid is a proton donor, right? So proton donor, and then we have 2 marks. Yeah, 1 mark for 1 word. Okay, that is 2.1.1. Then 2.1.2, write down the formula of the 2 acids in the above reaction. Well, we are back to acids base conjugate pairs. Let's go ahead and do that one more time. HCO3 minus plus NH3 to give us CO3 2 minus plus NH4 plus. Right, so we have done 2.1.1. We've already defined what an acid is according to the Lorentz-Bronsted theory. Now we need to write down the formula of 2 acids in the above reaction. Okay, so let's take a look. HCO3 minus. It doesn't really matter what you start with. You can start with anything, really. Let's start with NH3. Right, so NH3. If it is an acid, we should have NH2 minus. It has donated a proton. And then if it is a base, we should have NH4 plus. It has accepted a proton. So let's take a look. We have NH3, and then we end up with NH4 plus. So clearly NH3 accepts a proton. If it accepts a proton, it is a base. So this is a base, right? And then we are done essentially. If that is the base, this is its conjugate acid. This is gonna be a base, and then this is the conjugate acid. So the formula of 2 acids in the above reaction. Well, HCO3 minus. It donates a proton to become CO3 to the 2 minus. Which other acid do we have? We have NH4 plus. It is a conjugate acid to the base NH3. So the answer to 2.1.2, HCO3 minus and NH4 plus. Right. 2.1.3, define the term ampholyte. Well, an ampholyte is a substance that can act as an acid and as a base. Right, it can act as both an acid and a base. So that is 2.1.3. 2.1.4. Right. Write down the name, write down the formula of an ampholyte in the above reaction. Write down the name, write down the formula of the ampholyte in the above reaction. So let's go ahead and take a look and see what is happening. So what is our ampholyte? Let's take a look at the reaction that we have. Let me just change my color here. I'm just giving myself some time to think here in changing the color. Right. So we have HCO3. Let's start here. We have HCO3 and NH3. Right. NH3 is a base. And then NH4 plus, it is an acid. We don't have such thing as NH2 minus. We don't have such a thing. So NH2 minus, it does not exist. This is not a thing we have in chemistry. So we know that NH3 cannot act as an acid. it cannot donate and become NH2 minus. So this is out of the way. This is out of the way. We know that this cannot be true. And then CO3 2 minus, that is our base. Well, it cannot donate a proton to become CO3 to the 3 minus because it doesn't have a proton. So this cannot be an amphylide, right? It is acting as a base in this case. Can it donate a proton? No, it cannot because it doesn't have a proton. And then on the other hand, acid NH4 to NH4 plus. Okay, if it is acting as a base, it needs to then become NH5 to the 2 plus, and this is technically impossible. How can you show that is technically impossible, or how can we reach to that conclusion? Try drawing a Lewis structure diagram for NH to the NH5 to the 2 plus and see what you end up with. This is technically impossible, right? So we know that NH4 plus cannot act as a base. HCO3 minus, it is an acid, but it can also act as a base. How can it act as a base? Okay, take a look at this. H2CO3 plus H2O. This can give us H3O plus HCO3 minus. No issues arise whatsoever. So you can see that this is the acid and then this is the conjugate base, right? So in this case, it is acting as a base, but in our reaction, it is acting as an acid. So it can act as both an acid and a base. So 2.1.4, the answer is HCO3 minus. It can act as both an acid and a base, clearly. And then 2.1.5, write down a balanced chemical equation to show how the amphylide named in question 2.1.4 above reacts with water, in which water acts as an acid. Okay, let's see. HCO3 minus plus H2O. We are saying that we need water to act as an acid. So water needs to donate the proton, and HCO3 minus needs to therefore accept the proton. Okay, so we would have H2CO3 plus OH minus. Okay, let's take a look at this and see if all is well. Write down a balanced equation to show how the amphylide named in question 2.1.5 above reacts with water, in which water acts as an acid. If water acts as an acid, it shall donate a proton, and HCO3 minus should accept. When HCO3 minus accepts, it becomes H2CO3. Okay, that is well. And then if H2O donates a proton, it acts as an acid, then it will become OH minus. That is also perfectly fine. So that is the answer to 2.1.5. Okay, let's move to 2.2 and hear the stories. So in 2.2, CO3 to the 2 minus in the above reaction is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid according to the following balance equation. Okay, write down a reason why Cl minus is referred to as a base. Write down a reason why Cl minus is referred to as a base. So take a look at this. We start with HCl, which is hydrochloric acid. It donates a proton, and we are left with Cl minus, right? When we define a conjugate acid or a conjugate base, we say that it is the ion, it is the space that is left after an acid has donated a proton or after a base has accepted a proton. Okay, so Cl minus is what is left after an acid has donated a proton. It is a conjugate base, so that is why we refer to it as a base. It is what is left after an acid has donated a proton. Okay, that is 2.2.1. Then 2.2.2, calculate the number of moles of hydrochloric acid reacted. That is for 3 marks. Let's take a look and see what is happening here. So it is reacted with CO3 to the 2 minus is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid. So we have the volume, we have the concentration, we are looking for the number of moles. We are really sticking to the basics here. Concentration is equals to the number of moles divided by the volume. So what is the concentration? 0.2. And then the number of moles is what we're interested in. And then the volume is 20 centimeter cube. We can just multiply it by 10 to the minus 3 and we have converted it to decimeter cube. Right. So let's cross multiply. Number of moles is equals to 0.2 multiplied by 20 times 10 to the minus 3. So 0.2 multiplied by 20 times 10 to the minus 3, 0.004 moles. So there we go. That is the answer to 2.2.2. There's something really complicated here. Let's do question 3 and see what is going on. So question 3, two acid-base reactions are shown in the chemical equation below. Okay, and then 3.1.1, define a base according to Arrhenius theory. Arrhenius theory is the difficult one of the two, and then a base is a substance that ionizes or dissociates in water to produce hydroxide ions, right? It is a substance that ionizes or dissociates in water to produce hydroxide ions. So that is 3.1.1. What about 3.1.2? I'm glad you asked. Write down the formula of a conjugate acid of OH minus in reaction 1. Conjugate acid of OH minus in reaction 1. So in coming to the conclusion that Cl minus is a base, well, the reason we say that Cl minus is a base, it is because it is the space that is left after an acid has donated a proton. It is therefore a conjugate base. So here, a conjugate acid of OH minus in reaction 1. Okay, so let's take a look. NH3 becomes NH4 plus. It accepts a proton. And then H2O becomes OH minus. It donates a proton. So a conjugate acid to OH minus is H2O. That OH minus is there because H2O has donated a proton. So that which donates, we know fully well that it is an acid. And then the OH minus, it's a base because it's what is left after an acid has donated a proton. So a conjugated base to OH minus in reaction 1 is H2O. That is 3.1.2, not 3.1.1. That is 3.1.2 H2O. Right. And then now 3.1.3, write down the formula of a conjugate base of HPO4 to the 2 minus in reaction 2. I don't think these questions are difficult per se. I think we are really sticking to the basics here. So let's take a look at conjugate base to HPO4 to the 2 minus. So we have HPO4 to the 2 minus reacting with H2O. H2O accepts a proton. So from H2O to H3O plus, it has clearly accepted a proton. And then HPO4 to the 2 minus donates a proton to become PO4 to the 3 minus. So what can we say about that? PO4 to 3 minus is the conjugate base of HPO4 to the 2 minus because it is what is left after the acid has donated a proton, like we are emphasizing. So the answer to 3.1.3, PO4 to the 3 minus. And why is that so? It is what is left after an acid has donated a proton. Okay, the question that follows. Methyl orange indicator is added to the mixture in reaction 1. Right. Methyl orange indicator is added to the mixture in reaction 1 above at the completion of the reaction. The color change of methyl orange indicator in acidic and basic solutions is shown in the table below. Color in acidic solution, it is red. So if the color turns red, then that solution is acidic. and then color in basic solution is yellow. So if the color turns yellow, then we know that the solution is basic. And then 3.1.4, define the term acid base indicator. Yeah, this is not a very common definition, but an acid base indicator, it is a weak acid or a weak base which color changes as the H plus ion concentration or the OH ion concentration in the solution changes. So a weak acid or a base that will change color if the concentration of H plus changes or if the concentration of OH minus changes. Right, so that is an acid base indicator. It changes color when the concentration of H plus changes or when the concentration of OH minus changes. That is suitable. That is a good definition because we need an acid base indicator to change color when a solution becomes acidic or if a solution becomes basic. So if it changes because the concentration of H plus has changed or because the concentration of OH minus is changed, then that is suitable because it is there for acidic or basic. You just need to know what the color change is going to be if it is acidic and what color change it is going to be when it is basic. That is 3.1.4. 3.1.5. What is the color? What is the color of the indicator in the reaction mixture? Give a reason for the answer. So the indicator is added in reaction 1. So let's zoom in reaction 1 and make sense of what is happening here. So, let me just erase this. So, reaction 1. Well, we know that H2O, if you have an acid, is going to act as a base. And then if you have a base, it is going to act as an acid. So take a look at this. We start with H2O and then we end up with OH minus. So is it acting as a base or is it acting as an acid? Clearly it is acting as an acid because it has donated a proton from H2O to OH minus. So H2O is an acid, right? And then we know that NH3 is a base, right? But then even if you were not aware of that, just looking at how H2O behaves, you should reach the same conclusion that NH3 is a base. So what is the pH of H2O, right? The pH of H2O is 7. So what is deciding whether the solution is acidic or basic is NH3, because we know that the pH of H2O is 7. So if you have a base, then the pH will be greater than 7. And then if you have an acid, the pH is going to be less than 7, and then then H2O will therefore act as a base in that case. So clearly here, because H2 is acting as an acid and we have NH3 as a base, then at the end of the reaction, our mixture is going to be basic. So what is the color of the indicator in the reaction mixture? It should turn yellow here because it is said that the color in basic solution is yellow. And we have H2O, which the pH is 7, NH3, of which the pH is greater than 7 because it is a base. So the answer to 3.1.5, we have yellow. Give a reason for the answer. Well, the reason is because the solution is going to be basic at the end, right? You can also see that by the presence of OH minus. OH minus is hydroxide ions. We know that hydroxide ions is what you get when a base ionizes or dissociates. You get OH minus, right? Okay, and then 3.2. Let's take a look. Let's see what is happening here. 3.2. Write down a balanced equation for the dissolution of ethanoic acid. Right. I'm not sure if this is the correct term where we're supposed to use dissociation, but okay. CH3COOH in water. Let's go ahead and take a look. So CH3COOH plus H2O. We know fully well that this is ethanoic acid. So because it is an acid, it should donate a proton. And then H2O must act as a base. It must accept that proton. So the products that we're going to have CH3COO minus plus H3O plus. The acid has donated a proton to become CH3COO minus, and then H2O, which is acting as a base in our case, has accepted a proton to become H3O plus. So that is ethanoic acid in water. It will produce hydronium ions. We expect an acid to produce hydronium ions when dissolved in water. That is 3.2. Question 4. Looks like things are starting to get a bit interesting here, but we are here for that. 4.1. The Bronsted-Lowry and Arrhenius theory are used to define acids and bases. We know that by now. And then 4.1.1. Define a base according to Bronsted-Lowry theory. Define a base according to Lowry-Bronsted theory. Lowry-Bronsted is the easy one. So base is a proton acceptor. Right, so that is 4.1.1. We shouldn't be getting that wrong. A base is a proton acceptor. Okay, 4.1.2. We're given a couple of reactions here, right? And then the question is saying the reaction that illustrates Arrhenius theory. Okay, between A, B, and C. So Arrhenius theory says that a substance that produces, it says that an acid will produce hydronium ions or hydrogen ions when dissolved in water, right? And then a base will produce hydroxide ions. So we are looking for that. Which equation produces hydronium ions, or which equation produces hydroxide ions? Let's take a look at equation A. In equation A, we don't have hydrogen ions, hydronium ions, or hydroxide ions. So that is not a good illustration of Arrhenius theory. Reaction B, same is true. We don't have a hydrogen ion, we don't have a hydroxide ions, we don't have a hydronium ions. Not a good illustration of the Arrhenius theory. But equation C, you can clearly see, well, not equation C, but reaction C, you can clearly see that there is hydrogen ion produced, there is H plus, when HCO4 minus ionizes. So the answer to 4.1.2 is C, because clearly an acid is producing hydrogen ions, and that is what Arrhenius theory says. It defines an acid as a substance that produces hydrogen ions when dissolved in water. Okay, 4.1.2. 4.1.3. A substance that can act as an ampholyte. A substance that can act as an ampholyte. From the reactions A, B, and C right down there, a substance that can act as an ampholyte. Do we have H2O as one of the reactions here? It's one of the reactions, because if I have H2O, I'm just jumping straight to H2O and then I call it a day. Okay, I do have H2O in reaction A. Well, in reaction A, it is just acting. It's a product there in reaction A. So let's see. Do we have any other equation with H2O? We don't have any other reaction with H2O. So whether it is acting as an acid or as a base in reaction 1 is not really gonna matter, because we don't have an opportunity to demonstrate that it is acting as the other in another reaction. Okay, but I'm realizing here that in reaction B we have HSO4 minus, and then in reaction C we also have HSO4 minus. Let's see if HSO4 minus acts as both an acid and a base in these reactions. So in reaction B, it accepts a proton to become H2SO4 minus. So if it accepts, then it is a base in reaction B. Okay, and then in reaction C, it donates to become SO4 minus. So it is an acid in reaction C, I meant. So it is acting as both an acid and a base. And then 4.1.3, the answer is therefore HSO4 minus, because clearly in B it is acting as a base, and then in C it is acting as an acid. Okay, and then 4.1.4, a conjugate acid base pair in reaction C. Okay, so reaction C, HSO4 minus is our acid. It donates it donates a proton to become HS. it donates a proton to become SO4 to the 2 minus. And then we know that a conjugate base, it's what's left after an acid donates a proton. So the pair HSO4 minus and SO4 2 minus. So there we go. That is 4.1.4. Okay, 4.2. Grade 11 learners uses 2 steps to react sodium carbonate with concentrated sulfuric acid. In step 1, they prepare 250 centimeter cube standard solution by dissolving 5.13 grams of Na2CO3 crystals in distilled water. They reacted the prepared Na2CO3 with H2SO4. Okay, right. The reaction occurs according to the following balanced equation. And then 4.2.1, define an acid according to Arrhenius theory. Right, we're getting tired of these definitions. I think we have defined an acid and a base as according to Arrhenius theories and Lorentz theories. In these questions collectively, we have defined everything, I think. So an acid is a substance that ionizes to produce hydrogen ions when dissolved in water. That is 4.2.1. So 4.2.2, calculate the concentration of Na2CO3 in the standard solution. Okay, right. Let's take a look at the information that we have, because physical sciences is just a matter of, you're given information, you have a principle, and you use the principle to find the unknown using the information that we have. So here, the concentration is our unknown. We're trying to figure out what the concentration is. And then what information do we have with regards to Na2CO3? Okay. We know that we have a mass of 5.13 grams that is dissolved in distilled water. So the mass is equals to 5.13 grams. And then the volume of the distilled water, right? Because we have some water here and we are adding Na2CO3. The volume of the water is 250 centimeter cube. Okay, so concentration is equals to number of moles divided by volume. So we have the volume, we don't have the number of moles, but we can find the number of moles using the mass, right? Number of moles is equals to the mass divided by the molar mass. Okay, so concentration is equals to, in place of number of moles, mass divided by molar, we divide everything by V. This is just equals to the mass divided by the molar mass multiplied by the volume. So we can just use this equation to find the concentration of Na2CO3. So what is the mass? The mass is 5.13. Okay, and then the molar mass is sodium is 23, so we have 23 multiplied by 2, and then carbon is 12, oxygen is 16. You multiply by 3, you multiply that by 3, and we get 106 multiplied by the volume, which will be 250 times 10 to the minus 3. We are converting it to decimeter cube by doing that. So 106 multiplied by 0.25. Right, let me see what I get there. I'm getting 0.2 moles per decimeter cube. That is the concentration of Na2CO3, 4.2.2. What about 4.2.3? We're looking for the number of moles of H2SO4 that reacted. The number of moles of H2SO4 that reacted. Okay, we're looking for the number of moles of H2SO4. We're looking for the number of moles of H2SO4. What can we use? We can use the number of moles of Na2CO3 and the balancing coefficients of the two. Because take a look at this. The number of moles of Na2CO3 is 2. The number of moles of H2SO4 should be 1:1 because of the balancing coefficient. So we just need to figure out what the number of moles of Na2CO3 is, and then we have the number of moles of H2SO for that reactant. Take a look at this. At this point, we have the concentration of Na2CO3, and we also have the volume. So finding the number of moles should not be that difficult. So the number of moles of H2SO4, we now know that it is equal to the number of moles of Na2CO3 will be equal to the concentration of Na2CO3 multiplied by the volume of Na2CO3, right? Okay, because we have established this relationship, we are then able to do this, right? So before you establish this relationship, you can't do this. So the concentration 0.2, the volume 250 divided by 1000. So let me just put that in my calculator and see what I get. I'm getting 0.05 moles.
So we have two beakers, A and B, containing strong bases. Beaker A has 500 centimeter cube of BaOH2 and then of unknown concentration, and then beaker B has 400 centimeter cube of potassium hydroxide KOH of concentration 0.1 mole per decimeter cube. And then 7.1 says define a base according to Arrhenius theory. A base, according to Arrhenius theory, ionizes to form hydroxide ions. So that's basically the definition of a base according to Arrhenius theory. A base ionizes to form hydroxide ions. And then 7.2 says calculate the number of moles of hydroxide ions in beaker B. So what makes that beaker B? In beaker B, we are told that in beaker B we have KOH, right? And then when this ionizes, it will give you K plus OH minus, right? We are given information about KOH. So from the information we have about KOH, we'll then be able to find the number of moles of OH. So let's go ahead and do that. So we are told that the concentration is equal to 0.1 moles per decimeter cube. And then at the volume, it is given as 400 centimeter cube, which we have to convert to decimeter cube, right? We divide by 1000, so we're gonna get 0.4 decimeter cube. Now we can find the moles of KOH and then use that to find the moles of OH using the balancing coefficients. So we're gonna get N of KOH is equals to C multiplied by V, right? We're saying that because we know that the concentration is equal to the number of moles divided by the volume. So we're using that formula. So N of KOH will be equal to, what is the concentration? 0.1 mole per decimeter cube. And what's the volume? 0.4 decimeter cube. This will give us 0.04 moles, right? And then now we can use this number of moles of KOH to determine the number of moles of OH minus, right? So we're gonna say the number of moles of KOH divided by the number of moles of OH minus is equals to 1 divided by 1, because that's the balancing coefficients. So basically the number of moles of OH minus is just equals to the number of moles of KOH, which is equals to 0.04 moles. And that's how you do 7.2. And then moving ahead, we have 7.3, which says the contents of beakers A and B are added together in beaker C. The solution is in beaker C has a pH of 13. So we have pH equals 13. And then from pH, before we go any further, we can determine the pOH, right? Because we know that pH plus pOH equals to 14. So that will say pOH equals to 14 minus 13. So pOH is equals to 1. Okay, let's move forward. So it goes on to say that assume that the volumes are additive and that the temperature of the solution is 25 degrees Celsius. And then 7.3.1 says calculate the concentration X of the BaOH2 in beaker A. So what is happening? Beaker A is being poured to beaker C, right? And then beaker B is being poured to beaker C. So beaker A has its own number of moles of OH, right? That will be poured to beaker C. And then beaker B also has its own number of moles that are going to be poured to beaker C. And then the number of moles in beaker A are unknown, but the number of moles on beaker N and in beaker B are known. And then we can use the pH to find the number of moles of OH minus in beaker C. So what we're going to do, we're going to find the number of moles of OH in beaker C. And then after that, we'll subtract the number of moles in beaker B. And then what will be left is the number of moles in beaker A. So if we go ahead and do that, let's find the number of moles in beaker C. So we have POH equals to 1. Like we determined above, right? And then we know that to calculate POH, we use the concentration of OH minus. So we're going to have minus log OH minus equals to 1. So we're going to have log OH minus equals to minus 1. And now to solve for OH, we can say OH minus is equals to 10 to the power minus 1. You can always do that. It always works. So if you take 10 to the power minus 1, you're going to get OH minus is equals to 0.1. So we have the concentration of OH minus in beaker C. Now we can find the number of moles, right? So the number of moles of OH minus will be equals to the concentration multiplied by the volume, right? What's the concentration? It's what we just determined is 0.1. And then what's the volume? The volume, it is said to be additive, right? So we're going to add the volume of beaker A and the volume of beaker B. So that will be 500 centimeter cube plus 400 centimeter cube divided by 1000. And then if I get this, I put this in my calculator, I'm getting 0.09 moles, right? So now we have the number of moles of beaker C, which is equal to the number of moles of beaker B plus the number of moles of beaker A. The number of moles of beaker C is 0.09. The number of moles of beaker B is what we calculated in 7.2, and that was I think 0.04, right? And then plus the number of moles of beaker A. So the number of moles of beaker A will be equal to 0.09 minus 0.04, which is equal to 0.05. So now we have the number of moles in beaker A. So we can use that to calculate the number of moles of BaOH2. So BaOH2, when it ionizes, it becomes Ba plus 2OH, right? So we can see that the balancing coefficient is 1:2. So we're going to have the number of moles of BaOH2 divided by the number of moles of OH being equals to 1 divided by 2, right? So we're going to have the number of moles of BaOH2 equals to the number of moles of OH divided by 2. So that is equal to 0.05 divided by 2. If I put that in my calculator, I get 0.025. So now we have the number of moles of BaOH2. We can then calculate the concentration. We know that concentration equals to number of moles divided by V, right? The volume. The number of moles is 0.025 and the volume is the volume of beaker A, not beaker A and B added together. So we're gonna have 500 divided by 1000. And then if you put this in your calculator, you're gonna get 0.05 mole divided by decimeter cube, which is equals to X. And then we can move forward. 7.3.2, it starts with the statement there that says the solution in beaker C is titrate. The solution in beaker C is titrated with ethanoic acid. It was found. The solution in beaker C is titrated with ethanoic acid. It was found that 15 centimeter cube of the solution neutralizes 30 centimeter cube of the acid. And then we are given a balanced equation. And then 7.3.2 says, is ethanoic acid a weak acid or a strong acid? At this point of time, you should know that ethanoic acid is a weak acid. And then it says, give a reason for the answer. In grade 12, you will only provide one reason for why an acid is weak. That is to say, it ionizes incompletely. And then 7.3.3 says, calculate the concentration of the ethanoic acid, right? So they neutralized completely. So let me write the equation again. So we have CH3COOH plus OH minus, which is giving us CH3COO minus plus H2O. So again, we can use the number of moles of one to find the number of moles of the other. If you pay careful attention, when you are doing problems in chemical equilibrium and acid and base, you always relating the number of moles, right? You start with one and then you try to figure out the other and vice versa. So we have information for OH, which we can use to determine the concentration of the ethanoic acid. So we determine the concentration of OH minus in 7.3.1, right? And it was 0.1 moles per decimeter cube. And then we're given the volume to be 15 centimeter cube, which we'll have to convert to decimeter cube. So the number of moles from this will be given by the number of moles equals to the concentration multiplied by the volume, right? The concentration is 0.1 and then the volume is given as 15 centimeter cube. So that will be 0.1 multiplied by 15 divided by 1000. We divided it by 1000 because we convert it into decimeter cube. That will give us 0.0015 moles, right? We can see the balancing coefficient that this is 1 and this is 1, right? So the number of moles of OH equals to the number of moles of our ethanoic acid. So to calculate the concentration of ethanoic acid, we're going to say concentration equals to number of moles divided by volume. And then we know that the number of moles is the same as the number of moles of OH because the balancing coefficients are the same, right? So we're going to have 0.0015. And then what is the volume? The volume is given as 30 centimeter cube. So we're going to have 30 divided by 1000. Which is going to give us, let me put that in my calculator real quick. So we have 0.0015 divided by 30 divided by 1000. That is equals to 0.05 moles per decimeter cube. And then you get your 18 marks. Two reactions of sulfuric acid are shown in the diagram below. And then the first question, which is 8.1.1, says define a Lorry-Bronsted base, right? This is the guy or the girl, not really sure, that defines a base and an acid the easy way, right? An acid, it's a proton donor, and then a base is a proton acceptor, right? So 8.1.1 proton acceptor, and you get 2 marks. And then 8.1.2 says
write down a balance equation for reaction 1. Let's take our attention to reaction 1. So reaction 1, we have sulfuric acid, H2SO4, and NaOH. So we have an acid plus a base, right? And an acid and plus a base. An acid and a base will always give you a salt plus H2O, right? That's just the general idea when you have an acid and a base. So we have H2SO4 plus NaOH, and this will give us something, right? Let me put the arrow here for the sake of space. So we need the acid to donate protons, right? And then we need the base to accept. So when the acid donates, we're gonna have this H2O here from the general formula, right? So we're gonna have H2O. So if we have H2O on the acid, we're gonna be left with SO4. So this Na, which was accompanying the OH, which turned to H2O, will be here with NaSO4, right? It will be our salt. But then I want you to realize something. Since H2SO4 lost 2 hydrogens, it will now be SO4 2 minus, right? And then we know that Na is only plus. So we're gonna need 2 NAs. So we're gonna have Na2SO4 plus H2O. Now, when we're at this point, we can then balance our equation. So we have 2 hydrogens here, we have 1 here, and then here we have 2. So the hydrogens are not balanced. How can you possibly balance this hydrogen? If we put a coefficient of 2 here, we're gonna have 4 on the right, and we're gonna have 3 on the left. But if we put a coefficient of 2 here, then we have 4 on the left and 4 on the right. So now the hydrogens are balanced. We can look at S. We have 1 S here, we have 1 S here, so that is balanced. And then let's look at the oxygens. We have 6 oxygens on the left hand side, and then on the right hand side we also have 6 oxygen. So it seems like all is well, and we can move to 8.1.3. 8.1.3. But for the most part, there's only a few reactions you're gonna be examined on, right? So just go to your exam guideline, go through past exam papers, and just memorize all the reactions that you see. And then 8.1.3 says, write down the name of the salt represented by X. So the salt represented by X is Na2SO4. What is Na? We know that Na is sodium, and SO4 is sulfate, right? And that is exactly what the name of our compound is. The name of our salt is sodium sulfate, right? But then it's not all the time that you just take the names of the different elements and then you just call it that. And then 8.1.4 says, let's write down the formula of ampholyte A. Ampholyte A is in our reaction 2, right? So in our reaction 2, we have H2SO4 plus H2O. And then it gives us, we know we're supposed to have H3O plus. So the sulfuric acid only donated 1 proton, right? So here we are left with HSO4 minus, right? So the name of our ampholyte is HSO4 minus. But is HSO4 minus an ampholyte? Yes, it is indeed an ampholyte. In this reaction, is acting as a conjugate base, right? But then if you say HSO4 minus plus H2O, then it's gonna act as an acid. And then let's move to 8.1.5. Write down the formula of the 2 conjugate acid base pairs in reaction 2. So we've already wrote down So we've already written down reaction 2, right? Let's just look for the acid-base conjugate pairs. So H2SO4 is an acid, and then when it loses the protons, we get the conjugate base, right? So if this pair is acid and base, then the other pair by default it will be our acid and base. So we can say H2SO4 and HSO4 minus is an acid base conjugate pair, and then H2O and H3O plus is another acid base conjugate pair. So whatever remains when an acid has donated a proton is the conjugate base, right? That's the rule of thumb. Now let's move to 8.2. 8.2 says a solution of sodium hydroxide NaOH is prepared by dissolving 6 grams solid NaOH in 500 centimeter cube of water. This solution reacts completely with 10 grams of impure ammonium chloride NH4Cl according to the equation below. And there we have our equation, and it says calculate the concentration of NaOH. So 8.2.1 NaOH. Problem solving 101. We have to write down the information we know about the NaOH, right? So we know fully well that the mass is 6 grams, and then the volume is 500 centimeter cube, and we want to find the concentration. Concentration is number of moles divided by the volume. So from the mass we can find the number of moles, and then we have the volume here. So let's go ahead and do that. So the number of moles will be equals to the mass divided by the molar mass. The mass is 6 grams and the molar mass of NaOH is 40. So we're gonna have 0.15 moles, right? Now we can say that the concentration is equal to the number of moles divided by the volume, 0.15 divided by 500 centimeter cube, which you're gonna divide by 1000 to convert to decimeter cube. So we get in concentration of 0.3 moles per decimeter cube. And now we can move to the second question, which says let's calculate the percentage impurities in the NH4Cl. So let's break down percentage impurities. So we usually calculate percentage purity, right? So I'm assuming that percentage purity plus percentage impurity should be equal to 100%, right? So we can basically find the percentage purity, and then from the percentage purity we're gonna say 100 minus percentage purity is percentage impurity. Let me show you what I'm talking about. So we have 8.2.2. So we know that when we want to find percentage purity, we will need the mass, right? So let's say NH4Cl. So at the end of the day, we're going to need the mass, right? We know that initially the mass or mass total is 10 grams, right? We're going to find the mass. For purity, we will find the mass of the pure substance. So the mass that reacted, right? So let's go ahead and do that. What information do we have? Let's write our equation. NaOH plus NH4Cl is giving us NaCl and so on, right? So from the NaOH, we know that the concentration is equal to 0.3 moles per decimeter cube, and then the number of moles is 0.15 moles. And then we're supposed to use this information to ultimately find the mass of NH4Cl, right? Because there's no way we can find the percentage purity without knowing the mass. So how are we going to do that? We are definitely going to use the mole ratios of the two, right? Because in chemistry, for the most part, you're finding the number of moles and using it to find other quantities. So we can say that the number of moles of NaOH divided by the number of moles of NH4Cl will be equals to the balancing coefficient of NaOH is 1 and NH4Cl is 1. So now we're going to cross multiply. The number of moles of NH4Cl will be equals to 0.15 moles. The number of moles of NaOH multiplied by 1. So now we have the number of moles of NaOH. We can then find the mass of the NH4Cl that reacted, right? So the mass is given by the number of moles multiplied by the molar mass. We know fully well that the number of moles is 0.15, and then now we want the molar mass of NH4Cl. I think it is 53.5, right? So we get a mass of 8.025 grams, right? So 8.025 grams is pure, and then the remainder is impure, right? So we want to find the percentage impurity, not the percentage purity, right? So we know fully well that percentage purity is equals to mass of pure divided by mass of the entire sample, right? Multiply by 100. So percentage impurity will be equals to the mass of the impure, right? Divided by mass of sample multiplied by 100. It's a bit of, a trick equation, but not that much. So the mass of the impure, we're saying that initially we had 10 and 8.025 reacted, and then divided by the mass of the pure, which is 10 multiplied by 100, right? And that is 19.75%. You can do it even the other way that I suggested. You can find the percentage purity. So when you find the percentage purity, it will be 80.25%, right? So you would say 100 minus this value here, and you will still get 19.75%. So if you want the definition for 1 mole of a substance, then I've written it down in 6.1.1, right? You can just pause the video and copy it down. So what we're going to start with here is balancing the equation between sodium carbonate and hydrochloric acid, right? The equation is already given to us, but it's unbalanced, right? So that makes our job a little bit more easy. So let's go ahead and try and balance our equation. So on the left hand side, we have 2 atoms of Na, right? And then on the right hand side, we only have 1. So that means that the number of atoms of Na are not balanced. But how can we balance that? If we put a coefficient of 2 here, then we're going to have 2 atoms of Na on both sides, right? So now we can move from Na and go to carbon. On the left hand side, we have 1 carbon atom, and then on the right hand side we also have 1 carbon atom. So the carbon atoms are already balanced. We can move to the oxygen, right? Here we have 3 oxygen atoms, and then on the right hand side we have 1 here and 2 here. So we have 3 oxygen atoms on the left and the right hand side. So the oxygen atoms are balanced. Let's go to the hydrogens. Here we have 1 hydrogen on the left hand side, and then on the right hand side we have 2 hydrogens. We have H2, right? So the hydrogens are not balanced. How can we balance them? If we put a coefficient of 2 on the left hand side, then we're gonna have 2 hydrogens on the left hand side and 2 hydrogens on the right hand side. Now let's look at Cl, right? We have 2 atoms of Cl on the left hand side. On the right hand side, because of this coefficient 2 that we use to balance Na, we also have 2 Cl, right? So now our equation is balanced. We only had to add 2 here on HCl and 2 on NaCl. let's do 6.1.3. So 6.1.3 says calculate the mass of sodium carbonate that reacted, and then there's 7 marks. In order to do these questions, you have to be extremely sober. There's no other way around it, right? You have to be, extremely sober. So let's look at our statement, right? We are told that in an experiment, a learner added 1.5 grams of sodium carbonate, right, to hydrochloric acid. A volume of 306 centimeter cube of carbon dioxide was formed and collected under standard pressure at room temperature. Take the molar gas volume at room temperature as 24.45 decimeter cube, right? So let me just copy down the equation again real quick, because we have to use this equation, right? If we don't have the equation and we just write in things, then it becomes all over the show, right? There need to be clarity in our writing, right? So we are told that at the end of the day, we have a volume of 306 centimeter cube of CO2 produced. And for the sodium carbonate, we are given an initial mass, which is 1.5 grams, right? So of this 1.5 grams, not all of it reacted, right? That's why the question is asking us to calculate the mass that reacted. But how can we calculate the mass that reacted? Using the CO2, right? The volume of CO2 that was produced, we can find the number of moles of CO2 that we produce. And then with the number of moles of CO2 that we produce, we're gonna then use the mole ratio to find the number of moles of Na2CO3 that reacted. And from the number of moles, we can find the mass. Let me show you what I'm talking about. Let's not forget that here we have the balancing coefficients. So the number of moles of CO2, we're going to have the number of moles being equals to the volume divided by molar gas volume, right? If you have a volume of a gas, that's how you can find the number of moles. You use this formula here. So what is the volume? We know fully well that the volume is 306 centimeter cube, right? But then in chemistry, we don't use centimeter cube, we use decimeter cube. So what do? We divide by 1,000 from centimeter to decimeter cube. So we're gonna say divided by 1,000, and then we divide by molar gas volume. Is given to us as 22.45 decimeter cube. And then if you punch that in your calculator, you're gonna get 0.0125 moles per decimeter cube, right? So now we have the number of moles of CO2 that were formed with part of the sodium carbonate that reacted. Now using the mole ratio, we're going to be able to find the moles of Na2CO3 that reacted, and consequently the mass that reacted, right? So now we can say the number of moles of CO2 divided by the number of moles of Na2CO3 is equals to the balancing coefficient. What is the balancing coefficient on CO2? The balancing coefficient is 1, right? And then the balancing coefficient of Na2CO3 is also 1. Yeah, if you're still so confused and you don't even know what a balancing coefficient is this number here, right? You can see for NaCl the number is 2, for HCl the number is 2, for Na2CO3 we don't have anything, right? But we actually have, it's 1, right? And then for CO2 it's also 1. Just in case. So now we can say that the number of moles of Na2CO3 will be equals to, we cross multiplying everything by 1, right? So it will just remain how it is. It's equals to the number of moles of CO2 being equals to 0.0125 moles per decimeter cube. So now we have the number of moles of Na2CO3 that reacted, and we can then find the mass, right? Because we know fully well that the number of moles is equals to the mass divided by the molar mass if you're dealing with a solid, right? So now we can say that this is for Na2CO3. Let's not forget that. So now we can say that the mass is equals to the number of moles divided by the molar mass. We cross multiply it, right? So we're going to have 0.0125 multiplied by the molar mass of Na2CO3. It's 106. You can verify that on your periodic table, right? And then the answer we get in now is 1.33 grams, right? So that's the mass of Na2CO3 that reacted, right? Let's do 6.1.4. Calculate the percentage of sodium carbonate in excess. So we have the mass that reacted, right? We have the mass initial that we started with, right? So we can find the mass in excess, right? Because let's say for Adam and Eve's sake, right? You have initially you had 5 apples, and then something happens to your apple, and then after, right, in excess, basically you have 2 apples. How many apples were used? You would say 3, right? So this is just telling us that the mass that is used is equals to the mass initial minus the mass in excess, right? You cannot deny for Adam and Eve's sake. So the mass initial is given to us as 1.5, right? The mass in excess, that's what we're looking for, mass in excess, right? And then the mass used is what we calculated here, right? We have 1.33. So now you're going to take this term to the left hand side, right? You're going to have 1.33 minus 1.5, right? And you're going to get minus 0.17 being equals to minus the mass in excess, right? It's easy, divide both sides by -1, and then the mass in excess is equals to 0.17 grams, right? So now we can say that the percentage of CaCO3 in excess, right, will be equals to, so we have 0.17 divided by the initial mass, which is 1.5, multiplied by 100. Obviously, we want the percentage. So that will be 11.33 recurring, right? And so on, percent. You can see here the kind of stuff we do in that you have no choice. You have to be, extremely sober, right? Let's do 6.2. 6.2 is saying that zinc reacts with sulfuric acid according to the reaction below, right? And then there we have our reaction. The mass of zinc is recorded during the experiment and is showed on the graph below. The reaction stops after 2 minutes, right? So let's analyze our graph for just a second. Initially we had a mass of 5 grams, right, at t is equals to 0, and then after some time the mass is now 2 grams and it stays at 2 grams, right? And then 6.2.1 says name the substance that is the limiting reactant, right? Let's analyze our situation. We have zinc and sulfuric acid, right? The mass of zinc starts at 5 grams, right, here, and then at 2 grams it never goes down, it remains there. Clearly, what was causing the mass of zinc to be converted to something else is depleted, right? So zinc is being limited by something it's reacting with here, and the only thing it's reacting with is sulfuric acid, right? So the substance that is acting as the limiting reagent is the sulfuric acid, right? So 6.2.1, you just say sulfuric acid. And now we can do 6.2.2. 6.2.2 says calculate the initial concentration of the sulfuric acid if 50 centimeter cube of the acid was used? All the time when I have a question like this, I'm going to write the formula down, right? If I cannot see the formula on the answer sheet, it's just, too confusing for me. So I have the zinc plus H2SO4 giving me ZnSO4. I don't know what the name of that is, plus H2. Stories. The question is saying from the sulfuric acid, let's find the initial concentration, right? But because you're a chemist, we know that to find the concentration, we need the number of moles and the volume, right? But I kid you not, they've given us the volume here. So what we want is only the number of moles. We know that the volume is equals to 50 centimeter cube, right? Which we are obviously going to convert to decimeter cube. So we want the initial concentration. So we need the number of moles of H2SO4, right? The number of moles of H2SO4. How can we find that? We can use zinc, right? Because we know fully well the mass of zinc that reacted, right? Again, for Adam and Eve's sake, initially we had 5 grams of zinc, and then after some time we have 2 grams. So how much reacted? It should be clear to see that 3 grams of zinc reacted, right? So now we can say that with regards to zinc, we know that the mass that reacted is 3 grams, right? So from the mass, we can find the number of moles of zinc that reacted. And from the number of moles of zinc that reacted, we can use the mole ratio to find the number of moles of H2SO4. If we have the number of moles and we have the volume, we have the concentration, and we are done with our problem, right? So let me show you what I'm talking about. Now we say that the number of moles is equal to the mass divided by the molar. So what is the mass? The mass is 3, right? And the molar mass of zinc, that is 65. And when you punch that in your calculator, you should get 0.0462 moles, right? Again, the mole ratio. So the number of moles of Zn divided by the number of moles of H2SO4 should be equals to the ratio of the balancing coefficients. So we have 1 divided by 1, right? So the number of moles of H2SO4 is equals to the number of moles of zinc, which is equals to 0.0462. I wish we had a problem where the balancing coefficients were not 1 and 1, because I feel like people will make mistakes, because in other questions you might not get 1:1. So make sure you go and watch other videos on acid and bases so that you can see how you manipulate this kind of equation when you don't have a balancing coefficient of 1 and 1, right? But stories. So now the number of moles of H2SO4 is that, right? And then now we can find the concentration. That's what the question is asking us to do. Concentration is equals to number of moles divided by volume. So we have 0.0462 divided by the volume, right? 50 centimeter cube. Obviously, we're going to divide it by 1,000. We deal with decimeter cube. We are chemists, right? And when you punch that in your calculator, I wish you get 0.92 moles per decimeter cube.
7.1.1. Is ethanoic acid a weak acid or a strong acid? Give a reason for the answer, right? So I'm gonna say it's a weak acid, right? Why am I saying it's a weak acid? I'm saying it's a weak acid because it's an ingredient of household vinegar, which you've probably used at some point of time. And if you pour a bit on yourself, you don't get burnt in any way. So it's a weak acid, right? But then when they say give a reason, they don't want you to say that. They now want the technical reason why it's considered a weak acid. So what is the technical reason? It's considered a weak acid because it dissociates partially in water, right? That's the reason they're looking for. So you're gonna say dissociates partially in water. And then we have 7.1.2. It says an ethanoic acid solution has a pH of 3.85 at 25 degrees Celsius. Calculate the concentration of the hydronium ions H3O plus in the solution. So fine, we know that pH is equals to minus log and then H3O plus, and then the pH is given to us as 3.85. So 3.85 will be equals to minus log concentration of H3O plus, and then we multiply everything by minus 1, right? So we're gonna get minus 3.85 equals to log HO3 plus. And then we can say that the concentration of H3O plus is equals to 10 to the power minus 3.85. And then if I put that in my calculator, I'm getting 1.41 times 10 to the minus 4 moles per decimeter cube. And then we have 7.1.3, which says sodium ethanoate CH3COONA, right, forms when ethanoic acid reacts with sodium hydroxide. And then it says, will the pH of sodium ethanoate solution be greater than 7, less than 7, or equal to 7? It's definitely gonna be greater than 7. Why is it greater than 7? We know now that ethanoic is a weak acid, right? So we have a weak acid being combined with a strong base, because sodium hydroxide is a strong base, right? So if you combine these two, you're gonna get a base, right? You will have a pH of greater than 7. So if instead you had a strong acid and a weak base, then the pH would be less than 7. And then we have 7.1.4, which says explain the answer to question 7.13 with the aid of a balanced chemical equation. So let's put sodium ethanoate in water and see what happens. So we have CH3 COONA plus H2O, and then this is supposed to give us something, right? So because we're saying that this is a base, right, because it has a pH of greater than 7, so this has to be an acid. So a base will accept a proton, right? And then the acid will donate a proton consequently. So if CH3COONA accepts a proton, we're gonna have CH3COOH plus NaOH. So we can see that we have hydroxide here, and as a consequence, the pH will be basic. So let's move forward and go to 7.2. 7.2 says household vinegar contains 4.52% of ethanoic acid, CH3COOH by volume, right? And then 1.2 gram of impure sample of calcium carbonate is added to 25 centimeter cube of household vinegar. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14.5 centimeter cube of a sodium hydroxide solution of concentration 1 mole decimeter cube. And then we have a balanced equation for the reaction. That's a mouthful, but let's see what we can do. So we have 7.2.1 saying calculate the number of moles of the unreacted ethanoic acid. So it is said that the excess ethanoic acid is neutralized by
sodium hydroxide, right? So we're gonna have NaOH. This NaOH neutralize the ethanoic acid. But then we are told that the volume that does the neutralization is 14.5 centimeter cube, and then the concentration was 1 mole per decimeter cube, right? So what we can do, we can find the number of moles of NaOH related to the number of moles of ethanoic acid, and we're basically done, right? So from here we can see that the number of moles is equal to the concentration multiplied by the volume. We know the concentration fully well, that is 1, and the volume is 14.5 divided by 1,000. By now you should know why I'm dividing by 1,000. I'm converting the centimeter cube to decimeter cube. So if I divide that by 1,000, it's giving me 0.0145 moles, right? So now I want you to look at something. The balancing coefficient of our ethanoic acid is 1, and the balancing coefficient of our NaOH is 1. So the number of moles of NaOH is equal to the number of moles of CH3COOH, and then that will be 0.0145 moles. But what if the balancing coefficients were not the same? I've solved a similar problem with that kind of situation, so I would advise you to go and check it out. So moving forward, we have 7.2.2, which says calcium carbonate reacts with the ethanoic acid according to the following balance equation, right? And then it says calculate the percentage of calcium carbonate in the impure sample if 1 centimeter cube of household vinegar has a mass of 1 gram. So what this question basically wants us to do is calculate the percentage purity of calcium carbonate, right? And then when we calculating percentage purity, we'll always end up saying the percentage of the whatsoever we have, right, is equal to the pure divided by the impure and multiplied by 100. We have the pure, it's 1.2 gram is given to us, and now what we need to determine is the pure, right? But then how would we go ahead and do that? We need to find the number of moles of ethanoic acid that reacted, and by using that we can then relate the number of moles using the balancing coefficients, and consequently found the mass of the calcium carbonate. So for the number of moles of ethanoic acid that reacted, we still need the mass initial, and to determine that we're gonna say that the mass is equals to 4.52 divided by 100 multiplied by 25. Why am I saying that this will give us the mass? Because usually the mass is the number of moles by the molar mass. So look at this. This is the percentage of ethanoic acid in household vinegar, right? And then we are told in the equation that 1 centimeter cube, we can take it as 1 gram, right? So that's exactly what I'm doing there. So we're gonna have 4.52 divided by 100 multiplied by 25, which is equals to 1.13 grams, right? And from this 1.13 grams, we can then calculate the number of moles of ethanoic acid initial, right? So we're gonna say the number of moles is equals to the mass, obviously, divided by the molar mass, which will be 1.13 divided by the molar mass of carbon is 12 plus 3 for the 3 hydrogens plus 32 for the oxygens plus 1, right? So let me punch this in my calculator real quick and see what I get. So divided by 12 plus 3 plus 32 plus 1 plus 12 again. I just missed the carbon there, and this is giving me 0.0188 moles, right? So now, because we have number of moles in initial, right, and we have number of moles that are in excess, right, that didn't react, we can then calculate the number of moles that reacted. So we're going to say number of moles that reacted equals to number of moles initial minus number of moles in excess, right? So the number of moles that reacted will be equal to the number of moles initial, which is 0.0188, minus number of moles in excess, which we calculated in 7.2.1, right? That is 0.0145. And then let me put that in my calculator real quick. That is 0.043. So now we can determine the mass of the calcium carbonate, right? So we can say that the number of moles of our acid divided by the number of moles of our base basically is equals to what the balancing coefficient of the acid is 2, right? And for the base is 1. So we're gonna say that the number of moles of the base equals to 0.043 divided by 2. If I do that, let me see what I get. It's giving me 0.00215. So from that 0.00215, we can calculate the mass of calcium carbonate, right? So we're gonna say that the mass is given by the number of moles multiplied by the molar mass. So this will be 0.00215. And what's the molar mass of calcium? Calcium carbonate. That's 100, right? Which is 0.215, right? So now we can come back to our formula for the percentage purity, right? And then for the impure, we can then put 1.2, and then for the pure, we can put 0.215. And then if we multiply that, we're gonna get about 18.08, right? Or something, somewhere there.
The following apparatus is used for the tractation of a dilute alkali with a dilute acid. And we're given a balanced equation, and 7.1.1 says, what type of a reaction takes place when an acid is added to an alkali? An alkali is basically a base, right? So we have an acid and base reaction. So 7.1.1 acid and base reaction. Another name for an acid and a base reaction is neutralization, right? So you can write acid and base, or you can write neutralization. Now let's move to 7.1.2, which says that write down the name of the dilute alkali. So the acid is H2SO4, right? Which is basically sulfuric acid. Ba is barium, right? And then OH, you usually pronounce it as hydroxide, right? If you remember, if we have NaOH, this would be sodium hydroxide, right? So this will consequently be barium hydroxide. So here 7.1.2, we have barium hydroxide. 7.1.3 says, name the pieces of apparatus labeled X. So here's X here. You should be familiar with X at this point of time, right? X is a burette. It's essentially a glass tube, right? With readings on it, and it has a turning plug here, right? To control the amount you're putting in on your beaker or whatsoever you're using. So 7.1.3, we have a burette. And then 7.1.4 says methyl orange is used as an indicator what will you observe in Y when the acid is added before the endpoint is reached. So before we add any acid, right, you are going to basically have a base, right? If you add methyl orange to a base, then the methyl orange is gonna turn yellow. So what we are going to observe between before the endpoint is reached is that the methyl orange turns yellow, and then as we add more acid, it will gradually turn to orange as we reach a pH of around 7. And then if you keep on adding more acid and now the solution actually becomes acidic, then the methyl orange will turn red. So for 7.1.4, the methyl orange turns yellow because we added into a base, and gradually turns orange. And if you keep adding more acid and your solution becomes acidic, it will consequently turn red. And then 7.1.5 says, state whether each of the following increases, decreases, or remains constant while the acid is being added before the endpoint is reached. So back to the basics. What's an acid? An acid is a proton donor. So when we increase the acid, we increase in H+, right? So what will happen to Ba to the 2+, right? We won't have any effect on Ba to the 2+ when we increase the acid, right? So Ba2+ will remain constant, right? And then what will happen to OH minus? The concentration of OH minus will go down when we add H+. Why am I saying that? So before we started adding the acid, right, we just had BaOH2 giving us Ba to the 2+ plus 2OH minus, right? So when we add the acid H2SO4, the Ba2+ will react with SO4 2 minus, and then the OH minus will react with 2H plus. So the more we add the acid, the more the concentration of OH minus decrease, right? Because OH plus H is clearly H2O. So here for OH minus is going to decrease. So for pH, we know that the pH is equals to minus log of H plus. The more you increase the concentration of H plus, the lower the pH will be, right? So as we increase H plus, the pH will consequently decrease. And then now we can do 7.1.6. 7.1.6 says that during the reaction, 50 centimeter cube of the dilute alkali reacts completely with 30 centimeter cube of the dilute acid. So the dilute alkali is reacting completely. That tells us that the dilute alkali is our limiting reactant, right? And then the question goes on to say, calculate the mass of barium sulfate that will form during the reaction if the concentration of the dilute alkali is 0.1 mole per decimeter cube. So we have the dilute alkali BaOH2, right? And then we are given the concentration. It is said to be 0.1 mole per decimeter cube, and then we are given the volume, which is said to be 50 centimeter cube. So if we find the number of moles of BaOH then we're going to be able to use those number of moles to find the number of moles of barium sulfate, right? And from the number of moles of barium sulfate, we'll consequently be able to find its mass, because that's what the question is asking us to do, right? So here we're gonna have the concentration is equal to the number of moles divided by the volume. If you make the number of moles a subject of the formula, you get concentration multiplied by volume. So what's the concentration? The concentration is 0.1, and what is the volume? The volume is 50 centimeter cube, right? But we'll deal with decimeter cube. So here we're going to have 50 divided by 1,000. So 50 divided by 1,000. So we basically have 5 divided by 1,000, which will be close to 0.005 moles, right? So if we go back to our equation again, the balancing coefficients, we have 1, 1, 1, right? So the number of moles are basically equal for all those three that I just indicated there. So the number of moles of BaOH2 will be equal to the number of moles of BaSO4. So that will be 0.005 mole, right? Now we can calculate the mass of barium sulfate. We have the number of moles, and the molar mass, we can get it from our periodic table. So now we know fully well that the number of moles is equal to the mass divided by the molar mass. If you make the mass of the subject to the formula, you get number of mole multiplied by the molar mass. So what is the number of mole? What we just calculated, right? So we have 0.005 multiplied by the molar mass of barium sulfate. If you add the molar mass of barium and SO4, that will give you 233. So 233 multiplied by 0.005, that is 1.165 grams. So the mass of the barium sulfate that will be formed will be 1.165 grams. I hope that is clear. Let's just recap for the last time. We're given the concentration and the volume of dilute alkali or barium hydroxide, right, which was used, and then we figured out that it's our limiting reactant, right, because we are told that it reacts completely. So from there we find the number of moles of the alkali, the dilute alkali, and we use those number of moles to find the number of moles of the barium sulfate, right? And from the number of moles we calculate in the mass here, right? High school chemistry is basically finding the number of moles of one reactant and using it to find the number of moles of the other, and from there you'll find either the concentration or you'll find the mass. And then 7.2 says 2 test tubes contain solutions of NH4 NH4 I think, and CH3COONA. Their pH values are less than 7 and greater than 7 respectively. Write down the following rewrite the following hydrolysis equation in the answer book and complete them to explain this behavior. So for NH4+, we are told that the pH is less than 7, right? So if it is less than 7, it is acidic, and if it's acidic, then it's a proton donor, right? So that NH4+ is supposed to lose a proton, it's supposed to lose one hydrogen, right? So here we're gonna have NH3, right, instead of NH4, because now we have lost a hydrogen, plus H3O plus, right? And then that's basically what you're being asked to do. And then now let's pay our attention to 7.2.2. It is said to have a pH of greater than 7. What does that tell us? It tells us that it is basic, so it's supposed to gain a proton, right? So we're gonna have CH3COOH, right? There we go. We have gained a proton plus, now the proton is coming from H2O, right? So the H2O now will be OH minus, and then now so the hydrogen that NH4 plus lost came to H2O, right? So hence here we have H3O plus. High purity copper is obtained by electrolysis using a thin pure copper cathode and an acidified solution of copper sulfate, clearly demonstrated on our schematic. And then 9.1 says, at which electrode will pure copper be deposited? Write only A or B. So back to the basics again. In electrolysis, we have two electrodes connected to a power source, right? Clearly, this will be the positive terminal and this will be the negative terminal. Now the question you have to ask yourself is that which electrode is connected to the positive terminal and which electrode is connected to the negative terminal. In an electrolytic cell, the anode will be connected to the positive terminal. So here we know that electrode B is our anode, and then consequently electrode A is our cathode. But that's not what the question is asking us. At which electrode will pure copper be deposited? Write only A or B. Where the pure copper is deposited, it's where a reduction happens, the gaining of electrons that takes place at the cathode, right? So from that information here, our answer would be A, right? That's where the pure copper will be deposited because A is our cathode and that's where reduction takes place. And then 9.2 says write down the half reaction for this cell. We have pure copper. It needs to be deposited somewhere. We're saying that it takes place at the cathode, and at the cathode that's where reduction takes place. So we're gonna have copper 2 plus 2 electrons giving us copper. That's our reduction half reaction for this cell. Now let's move to 9.3. 9.3 says that use the graph to calculate the percentage purity of the impure copper that was used as the cathode. The mass of the impurities formed in an hour is 15.8 grams when a constant current is used. Right, now let's go back to the basics. We have percentage purity, right? Percentage purity, that is mass of pure sample, right? Divided by the mass of the impure multiplied by 100. But in this question, it's not really that clear, so we have to break it down, right? The mass of the pure sample will be the mass deposited at the cathode, right? So here we're gonna have mass deposited, and then mass of impure will be mass deposited plus the impurities that are left behind, right? So here we have mass deposited plus the mass of the impurities, right? Multiplied by 100, because we have this chunk of an impure sample, and then some of that amount gets deposited at the cathode, so we know that that amount is pure. But then the mass of the impure sample as a whole will be the mass of the impurities plus the mass of the deposited. So we are told that after an hour 15.8 grams is deposited at the cathode, right? So we're gonna have 15.8 divided by 15.8 mass deposited plus the mass of the impurities. The mass of the impurities formed in an hour is 15.8 grams, right? So we're basically gonna be finding mass deposited. So we're gonna have mass deposited which we are going to find divided by 15.8. That is for impurities, right? Plus mass deposited again. So we have mass deposited. We still multiplying this entire number by 100. So now our duty is to find the mass deposited, right? If we go back to our sketch here, you're gonna see that the number of moles deposited in 1800 seconds is 0.25, right? But then here on our equation, we're given the mass of impurities in an hour, right? So we have to multiply this 0.25 to find the number of moles deposited in an hour, right? We have the impurities in an hour. We have to find the number of moles in an hour. So now we can say that the number of moles is equals to mass divided by molar mass. So we're looking for the mass, so we're gonna say the number of moles multiplied by the molar mass. So what is the number of moles? The number of moles in an hour will be 0.25 multiplied by 2, right? We are given the number of moles in 30 minutes. We want the number of moles in an hour, so we simply multiply by 2, right? And then the molar mass, we're looking for the molar mass of copper, which is 63.5, and then when you multiply that 2, you get 31.75 grams, right? Our percentage purity, right, will then be equals to 31.75, which is the mass deposited divided by 15.8, which is the mass of the impurities, plus the mass deposited again, which is 31.75 multiplied by 100. And then if you punch that in your calculator, and that will give you 66.67%. Now let's move forward to 9.4. 9.4 says the copper sulfate is an electrolyte and the concentration remains constant for the duration of the reaction. 9.4.1 define an electrolyte. An electrolyte is a solution that conducts electricity through the movement of ions. An electrolyte is a solution that conducts electricity through the movement of ions. And then 9.4.2 says explain why the concentration of the solution remains constant. The concentration of the solution remains constant because the rate of oxidation is equal to the rate of reduction. The rate of losing electrons is equal to the rate of gaining electrons, and as a consequence, the concentration of the solution remains the same.
Write down the energy conversion that takes place in this cell. It is an electrolytic cell, so we have electrical energy to chemical energy, electrical energy to chemical energy. We can also see that by the presence of a power source, we have electrical energy being supplied to the cell, and that electrical energy is then converted to chemical energy. 9.1, let's take a look at 9.2. At which electrode A or B will pure copper be deposited? 9.2. Right, so pure copper, it will get deposited at the negative electrode, meaning that the answer to 9.2 should be B. Let me show you why it will get deposited at the negative electrode. Take a look at this. We have CuCO4, which will break down to form copper 2 plus SO4 2 minus. This is a positive ion. This is a negative ion. The positive ion will get attracted to the negative electrode, which is B, and that's where a reduction is going to take place. So that is why I'm saying that the pure copper will be deposited at the B, because it is negative, and the copper 2 plus will be attracted to the negative electrode as positive and negative attracts. 9.2. Let's take a look at 9.3. Write down the half reaction that takes place at the anode. At the anode, we have oxidation. of copper, right? So we're going to have copper turn into copper 2 plus 2 electrons at the anode. This is at the electrode A. At the electrode A, we're going to have copper becoming copper 2 plus 2 electrons. There we go. Let's take a look at 9.4. How will the gradient of the graph be affected as the reaction is allowed to proceed until completion? Right, only increase, decrease, or remain the same. So let's take a look at what's happening here in more detail. The diagram below represents the purification of copper ore to pure copper. The cell also contains zinc, silver, and platinum impurities. Right. The graph shows the initial relationship between the mass of copper deposited versus the time. So back to our question, how would the gradient of the graph be affected as the reaction is allowed to proceed until completion? Well, the gradient of the graph is not going to change. The gradient of the graph is not going to change. As oxidation occurs, reduction occurs. So we're never going to reach a point where the mass of copper deposited, the rate at which the mass of copper deposited goes down. We're never going to reach such a point or a rate where it increases. The gradient will remain the same throughout until completion. Right. 9.5. Refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Why zinc will not be deposited at the cathode. Why zinc is not going to be deposited at B. So let's take a look at what is happening here. The question says that we have some impurities, which happens to be zinc, silver, and platinum. But in our question, we are only interested, so let me just say in 9.5, we are only interested on zinc and copper. Why is zinc not being deposited at the cathode? Why is it copper that is being deposited at the cathode? So it means that we have, as our ions in the solution, we have zinc 2 plus and copper 2 plus. One of these two is to be deposited at the cathode, where reduction is going to take place. So between zinc 2 plus and copper 2 plus, what is the stronger oxidizing agent? Because the stronger oxidizing agent is what's going to get deposited at the cathode. The stronger oxidizing agent is what's going to get deposited at the cathode. So what do we need to do? We need to go to a predict table and see which one it is between zinc 2 plus and copper 2 plus. The question says, why is zinc not being deposited at the cathode? So obviously we already have our answer, but I'm just trying to show you where it is coming from. Copper 2 plus is a stronger oxidizing agent compared to zinc 2 plus. Let's go to our table so that it can be easy to see. All right. So our table, standard reduction potential. Okay, let's take a look at, let's use 4A. It doesn't really matter which table we use, by the way. So take a look. Increasing oxidizing ability as we go down. So let's look for zinc and copper 2 plus. Okay, so where is zinc? Where is copper 2 plus? This is copper plus. We're not looking for that. We're looking for copper 2 plus. We have copper 2 plus right here. No, that is actually not the one we're looking for, because we're looking for the one that will accept 2 electrons to form copper. This is the one we're looking for. This is the copper 2 plus you're looking for. So be very careful when you're using this table. You just don't find copper and take it as it is. You have to take a look at exactly what you are dealing with. Okay, so we're saying that copper 2 plus is a stronger oxidizing agent. So we must find zinc. I was starting to get worried a bit. Here we have a zinc 2 plus, but look at my arrow. My arrow is going the wrong direction. The arrow is supposed to be pointing up, as you can clearly see here on our table. So clearly, copper 2 plus is a stronger oxidizing agent compared to zinc. So the answer to 9.5, which is saying refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Zinc will not be deposited at the cathode because copper 2 plus is a stronger oxidizing agent, right? And zinc 2 plus is a stronger reducing agent, therefore. Okay, so that is the reason why it is copper 2 plus that's going to be deposited at the cathode and not zinc 2 plus. Okay, that is 9.5. Let's take a look at 9.6. Maybe I need to erase this going to 9.6 so that I can have a bit of space. So let's do that. Back to our diagram and back to 9.6. So 9.6, when the current flows for 30 minutes, 15 grams of copper was deposited at one of the electrodes. Okay, and then 9.6.1, calculate the number of moles of copper deposited. Well, quite an easy equation because we are given the mass, so we are really sticking to the basics. Number of moles is equal to the mass divided by the molar mass, right? And then the mass is 15 grams. The molar mass of copper, that is 63.5. When you put that in your calculator, you get 0.24 moles. Right, it's quite a strange equation, right? Because we're just calculating the number of moles, no trickery whatsoever. 9.6.1, let's take a look at 9.6.2. Determine the number of moles of electrons that flows through the circuit while 15 grams of copper is deposited. 1 mole of copper gives us 2 moles of electrons. Right, it sounds very wrong to say 2 moles of electrons, but we can see the relationship here. For 1 copper atom, we have 2 electrons. So if we're saying that the number of moles of copper, well, we're saying copper is 2 electrons. If we're saying it is 0.24, then that of electrons should then be 0.48 moles. So there we go. That is question 9.
In electrochemical cell A, we have carbon as the electrode, while in electrochemical cell B, we have copper as the electrode. The first question, 1.1, are A and B electrolytic or galvanic cells? It will be easy to see that A and B are electrolytic cells. Why do we say so? The presence of a power source and the mere fact that both electrodes are in one container. In a galvanic cell, the electrodes are in different containers and there is no power source. 1.2, which of the electrode P, Q, R, or T will show a mass increase? Write down a half reaction to motivate the answer. In both galvanic and electrolytic cells, we see a mass increase at the cathode. The only difference is that in a galvanic cell, the cathode is positive, while in an electrolytic cell, the cathode is negative. If you look at electrochemical cell A, Q is the negative electrode and T is the negative electrode. So that is where we expect to see a mass increase. So the answer here is Q and T. Why is there a mass increase at the cathode? That is because copper 2 plus is getting reduced to copper. More on this in the following question, 1.3. I'm going to explain why that is so. But for now, let's just leave it like that. Let's go to 1.3. So in 1.3, we're supposed to write down the name or formula of the product formed at electrode P. So let's go ahead and take a look at electrode P. P is the anode and Q is the cathode. So we have P being our anode and Q being the cathode. This is probably the most important part of the video. This is exactly what I want you to learn. We know that N ions move to the anode. What are N ions? Negative ions. In our case, the negative ions we have is Cl minus. Why am I saying Cl minus? This is coming from CuCl2. The electrolyte we have, it is an aqueous solution and not liquid. So we also have OH minus from H2O. And then the cation ions, positive ions that will move to the cathode. We have Cu2 plus and H plus. The question here now is between Cl minus and OH minus, what undergoes oxidation? Cl minus is gonna undergo oxidation. The only way OH minus would go under oxidation is if instead of using concentrated Cl2, we use dilute. And another special case is when we have SO4 minus or NO3 minus as the other N ion. If this is the case, then OH minus will get oxidized. But if these conditions are not satisfied, then Cl minus or any other N ion will get oxidized. So at the anode, we have 2Cl minus getting oxidized to form Cl2 plus 2 electrons. The product that is formed at electrode P is chlorine gas, or Cl2, if you decide to write the formula. Let's go ahead and do 1.3.2. We're looking for the name or formula of the product formed at electrode R. Electrode T is the cathode, so electrode R is our anode. What N ions are we going to have at the anode of electrochemical cell B? This is where it gets interesting and gets complicated. At the anode, we have copper as our electrode. So the species we're going to have is going to be copper, Cl minus, and OH minus. The question really here is between copper and Cl minus, what gets oxidized? Copper is a stronger reducing agent compared to Cl minus, so copper will get oxidized. We're going to have copper getting oxidized to form copper 2 plus 2 electrons. So the product at electrode R is actually copper 2 plus and not chlorine. Now I want us to go back to 1.3.1. If you look at 1.3.1, we talked about why Cl minus gets oxidized at the anode. Let's talk about the cathode. What will get reduced between Cu2 plus and H plus? What is going to get reduced there? It's Cu to the 2 plus. Why do I say so? Cu to the 2 plus is less reactive compared to H plus. The question now is, how do I know which species is less reactive compared to the other species? Well, the description of the video, I'm going to put the species from the least reactive to the most reactive. So make sure that you check that out in the description. This is quite a unique and special question, more especially when you take a look at 9.2.3. We're supposed to calculate the value of x as shown on the graph for 6 marks. What is the information we have? We have the current, which is 2.5 ampere, and the time, which is 10 hours. How do we go from current to time to x on the graph, which is basically the mass of the electrode? Well, you're about to find out. The first question, 9.1, we are supposed to define the term electrolysis. That is the use of electrical energy to produce a chemical change. The use of electrical energy to produce a chemical change. Usually, a lot of people will define it as a chemical process in which electrical energy is converted to chemical energy. That is also totally fine. That is 9.1. 9.2, on the other hand, the graph below, not drawn to scale, represents the changes in the mass of electrode T during electrolysis. We have the electrolysis of concentrated chromium chloride, CrCl3. We have 2 electrodes, R and T. The first question, 9.2.1, we're looking for the half reaction that takes place at electrode T. We have 2 electrodes, R and T. This is the mass. This graph is showing us the mass of the electrode T. As you can clearly see, the mass is increasing, and we know that the mass increases at the cathode. So T is our cathode and R is our anode. This is true for both galvanic cells and electrolytic cells. There is a mass increase at the cathode. So we need a half reaction that is taking place at the cathode. Okay, Our electrolyte is CrCl3. The ions we have is Cl minus and Cr to the 3 plus. Those are the ions we have. But this CrCl3, it is an aqueous solution. So there's H2O. Apart from these ions, we also have OH minus and H plus. We know that N ions, they migrate to the anode, while Cat ions migrate to the cathode. So that's why I have Cl minus and OH minus under the anode, and C to the 3 plus and H plus under the cathode. At the cathode, oxidation takes place. We're going to have oxidation of Cl minus. And at the cathode, reduction takes place. At the cathode, chrome 3 plus will undergo reduction. We can also see that from the net cell reaction that we are given. So the half reaction that will take place at electrode T, which is our cathode, will be Cr to the 3 plus 3 electrons to give us Cr. That is the half reaction that takes place at the cathode. 9.2.1. 9.2.2. A current of 2.5 ampere passes through the cell for 10 hours. Let's calculate the total charge that flows through the cell during this time. So we have the current, we have the time, we are looking for the charge. Which equation can we use? The current is the rate of flow of charge. So we're going to have the current being equals to the charge divided by the time. In order to find the charge, we can simply cross multiply and have the current 2.5 multiplied by time, which is 10 hours. But we know that our time is supposed to be in seconds. So we're going to have 10 hours multiplied by 60 minutes multiplied by 60 seconds. If you put that in your calculator, you're going to get 90,000 coulombs. This is the charge, the amount of charge that flows through the cell during this time. 9.2.2. The question you've been waiting for, 9.2.3. Let's find the value of x as shown on the graph. Well, what is the question really asking us to calculate? We know that we have chrome being deposited at the cathode. So we need to calculate the mass of the chrome that has been deposited at the cathode. How can we do that? Let's look at the information we have. We have the charge. How can we go from charge to number of moles essentially before we ultimately calculate with the molar mass and find the mass? From the charge, we can find the number of electrons. From the number of electrons, knowing fully well that 3 electrons will result to 1 chromium atom, we can determine the number of atoms of chromium. From the number of atoms of chromium, we can ultimately find the number of moles using Avogadro's number, and then we can determine the mass. Let's go ahead and do that. The number of electrons is equals to the charge divided by the charge of an electron. This will give us 90,000, which is the charge we determined above, divided by 1.6 times 10 to the minus 19. That is equals to 5.63 times 10 to the power 23 electrons. Let's use it to find the number of atoms of chromium. Well, 3 electrons will give us 1 atom of chromium. So we can say that the number of atoms of chromium is equals to the number of electrons divided by 3. We're going to have 5.63 times 10 to the power 23 divided by 3. If you put that in your calculator, you're going to get 1.88 times 10 to the power 23 as the number of atoms of chromium. Now we can use the number of atoms of chromium to find the number of moles of chromium. The number of moles is equals to the number of atoms divided by Avogadro's number. This will give us 1.88 times 10 to the power 23, everything divided by 6.02 times 10 to the power 23. This is equals to 0.31 moles. So we have the number of moles. We can go ahead and find the mass. The mass will be given by the number of moles multiplied by the molar mass. 0.31 multiplied by 52. That is the molar mass of chromium. If you put that in your calculator, you will get 16.12. X is just equals to 16.12 plus 2.2. This will give us 18.32 grams. Besides concentration, write down 2 conditions needed for the hydrogen half cell to function under standard conditions. In total, we have 3 standard conditions, one being concentration at 1 mole per decimeter cube. 1.1, we're looking for the other 2 standard conditions. That is pressure. Pressure is one of our standard conditions at 101.3 kilopascals. Another standard condition we have is the temperature at 298 kelvins or 25 degrees Celsius. That is the answer to 1.1. Let's go ahead and take a look at 1.2. Give 2 reasons besides being a solid why platinum is suitable to be used as an electrode in the above cell. So as you can see here, where there is hydrogen gas, platinum is used as an electrode. Let's talk about why that is so. Hydrogen gas, as the name says, hydrogen gas. So it is a gas and we need our electrode to be a solid. But apart from platinum being a solid, what other properties does it possess? Platinum does not react with H+. So that is one of the reasons why it is being used as an electrode. And another reason is that platinum is a conductor. Platinum is a conductor. At 1.3, we're supposed to write down the name of component Q. This is a galvanic cell and component Q should be a salt bridge. So there we go. We have a salt bridge in 1.3.1 and 1.3.2. What is the standard reduction potential of the X half cell? Right, this is for 1 mark. And when you are familiar with this kind of questions, you're going to be able to answer it without any difficulties. But here we sort of have to take the long route so I can show you what is happening. Let's look at the information we have. We are told that the initial EMF that is registered is 0.31 volts. So the EMF of our cell initially is 0.31 volts. Right, now let's look at our setup. This is the positive electrode and this is the negative. In a galvanic cell, the positive is the cathode and the negative is the anode. So what are we saying? We're saying that the potential of our cell can be determined by saying the potential at the cathode minus the potential at the anode. So what is the potential of the cell? This is 0.31 being equals to the potential at the cathode. The potential at the cathode is the potential of the hydrogen gas, as we can clearly see that it is at the positive terminal. So we're going to have 0. If you look at your table for standard reduction potentials, the potential of hydrogen gas is 0 minus the potential at the anode. So minus the potential at the anode, which happens to be X. If you go ahead and find the reduction potential of X, you're going to realize that it is equals to minus 0.31 volts. So this is the answer. It is for 1 mark because it is easy to see without doing any calculation. But if you are not familiar with galvanic cells and the EMF of a cell, this is how we get to the answer. Right. 1.3.3, the half reaction that takes place at the cathode. The cathode is the positive terminal on our galvanic cell. So we have the hydrogen gas. The basics at the cathode is where reduction occurs. What is reduction? reduction is the gaining of electrons. So we're going to have 2H plus 2 electrons to give us hydrogen gas. This is the equation you find on your table of standard reduction potentials. If this was the anode, then we would write the equation in the following way. We would have hydrogen gas giving us 2H plus 2 electrons if it was at the anode. If it is the cathode, if it is at the cathode and the reduction is taking place, then this is our equation. Right. I'm just doing that for the sake of clarity. When you have equation which requires the half reaction at the anode. 1.4.1, the hydrogen half cell is now replaced with an MM2 plus half cell. The cell notation of this cell is and we're given the cell notation of the cell. Okay, well, this is our anode and this is our cathode. What is the initial reading on the voltmeter? It is given as 2.05 volts. And the first question, identify metal M. Show how you arrived at the answer. What information do we have? We know that the initial EMF of the cell is 2.05. We also have the reduction potential of X. We calculated it in 1.3.2. That is minus 0.31. We're trying to identify metal M. If we find the reduction potential of metal M, then we're going to be able to go to our standard reduction potential table and see which one it is with ease. So the potential of M is what we are interested in. So what can we say now? We can say that the reduction potential, not the reduction potential, but the EMF of our cell is equals to the reduction potential at the cathode minus the reduction potential at the anode. So the reduction potential of the cell, 2.05. That at the cathode we have X. So that is going to be minus 0.31 minus the reduction potential at the anode. So we take in minus 0.31 to the left hand side. We're going to have 2.36 being equals to minus the potential at the anode. If we divide both sides by minus 1, the potential at the anode will be equals to minus 2.36 volts. If we go to our table of standard reduction potentials, at the anode we have magnesium or Mg. That is our answer to 1.4.1. 1.4.2 is the cell reaction exothermic or endothermic. In a galvanic cell, the reaction will always be exothermic. Right, 1.5. The reading on the voltmeter becomes 0 after using this cell for several hours. Give a reason for this reading by referring to the cell reaction. Well, the cell reaction reaches equilibrium. That is why the reading on the voltmeter becomes 0 after some time. Besides concentration, write down 2 conditions needed for the hydrogen half cell to function under standard conditions. In total, we have 3 standard conditions, one being concentration at 1 mole per decimeter cube. 1.1, we're looking for the other 2 standard conditions. That is pressure. Pressure is one of our standard conditions at 101.3 kilopascals. Another standard condition we have is the temperature at 298 kelvins or 25 degrees Celsius. That is the answer to 1.1. Let's go ahead and take a look at 1.2. Give 2 reasons besides being a solid why platinum is suitable to be used as an electrode in the above cell. So as you can see here, where there is hydrogen gas, platinum is used as an electrode. Let's talk about why that is so. Hydrogen gas, as the name says, hydrogen gas. So it is a gas and we need our electrode to be a solid. But apart from platinum being a solid, what other properties does it possess? Platinum does not react with H+. So that is one of the reasons why it is being used as an electrode. And another reason is that platinum is a conductor. Platinum is a conductor. At 1.3, we're supposed to write down the name of component Q. This is a galvanic cell, and component Q should be a salt bridge. So there we go. We have a salt bridge in 1.3.1 and 1.3.2. What is the standard reduction potential of the X half cell? Right, this is for 1 mark. And when you are familiar with this kind of questions, you're going to be able to answer it without any difficulties. But here we sort of have to take the long route so I can show you what is happening. Let's look at the information we have. We are told that the initial EMF that is registered is 0.31 volts. So the EMF of our cell initially is 0.31 volts. Right, now let's look at our setup. This is the positive electrode and this is the negative. In a galvanic cell, the positive is the cathode and the negative is the anode. So what are we saying? We're saying that the potential of our cell can be determined by saying the potential at the cathode minus the potential at the anode. So what is the potential of the cell? This is 0.31 being equals to the potential at the cathode. The potential at the cathode is the potential of the hydrogen gas, as we can clearly see that it is at the positive terminal. So we're going to have 0. If you look at your table for standard reduction potentials, the potential of hydrogen gas is 0. Minus the potential at the anode. So minus the potential at the anode, which happens to be X. If you go ahead and find the reduction potential of X, you're going to realize that it is equals to minus 0.31 volts. So this is the answer. It is for 1 mark because it is easy to see without doing any calculation. But if you are not familiar with galvanic cells and the EMF of a cell, this is how we get to the answer. Right. 1.3.3, the half reaction that takes place at the cathode. The cathode is the positive terminal on our galvanic cell. So we have the hydrogen gas. The basics at the cathode is where reduction occurs. What is reduction? Reduction is the gaining of electrons. So we're going to have 2H plus 2 electrons to give us hydrogen gas. This is the equation you find on your table of standard reduction potentials. If this was the anode, then we would write the equation in the following way. We would have hydrogen gas giving us 2H plus 2 electrons if it was at the anode. If it is the cathode, if it is at the cathode and the reduction is taking place, then this is our equation. Right. I'm just doing that for the sake of clarity. When you have equation which requires the half reaction at the anode. 1.4.1, the hydrogen half cell is now replaced with an M2 plus half cell. The cell notation of this cell is and we're given the cell notation of the cell. Okay, well, this is our anode and this is our cathode. What is the initial reading on the voltmeter? It is given as 2.05 volts. And the first question, identify metal M. Show how you arrived at the answer. What information do we have? We know that the initial EMF of the cell is 2.05. We also have the reduction potential of X. We calculated it in 1.3.2. That is minus 0.31. We're trying to identify metal M. If we find the reduction potential of metal M, then we're going to be able to go to our standard reduction potential table and see which one it is with ease. So the potential of M is what we are interested in. So what can we say now? We can say that the reduction potential, not the reduction potential, but the EMF of our cell is equals to the reduction potential at the cathode minus the reduction potential at the anode. So the reduction potential of the cell, 2.05. That at the cathode we have X. So that is going to be minus 0.31 minus the reduction potential at the anode. So we take in minus 0.31 to the left hand side. We're going to have 2.36 being equals to minus the potential at the anode. If we divide both sides by minus 1, the potential at the anode will be equals to minus 2.36 volts. If we go to our table of standard reduction potentials, at the anode we have magnesium, or Mg. That is our answer to 1.4.1. 1.4.2 is the cell reaction exothermic or endothermic. In a galvanic cell, the reaction will always be exothermic. Right, 1.5. The reading on the voltmeter becomes 0 after using this cell for several hours. Give a reason for this reading by referring to the cell reaction. Well, the cell reaction reaches equilibrium. That is why the reading on the voltmeter becomes 0 after some time. A piece of zinc is placed in a test tube containing acidified MnO4-. After some time, it is found that a redox reaction has taken place. Use the table of standard reduction potentials to answer the following questions. Write down the name or formula of the reducing agent. On your table of standard reduction potentials, you have your reducing agents on the right and your oxidizing agents on the left. It should be easy to see that the reducing agent is zinc. Why are we saying that the reducing agent is zinc? That is the question in 8.1.2. So let's go ahead and address that. When we look at zinc 2 plus and MnO4 minus, MnO4 minus is a stronger oxidizing agent. So it will undergo a reduction, meaning that zinc, on the other hand, the piece which is on the right hand side, it's our stronger reducing agent. It is going to undergo oxidation to form zinc 2 plus 2 electrons. That is 8.1.2. Let's take a look at 8.2 and 8.2.1. So we have a standard electrochemical cell, and the first question is to write the function of component Y. Component Y is a salt bridge. There's a few things that a salt bridge does for an electrochemical cell. One, it completes the circuit. It also provides a path for movement of ions. That is just some of the functions of component Y, a salt bridge. 8.2.2, in which directions will electrons flow in the external circuit? Choose from Ni to Mi, Mi to Ni. It means that now we need to determine whether Ni or Mn is the anode or the cathode. We have to go back to our table of reduction potentials. Mn is a stronger reducing agent. So this is where oxidation takes place, and we know that oxidation takes place at the anode. While on the other hand, Ni will be our cathode. In a galvanic cell, the anode is negative and the cathode is positive. Even though current flows from positive to negative, electrons flow from negative to positive. So that is the direction of flow of electrons, Mn to Ni. 8.2.3, we're supposed to calculate the initial EMF of the cell. So let's go ahead and do that. The initial EMF of the cell will be equals to the reduction potential at the cathode minus the reduction potential at the anode. At the cathode, we have Ni with a reduction potential of minus 0.27 minus the reduction potential at the anode where we have Mn, that is minus 1.18. If you put that in your calculator, you should get 0.91 volts. This is quite an easy one. Right, 8.2.4. Write down the balanced equation for the net reaction taking place. Let's start with the anode where oxidation takes place. At the anode, we have Mn. So we're going to have Mn losing 2 electrons to form Mn2 plus 2 electrons. And then at the cathode, we have Ni2 plus 2 electrons to give us Ni. It is easy to see that in equation 1, we have a loss of electrons. And in equation 2, we have a gaining of electrons. So in order to find the net cell reaction, we add the left-hand sides of the two equations and the right-hand sides of the two equations. But what we can do, we can ignore the electrons. We have 2 electrons on the left and the 2 electrons on the right. They're just spectators. We're gonna ultimately have, so we're adding Mn and Ni2 plus. So we're gonna have Mn plus Ni2 plus to give us Mn2 plus Ni. So Mn2 plus Ni. This is the net cell reaction. 8.2.5. The concentration of Ni to the 2 plus is now increased. Will the reading of the voltmeter increase, decrease, or remain the same? Okay, let's go ahead and make sense of this one. The initial EMF of the cell is given by the reduction potential at the cathode minus the reduction potential at the anode. We have an increase of Ni2 plus, the concentration at the cathode. So if you increase the concentration at the cathode, then this reduction potential is gonna increase. If that reduction potential increases, it is easy to see that the reading on the voltmeter will also increase. But let's say, for instance, it was the concentration of Mn2 plus that was increased. Then the reduction potential at the anode would increase. And if the reduction potential at the anode is increasing, the reading on the voltmeter would decrease. But in our case, the reading on the voltmeter is increasing.
Is the reaction that occurs in this cell spontaneous? Write down only yes or no. Give a reason for the answer. That is 8.1, Prelim 2023. Let's take a look and see what is happening. So a galvanic cell is set up using an Mn and an unknown metal X. The initial EMF measured under standard conditions is 1.05 volts, as we can clearly see there. The electrons flow from the Mn to metal X in the external circuit, right? And then 8.1 is the reaction that occurs in this cell spontaneous. Yes, it is. And why do we say so? EMF is greater than 0. If the EMF in this cell is greater than 0, then the cell is spontaneous. This reaction does not need any external energy for it to occur, right? Does not need anything. It does not need power supply, unlike in an electrolytic cell. That is 8.1. Taking a look at 8.2, which electrode X or Mn is the anode. Okay, so the answer to this question is here in this statement. The electrons flow from the Mn to metal X in the external circuit. So we need to recall our basics with regards to a galvanic cell. The electrons, they flow from the anode to the cathode in the external circuit. So if they flow from Mn to metal X, then Mn should be the anode, and then the metal X should be the cathode. Clearly, the electrons flow from Mn to metal X in the external circuit. So Mn is the anode and X is the cathode. Okay, we're just applying the basics here. That is 8.2, 8.3. Use calculations to identify metal X. So we are given the initial EMF, which is said to be 1.05. But obviously, using our table of standard reduction potentials, we can obviously find the potential at the anode, which happens to be our cathode. So at the cathode, this is where we have our metal X. This is where we have X. And then at the anode, that's where we have Mn, like we've deduced. So now let's go down and look for our table of standard reduction potentials. We can use table 4a, we can use table 4b. All is well, right? There's no difference really. So let's go ahead and look for Mn and see where it is. So let's take a look. Mn, where do we find it at? We have Mn right there. So the reduction potential at the anode is minus 1.18. Okay, and then we know that the EMF of the cell is given by the reduction potential at the cathode minus the reduction potential at the anode. Okay, so the reduction potential at the cathode, that is where we have our metal X, right? So the potential of X. And then at the anode, we have minus 1.18. So 1.05 will be equals to the reduction potential at X plus 1.18. Okay, so the reduction potential at X will be equals to 1.05 minus 1.18. So that's more like saying 5 minus 18. So we get minus 0.13 volts as our reduction potential at the cathode. So still sticking to the table of standard reduction potential, it should be easy to see that at the cathode, if the reduction potential is minus 0.13, we must have PB. We can clearly see there that the reduction potential is minus 0.13. So right, X is PB. We can clearly see that. Right, that is 8.3. Let's take a look at 8.4. Right, 8.4.1. Write down the two standard conditions for this cell. Okay, we know fully well that we need the temperature to be 25 degrees Celsius, right, or 298 kelvins. That's one of the conditions that we need. Another condition we need is concentration to be 1 mole per decimeter cube. These are our standard conditions. Okay, 8.4.1. 8.4.2. On the other hand, we are looking for the cell notation. Okay, so obviously we know that we have what is happening at the anode, the salt bridge, and what is happening at the cathode, essentially. So at the anode, we have Mn, like we talked about, right? So we're going to have Mn, the metal, and then Mn to the 2 plus the salt bridge, and then Pb to the 2 plus, and then we have PB. Okay, we can show the states here that is a solid, that is also a solid, and here we have aqueous solutions, right? We can show the states. Yeah, we can even go further to show the concentration also, that the concentration of these aqueous solutions should be 1 mole per decimeter cube. Okay, that is 8.4.2. 8.4.3, reduction half reaction. Reduction half reaction. So reduction occurs at the cathode. That's where we have a gaining of electrons. So we're going to have Pb to the 2 plus, that gains 2 electrons to become Pb. There we go. Nothing complicated there whatsoever. That is the reduction of reaction. And then if the question was looking for the oxidation of reaction, we would have Mn giving off 2 electrons to become Mn to the 2 plus 2 electrons. And then we can sort of combine these two into overall cell reaction, right? To get Mn plus Pb to the 2 plus, giving us Mn to the 2 plus Pb. This will be the overall cell reaction. But anyway, stories.
A learner conducts 2 experiments to determine the reaction between copper and silver nitrate. In experiment 1, the learner adds a small amount of copper to a test tube containing silver nitrate. The solution changes from colorless to blue after a while. The first question, 2.1, we're supposed to define the term oxidizing agent. The oxidizing agent undergoes reduction. What is reduction? Reduction is the gaining of electrons. So the oxidizing agent is a substance that gains electrons, or rather a substance that is being reduced. That is the answer to 2.1. Let's take a look at 2.2. Explain why the solution turns blue by referring to the relative strength of the oxidizing agents. So let's go ahead and compare copper 2 plus, and silver plus. Let's go ahead and compare these two by referring to the relative strength of the oxidizing agents. Ag plus is a stronger oxidizing agent compared to copper 2 plus. We're going to have copper losing 2 electrons to form copper 2 plus. And this copper 2 plus is where the color blue is coming from. The color of copper 2 plus is actually blue. Let's take a look at 2.3. Experiment 2. So in experiment 2, the learner now sets up a galvanic cell as shown below. The cell functions under standard conditions. 2.3, write down the energy conversion that takes place in this cell. We know the energy conversion that takes place in a galvanic cell. That is chemical energy to electrical energy. Anyway, stories. Let's go ahead and take a look at 2.4. In which directions will N ions move in the salt bridge? Before we answer any of those questions, let's determine first whether copper or silver will be the anode or the cathode. Just like we have already deduced in 2.2, copper is going under oxidation. It is getting oxidized. Oxidation occurs at the anode. So this is our anode and this is our cathode. Now we can answer our questions. 2.4, in which directions A or B will N ions move in the salt bridge? So N ions, they move towards the anode, and cat ions move towards the cathode. It is easy to see that the N ions are moving towards A. 2.5, calculate the EMF of the above cell under standard conditions. So the EMF of the above cell under standard conditions, we're going to have the reduction potential at the cathode minus the reduction potential at the anode. This is equals to, at the cathode we have silver. What is the reduction potential? 0.8 minus the reduction potential of copper 2 plus. That is, you have to make sure that you're picking the right one because there's a few coppers on your table of standard reduction potentials. It is 0.34. If you put this in your calculator or you just compute it in your head, you shall get 0.46 volts as the initial EMF of the cell above. That is 2.5. Let's take a look at 2.6. Write down the balance equation for the net reaction that takes place in this cell. Well, at the anode, we have copper getting oxidized to copper 2 plus 2 electrons. And then at the cathode, we have silver plus an electron to give us silver. Oxidation half reaction, reduction half reaction. If you look at the oxidation half reaction, we have 2 electrons. If you look at the reduction half reaction, we have 1 electron. So what you want to do in a case like this is to multiply out by 2 where you have only 1 electron. So let's go ahead and do that here at the cathode. We're going to have 2 Ag plus plus 2 electrons to give us 2 Ag. You're gonna see right now why I'm saying we should do that. Now when you have these two equations, what you need to do is to add the left hand sides together and you add the right hand sides. Let's go ahead and do that. If we do that, we're gonna have copper plus 2 Ag plus 2 electrons to give us copper 2 plus 2 electrons plus 2 Ag. In a case like this, we call these electrons spectators. They're not taking part in our reaction. So we can drop them and be left with Cu plus 2 Ag plus to give us Cu2 plus 2 Ag. And this is our overall reaction. In an exam situation, this is what is needed. All of this junk is just me trying to show you how it comes about. 2.7, will the addition of 100 centimeter cube of 1 mole per decimeter cube of silver nitrate solution to the silver half cell influence the initial EMF of the cell? Write down increase, decrease, or remain the same. In our standard conditions, with regards to the concentration, we need the concentration to be 1 mole per decimeter cube. So this change is not changing our standard conditions because the concentration is still 1 mole per decimeter cube. So the initial EMF will remain unchanged. The answer here is remains the same. What type of reaction takes place in this cell? Well, it is a galvanic cell. So the reaction taking place is a redox. Why are we saying it is a redox? That is because there is a transfer of electrons. Let's look at 3.2. Which electrode, P or Q, is magnesium? Give a reason for the answer. So let's go ahead and look at our electrodes. We have electrode P and electrode Q. P is negative and Q happens to be positive. In a galvanic cell, the negative electrode is where you find your anode. On the other hand, the positive electrode is where you find your cathode. Between magnesium and lead, which one is undergoing oxidation? Which one will be our anode? We need to go to our table of reduction potentials and determine which one is a stronger reducing agent. Magnesium is a stronger reducing agent. It is going to be electrode P as it is negative and consequently the anode. So the reason we have to give here is that Mg is a stronger reducing agent. So between magnesium and lead, magnesium is a stronger reducing agent. Let's take a look at 3.3, 3.3.1. Write down the following: the standard conditions under which this cell functions. This is a galvanic cell. We have 3 standard conditions. Well, one being the temperature at 25 degrees Celsius or 298 kelvins. Another condition is the concentration at 1 mole per decimeter cube. Lastly, we have the pressure. But pressure doesn't apply in our case in this cell. That is because we don't have any gas. So in this cell, we're supposed to only mention temperature and concentration. That is another trick you have to be aware of. Right. 3.2. We're supposed to write the cell notation for this cell. As soon as the question says cell notation, salt bridge, and then I can start thinking about all the other things. We know fully well that we're going to have the anode at the left-hand side and the cathode at the right-hand side. The anode is magnesium, so we're going to have magnesium 2+, and the cathode is lead, so we're going to have Pb 2+ and Pb. And just like that, we have our cell notation. 3.3. name or formula of the oxidizing agent in the cell. The oxidizing agent is the species that gains the electrons, that is experiencing a reduction. Well, in our case, the oxidation half reaction, we're going to have Mg giving us Mg2 plus 2 electrons. This Mg is our reducing agent. And on the other hand, the reduction of reaction, we're going to have Pb2 plus 2 electrons to give us lead. This lead 2 plus is our oxidizing agent. It is the substance that is gaining electrons. So this is our answer to 3.3.3. Lead ions. The following question, 3.4, we're supposed to calculate the EMF of the cell above under standard conditions. Right, the EMF of the above cell will be equals to the standard reduction potential of the cathode minus the standard reduction potential of the anode. At the cathode, we have lead, and the lead has a standard reduction potential of minus 0.13 minus the standard reduction potential at the anode. At the anode, we have magnesium, that is minus 2.36. If you put that in your calculator, you should get 2.23 volts as the initial EMF of the above cell under standard conditions. The tricky equations, 3.5. How will the voltmeter reading change if the size of electrode P is increased? So increasing the size of an electrode does not affect the EMF. So the answer to 3.5.1 will be remains the same. Right, and now let's take a look at 3.5.2. If the initial concentration of the electrolyte in half cell B is increased. So increasing the initial concentration of the electrolyte will increase the reduction potential of that species or of that electrode. So let's take a look at our equation. The EMF of our cell is equals to the potential at the cathode minus the potential at the anode. We are increasing the concentration in half cell B. Half cell B is where we have our cathode. So the potential at the cathode is increasing. If the potential at the cathode is increasing and the potential at the anode remains the same, then the initial EMF of the cell is going to increase. So the answer here is increases. Yeah, when we increase the concentration, the reduction potential increases, and when we decrease the concentration, the reduction potential decreases. But you cannot just say that EMF will increase because concentration is going to increase. You have to look at, is it the concentration at the cathode, or is it the concentration at the anode? That is also going to matter. Learners are given two half cells, half cell 1 and half cell 2. During an investigation to identify the two half cells, the learners connect each half cell alternately to a cadmium half cell under standard conditions. We have the results for the first combination and the second combination. The first question, 4.01, write down 3 conditions needed for these cells to function as standard cells. Well, the pressure at 101.3 kilopascals. Another condition is the temperature at 25 degrees Celsius. And lastly, we need the concentration at 1 mole per decimeter cube. This is our 3 standard conditions. Let's go to 4.2, 4.2.1. For the first combination, let's identify the anode of the cell. So in our first combination, we are given the net cell reaction. Well, we have cadmium losing 2 electrons to form cadmium. So that is our anode. Our anode is cadmium. So we're going to have that there. At the anode, oxidation occurs. There's a loss of electrons. And as we can see, cadmium loses electrons in our first combination. And 4.2.2, we're supposed to identify Q using a suitable calculation. Well, what information do we have? We have the EMF of our cell. It is equals to 0.13 volts. We have the standard reduction potential of cadmium. It is equals to minus 0.4. So in order for us to determine Q, we're going to say that the EMF of our cell will be equals to the reduction potential at the cathode minus the reduction potential at the anode. So we're going to have 0.13 being equals to the reduction potential at the cathode. At the cathode is where we have Q, as we have already deduced that the anode is cadmium. And the reduction potential of cadmium, that is minus 0.4. So we're going to have 0.13 being equals to the reduction potential of Q plus 0.4. It should be easy to see that the reduction potential of Q will be equals to 0.13 minus 0.4, which is just equals to minus 0.27 volts. So Q is nickel if you go to your table of standard reduction potentials. Right, that is 4.2.2. That is how we solve those kind of questions. Let's go ahead and take a look at 4.3. So in 4.3, we're interested in our second combination. And 4.3.1, the oxidation of reaction. Well, what happened in reaction 1 is still happening in reaction 2. Cadmium is losing electrons. So that is our oxidation of reaction. We're going to have cadmium giving us cadmium 2 plus 2 electrons as our oxidation of reaction. That is 4.3.1. Let's go ahead and do 4.3.2. Name or formula of the metal used in the cathode compartment. Cadmium is our anode, so our cathode is R2, which happens to be a gas. If we have a gas, our electrode is going to be platinum. That is 4.3.2. The last question, 4.4. Identify the following species in order of increasing oxidizing ability. So the oxidizing agent undergoes reduction. We need to know that. So let's take a look at this. Between Q to the 2 plus and CD to the 2 plus, Q to the 2 plus is a strong oxidizing agent as it goes under reduction. So we know that Q to the 2 plus is a stronger oxidizing agent compared to CD2 plus. If you look at our second combination, we can come to the conclusion that R2 is a stronger oxidizing agent compared to CD2 plus because it also undergoes a reduction. The only thing that we now have to figure out is which one is a stronger oxidizing agent between Q to the 2 plus and R2. With cadmium, Q to the 2 plus and R2 act as our cathode. So whatever oxidizing agent between these two will lead to a higher EMF will be our strongest oxidizing agent. And if you look at the cell potential, R2 is giving us the highest cell potential. So we can say that CD2 plus is the weakest, followed by Q to the 2 plus. And the strongest oxidizing agent is R2.